ওটা সবাই তো দিয়ে নিয়েই যায়, তারপরে ওইটা ছেড়ে দেয়। সেটা কতদিন কি হয়েছে আমি জানি না, কিন্তু এখন মনে হয় হায়দ্রাবাদ ইউনিভার্সিটিতেই আছে।
হ্যাঁ, আমাদের এখানে টকও দিয়েছিল যখন এসছিলেন, আমাদের এখানে টকও দিয়েছিল, কথাবার্তা হয়েছিল, আমরাও গেছিলাম।
হ্যাঁ, তোমরা ওনার সঙ্গেও যোগাযোগ রাখতে পারো, কন্ডেন্স ম্যাটার ফিল্ড আছে। আর নির্মাণের কত দূরে তোমাদের ওখান থেকে?
নির্মাণ প্রায় 30 কিলোমিটার মতো দূর আমাদের ইনস্টিটিউট থেকে।
তোমার দেখা সাক্ষাৎ হয় না ফোনেই কথা?
উইকেন্ডে তো আমরা এখানে একসঙ্গে মানে মাঝে মাঝেই দেখা হয়, উইকেন্ডে কাজ করি বসে একসঙ্গে।
ও বাহ, খুব সুন্দর। এইটা হলে খুব ভালো। বাড়ির সবাই ভালো আছে তো?
হ্যাঁ, বাড়ির সবাই ভালো আছে।
তোমার পুরো ফ্যামিলি এখন ওখানেই থাকে, তাই তো?
হ্যাঁ হ্যাঁ, পুরো ফ্যামিলি এখন হায়দ্রাবাদেই।
তুমি তো আগে কি ভেতরে থাকতে?
হ্যাঁ, আমি বরাবরই ক্যাম্পাসের ভেতরেই, মানে ওদের কোয়ার্টার্সেই থাকি।
আচ্ছা, এখনো সেটাই করছো? আচ্ছা।
গুড মর্নিং দেবাশিস দা।
দেবাশিস অ্যাপিয়ার করে গেছে।
গুড মর্নিং।
হ্যাঁ, কেমন আছেন দেবাশিস দা?
এই মোটামুটি চলছে আর কি সবই। তোমাদের ওখানে আবার সেই কোয়েস্টের একটা কনফারেন্স হবে বোধহয়, তোমরা হোস্ট করছো?
হ্যাঁ হ্যাঁ, আমরা হোস্ট করছি, কোয়েস্টে কনফারেন্স হবে।
সেটা অনলাইন না অফলাইন করছো?
ওটা আপাতত প্ল্যান আছে হাইব্রিড। হ্যাঁ, মানে কি দু একজনকে বোধহয়
কাছাকাছি যদি ওখানে চলে আসে এই আর কি।
চলে আসে, মানে অপশন দেওয়া হবে যে যদি আসতে চায় তাহলে ঠিক আছে, না হলে অনলাইন। হ্যাঁ,
ভালো কথা। সুভাষিস বোধহয় না আজকে টকে আছে?
হ্যাঁ হ্যাঁ, সুভাষিস দা আছে।
ইন্দ্রনীল, শুনতে পাচ্ছ?
হ্যাঁ দেবাশিস দা বলুন। হ্যাঁ,
বলছি তুমি একটা জিনিস একটু খেয়াল রেখো, ওই যারা কন্ট্রিবিউটেড টক আছে অর্থাৎ ওই 20 মিনিটের মধ্যে 17 থেকে 18 মিনিট হচ্ছে তাদের বলার সময়, আর 2 থেকে 3 মিনিট ডিসকাশন, ঠিক আছে? হ্যাঁ, এইটা ভেঙে নিই।
আচ্ছা। আর এমনি ইনভাইটেড টকের 35 মিনিট বলার সময়, তাই তো?
হ্যাঁ, 35 প্লাস
ইনভাইটেড টক,
ঠিক আছে।
মানে সুভাষিস দা বোধহয় ইনভাইটেড টক আছে
40 মিনিট আছে। হ্যাঁ হ্যাঁ হ্যাঁ, ইনভাইটেডটা 40 মিনিট আছে প্রথমে। হ্যাঁ, ও 35 প্লাস ঠিক আছে।
আচ্ছা আচ্ছা,
ঠিক আছে। কালকে লাস্টে এর লেকচার শুনতে পেয়েছো? গুগলাদের শুনেছিলে না শুনতে পাওনি? কাল রাত্রে। হ্যালো, তুমি কালকে জয়েন করেছিলে বিকালের দিকে? এ ছিল, গিলাদ ছিল আর অ্যান্টনি আসিন ছিল। তো দুজনেই খুব ভালো বলেছেন অ্যাকচুয়ালি। আসলে
না, কালকে জয়েন করা হয়নি, কালকে আমার অফিসে কিছু কাজ ছিল, সেই জন্য কালকে জয়েন করা হয়নি।
লাইভ স্ট্রিমিংটা তো আছে, ইউটিউবে দেখতে পেয়ে যাবে, ওগুলো দেখে নিও। দুজনেই খুব ভালো লেকচার দিয়েছেন।
হ্যাঁ হ্যাঁ, সবকটা টকই ইউটিউবে আছে না রেকর্ডেড?
হ্যাঁ, সব একমাত্র পরের দিকে ওই বারবারা ক্রাউসের একটা লেকচার, সেটা বোধহয় যাবে না, পরের সপ্তাহে আছে। ওইটা ছাড়া সবই ইউটিউবে থাকবে। হ্যাঁ,
সুভাষিস কখন বেরোচ্ছ?
আমি 11:30, কিন্তু ইন্দ্রাণী বেরোতে পারবে না, এসে গেছে, ওর মাথাটা ধরেছে। হ্যাঁ, আর যাচ্ছে না, আমি যাচ্ছি শুধু। হ্যাঁ, আমি তাহলে স্টার্ট করে দেবো। ঠিক আছে, আমি ইন্দ্রনীলকে বলে দেবো স্টার্ট করে দিতে। ঠিক আছে, ওকে ওকে।
ঠিক আছে।
হাই শুভাশিস।
ও শুভাশিস দিছে।
শুভাশিস,
শুভাশিসদের মধ্যে মাইকটা অন দেখাচ্ছে না, কারণ
হ্যাঁ।
মাইকটা, হ্যাঁ এবার ঠিক আছে, এবার ঠিক আছে, এবার মাইকটা এসছে।
ভিডিওটাও এখন কাজ করছে না এখনো পর্যন্ত ওর। ঠিক আছে, ওটা অন করে নেবে। আমাদের কনফারেন্সে রোজ কয়েকজন বয়স্ক মানুষ পার্টিসিপেট করছেন, তার মধ্যে বিদেশি বলছি, তার মধ্যে একজন হচ্ছে রিচার্ড ওয়ার্নার, বুঝলে? রেইনার্ড ওয়ার্নার, রিচার্ড বলছি, রেইনার্ড ওয়ার্নার, জানো কি ইন্দ্রনীল? হ্যাঁ, okay, the morning session will start very short, within 2 minutes. I request Dr. Indranil Chakraborty to chair this session. He is a good scientist in the field of quantum information computation as well as হ্যাঁ, গলাটা কেটে কেটে যাচ্ছে। হ্যাঁ, কিছু একটা প্রবলেম হচ্ছে, বলছি এখন শুনতে পাচ্ছ? হ্যালো হ্যালো।
হ্যাঁ দেবাশিস দা, ভয়েসটা আপনার কেটে কেটে যাচ্ছে, ইউর ভয়েস ইজ ব্রেকিং ডাউন।
অ্যাকচুয়ালি তোমার ওখানে বোধহয় প্রবলেম হচ্ছে, কারণ তোমার ছবিটা ঘুরছে না, বুঝলে? হতে পারে। ওকে ওকে, এখন ঠিক আছে, এখন শুনতে পাচ্ছ ঠিক করে? হ্যালো, শুনতে পাচ্ছ ইন্দ্রনীল? ডু ইউ হিয়ার মি? ইন্দ্রনীল, তুমি কি শুনতে পাচ্ছ?
হ্যাঁ এখন শুনতে পাচ্ছি, হ্যাঁ এখন শুনতে পাচ্ছি।
ওকে ওকে,
হ্যাঁ শুনতে পাচ্ছি এখন।
Dr. Indranil Chakraborty is a good scientist in the field of quantum information computation. He will chair this morning session. I invite him to chair this session. Okay, Indranil, you start.
Thank you, Devashishda, for such a nice introduction, and I welcome all the participants and the speakers to this 5th day of the International Conference on Quantum Information Foundation, organized by both Indian Statistical Institute, University of Calcutta, and SN Bose Center for National Basic Sciences. So we have today with us couple of speakers. We have a very fast talk with from the invited speaker and Professor Subhashish Banerjee, and he will be talking about quantum speed limit. We will be talking about quantum speed limit, and before I request Professor Banerjee to give his talk. I would like to take the privilege of introducing Professor Banerjee, and with Professor Banerjee for 10 years. So he is right now the professor in the Department of Physics, Indian Institute of Technology, Jodhpur, India. He obtained his PhD degree from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi, in the year 2003. He has been involved in the study of quantum theory of open systems since his PhD days. A major theme of his works has been to see how the theory of open quantum systems provides a common umbrella to the understanding the various facets of quantum optics, quantum information processing tasks, and quantum computing, quantum cryptography also. So he has also worked in the area of foundation of quantum mechanics, relativistic quantum mechanics, and field theory. He has published 2 books and more than 67 articles in national and international journals of repute. So I request to Professor Subhashish Banerjee to give talk on his on quantum speed limit and non-Markovian physics. Professor Banerjee. I think Professor Banerjee is not audible. The mic is muted.
Indranil, am I audible?
Yes, Subhashish, you are audible.
Okay. And my screen is also visible?
Also visible.
Okay. Great. It's very nice to hear you guys. Devashish, and
yes.
I could see Guruda also.
And now
that is very nice. Hello.
You have some problem with
okay, then if I am clear, then I will start. I like to thank, I like to thank the organizers for organizing this beautiful thing. It's a very long and elaborate schedule you have. My only pang is that not able to physically come because ISI Kolkata, I have a lot of good memories of this place. I hope things get better and we are able to physically make these visits. So I start with my talk because my time, I have to keep track of the time. So as the title suggests, I want to talk about quantum speed limits and non-Markovian physics. So quantum speed limit, basically, there are 2 more talks scheduled today on quantum speed limit, so you can understand its impact on quantum information. The quantum speed limit is intrinsically connected with the basic evolution of the underlying quantum dynamics and also its geometrical facets. Now, when I think about evolution, I generally tend to think about open system evolution, which is basically evolution where the system of interest moves forward, taking into account the effects of its ambient environment. That causes all kinds of interesting, though sometimes complex situations. definitely non-unitary aspects like decoherence and dissipation are a part of it. Now, open systems is a very vast subject, and in the last 10 years or so, it has become very popular in the quantum information community, though it was a prolific subject long before that. Now, even within quantum systems, in recent times, non-Markovian phenomena has become a subject of great interest. So I would like to see how the impact of non-Markovian processes impacts the evolution of quantum speed. That is the basic motivation for my presentation. Very briefly, quantum speed limit has a history which is entrenched in the foundations of quantum mechanics. In particular, the interpretation of energy-time uncertainty principle. So Mandelstam and Tam produced this interpretation about 20 years after the foundation of quantum mechanics in the 1940s. And they interpreted this energy-time uncertainty relation as an intrinsic time scale of the underlying unitary dynamics. This was after some more time passed, because their thing was dependent upon the variance in energy, and it was found that in some scenarios, the variance may not be very useful. So another useful bound was developed by Margolis and Levitan, where this bound dependent on the average of the energy. And then very soon, subsequently, a uniform bound, a tight bound was developed. And Aharonov and Bohm formalized energy time uncertainty principle as a bound on the minimal time of evolution, of the quantum evolution. Now, this was subsequently by many workers generalized to, because these things were for initial pure states and unitary dynamics. Now these were then generalized to initial mixed states and driven dynamics. There is a very good review by Defner and Campbell in JPhys in 2017. I would suggest people to look at it. It covers this field in a very comprehensive manner. So there they talk about these developments, and it can be seen that a lot of these developments were connected with Ullmann's conception of distance, basically. From the pure state to the mixed state, the notion of distance on the Hilbert space is basically realized by this Duras angle. This is a contribution by Ullmann in the mid-1970s, and this was the crucial ingredient to the development of these bounds. When we come to the open system counterpart of these bounds subsequently, we'll see that the numerators are kind of same. It's only the denominators that get changed. So these variances and these averages then are replaced by the generators of the master equations or the evolutions that underlying the open quantum systems. So this underlying concept remains more or less the same. Now, very briefly, open quantum system is basically about trying to develop a unified theory of how systematically one can deal with non-unitary processes like damping and dephasing in quantum systems. So basically, the whole philosophy hinges on the fact that all real systems of interest are basically open, because even vacuum has spontaneous emission, right? So all systems of interest have basically an environment, and spontaneous emission also is irreversible. So this can be modeled systematically by considering the evolution of the joint system and then taking a partial trace over the reservoir degrees of freedom, so that you basically concentrate on the system that you want to think about, the photon or the electron or whatever. Now, its roots are pretty old. For example, it has been used extensively since the 1960s In fact, even before that, in the field of nuclear physics, it was used, and then in the field of quantum optics in the 1960s, it was used. This is kind of summarized in Louisel's work. And then it was made elaborate in other areas such as condensed matter by Caldera Leggett and their whole work. Then the German team of Hermann Grabert and Zurek, of course, took this in the direction of foundational levels like decoherence and pointer states and things like that. And there are many other applications of this. An interesting event that happened, a series of events that happened that made this field it's directly pertinent to quantum information, the series of experiments by Vineland, this is Touche and Meart at Boulder, and by Sergei Herosh's group in Paris, where they concentrated on different systems like rubidium atoms and cavity quantum electrodynamics, but their aims were to basically see how quantitatively can we characterize these processes like decoherence and all that. So, and they were successful. So this gave an experimental implication to this field. So then one can easily see chronologically why this field now becomes very pertinent to the field of quantum information and computation. So what I told in words, just in an equation, we have the total system, we consider it to be a closed system composed of the system, the reservoir, and the interaction. Evolve it unitarily. We basically generally talk about density matrices in this area. And then because I'm not interested in this entire thing, so I'm interested in this S. So I take a partial trace of this. And the dynamics of this is sometimes represented by what are known as master equations and things like that. So there are many, many master equations, and I'll give one or two examples as I proceed. This is perhaps the most well-known form of that master equation. It's called the Lindblad, or in full form these days, it's more specifically called the GKSL master equation after Gorini, Kosakovsky, Sudarshan, and Lindblad. So basically, it is a semi-group kind of evolution. And it's mathematically very rich, but physically one can unbox it kind of and just pin it down to the three assumptions, which are the bond, which is weak coupling between the system and reservoir, Markov, which is a memoryless evolution, and rotating wave approximation, which happens when the system dynamics is fast compared to the relaxation dynamics. And as it so happens, a lot of quantum optical processes actually obey these conditions, and therefore a lot of quantum optics and therefore a lot of quantum information also gets described by this Lindblad equation, which is the simplest form one can think of a non-unitary evolution. So a kind of Lindblad looks something like this. This is like a two-level system interacting with the thermal bath. So this is this N thermal is a thermal term which will go to zero at zero temperature, but this term will survive. So this is the contributor to the spontaneous emission term. And this can be massaged, that whole equation can be massaged and put into this form. This is the form of the GKSL or the Lindblad form. And this is what is well known, but I'm not going to talk about this. This is not of the subject of this discussion here. Now, what I want to focus on is non-Markovian evolution. So non-Markovian evolution, as you can probably guess, because Markovian, this Lindblad evolution is basically constrained by a number of physical assumptions. It is quite natural to assume that some of these assumptions, or if not all of them, would be relaxed sometimes or the other. In such a scenario, the evolution will no longer be described by that Lindblad or GKSL kind of master equation. So such evolutions are called non-Markovian evolutions. So there's a lot of development in this field. I'll cover briefly some of these developments because I'll need it for using in the discussion in quantum speed limit. A very useful characterization of these things was given by HCLA. This is Hall, Kresser, Lee, Anderson. This is Michael Hall. This is in 2014. They developed a master equation, a time local master equation, which is a generalization of the usual Lindbladian form. And this generator, just by requiring the requirements of that the master equation must preserve hermiticity and trace, can be shown to have this form. So this form is very similar to the Lindblad form. Only difference is this term here is basically time dependent, whereas in the original Lindblad form, this is time independent. Now, if these coefficients here, these are the various decay rates, if we borrow the terminology from the Lindblad. Now, because if you recollect, I told you when temperature is 0, this still a part of it survives, and this is called spontaneous emission that contributes. So that's a decay rate. So if this is greater than 0 or equal to 0, then the resulting dynamics for all time, then the resulting dynamics is completely positive. So another aspect of this, which was developed almost a little earlier, maybe around 2008 to 2010, there were two developments. One was in the divisibility of dynamical maps. This was the Rivas, Volga, Plenio, RHP kind of thing. And the other was this information backflow by Brouwer, Lane, and Pilou. And this is the BLP kind of thing. So in the RSP kind of scenario, you concentrate on the map and you concentrate on what is this. Any map can be broken up. If it's a CPTP map, it's completely broken up into this form. It's called the intermediate. Now, the simplest example of a divisible, so if it is divisible means this kind of thing holds for any kind of time domain. So if it's a divisible, a simplest example of this is a dynamical semigroup, which is generated by the Lindblad. This is basically that. So that's the reason why it is so nice to work with mathematically also. But one need not stop here. It could also be, one can define maps where these generators are time dependent, then there basically a time ordering operations will also have to be carried out. So this is basically that. Now, it was shown, it was quickly realized that positivity of these decay rates is equivalent to divisibility of the underlying map. And this was kind of made very clear in this HCLA work. Now this RHP measure, which is built upon the CP divisibility or indivisibility, if I may say that. So there, the non-Markovianity is characterized by the intermediate map being CP indivisible. So they check this out by a very simple idea of using the Choi-Jamyalski isomorphism. So this is the intermediate map acting on one part of the maximally entangled state. Take its trace distance. So if it is basically CP indivisible, then this trace distance will pick up a value which will be greater than 1, and therefore when you subtract it with 1, there will be something which is greater than 0. Whereas if it is CP divisible, it will give a value 0. So their idea was this kind of thing can be quickly seen and as a kind of a indicator of whether this is CP divisible or not, and they identified their non-Markovianity with this thing, that it is CP indivisible. A related but independent direction in which these developments took place was this idea of information backflow, which is basically what is the BLP measure, Brouwer-Lane-Pilou measure. So basically this is connected with the distinguishability of states, this D. Now this distinguishability is basically the trace distance. So this is therefore a very popular measure if you look into the literature. This actually is fairly easy to compute and gives, for example, some noise channels like the random telegraph noise channels. It gives very drastic results, which basically is boils down to the fact that if this trace distance shows some break in monotonicity, then basically this means that there is memory, because this is what is indicated, because this trace distance, which in any case has these properties, which I'm sure all of you are familiar with. So this is subadditive, invariant under unitary transformation, and under quantum operation is a contraction. Now, basically, the whole idea was very simple. When a quantum process reduces the distinguishability of states, then
ये क्यों आ जाता है? ये
Hello?
मुझे नहीं चाहिए, स्पीक नहीं चाहिए.
Was there a question there? Okay. Basically, a quantum process reduces the distinguishability. When it reduces the distinguishability of state, the information is flowing from the system to the environment. So correspondingly, when there is an increase of distinguishability, it signifies that information is flowing back from the environment to the system. So basically, in the case of, for example, if the evolution is Lindbladian, then you'll see that this basically, this feature is never there, basically. So this definition of memory was quantized by these people by a very simple idea. Basically, you take d by dt of this trace distance. Now, as between two states, as they evolve with time. So if there is any, so if it's, suppose it's a Lindbladian evolution, then it will always, this will always decrease. So then d by dt will be less than 0. But if it has some kind of an information backflow in it, then there will be some scenarios where this will actually increase. So in that case, this will be greater than 0. So you pick up those instances where these are greater than 0 and basically sum that up. And that was the measure. So that was the measure which is nowadays called the BLP measure. Now, much more recently, we, with my colleagues Srikanth and his student Srikanth, both have the same kind of names. We kind of identified another feature of this memory, which is called temporal self-similarity, and which is that the property of a system dynamics, where the propagator between two intermediate states is independent of the initial time. So this actually is very interesting, and but I won't have too much time to speak about it here. But the fact was, we were led to this because there are certain processes which are actually CP divisible. Things like, for example, the modified Holstein-Uhlenbeck noise and the PLN noise, but they were they also had operational. They were doing operationally showing aspects of memory, such as they were kind of slowing down the process of entanglement, sudden death, and things like that. So how to quantify those processes? Because you see, RHP and BLP will give a measure 0 there, will give an answer 0 there. So it was found that this is a kind of even a stronger concept of memorylessness than CP divisibility, because there could be some CP maps, that is like this OUN and PLN, which are not quantum dynamical semigroup, but which deviate from that, and that deviation can capture these things. Of course, those evolutions, like I told you, RTN, which show all memory in all kinds of measures, will also show up here. But these measures, these noises which don't show up there, will also be able, one will be able to identify this. So temporal self-similarity could be identified with the quantum dynamical semigroup generated by the Lindblad evolution. So any deviation from this makes the map dependent on the initial time. Now, I will very quickly take you through, without going to too much detail, what is this scenario for this OUN and PLN noise. So this is the master equation for that. This is a typical master equation for any dephasing process. We'll see that I'll be making use of this master equation in the quantum speed limit scenario also. Now these decay rates have this form. And we can find out what their semi-group limits are. This is the starred ones. The strategy was to take the intermediate map of this process, find out its Choi matrix. And it turned out from this Choi matrix, it can be seen that these terms here, under no circumstances, one can get rid of their independence of the initial time t0. So see, there always remains the lingering memory of the initial time t0. So this means that these evolutions encode a memory which is basically coming from deviation from temporal cell similarity. If you basically take this QDS, the quantum dynamical semi-group limit, and substitute it there, then it is it's actually trivial to see that in that case, there is no dependence on the intermediate time, and then this is actually memoryless. So you see, these give practical implication of such weaker than CP indivisible memory-like effects. And this, in the case of OUN models, in fact, around 2008, Yu and Eberle used it to study its impact on the prolongation of the time to entanglement sudden death. And later on, we saw that this kind of thing was useful to counteract decoherence in quantum box. This I will skip because this is just like showing that the amplitude damping channel, which is one of the simplest channels generated by the Lindblad evolution, is temporally self-similar. Now, basically, if we have a map, then the map can also be written in terms of generators. And roughly speaking, this measure is basically about taking the deviation of these generators. This star here corresponds to the QDS limit of this channel. Okay, and this LT would be the generator of the channel under consideration, for example, OUN or something like that. So you take this, for example, the trace norm, and do this, and this kind of thing. This, what we call this measure, this has some interesting, nice consistency properties. And this was very satisfying in the sense that we could show that, say, for example, this curve here, this is the PLN curve, or this dotted curve here, this blue dotted curve is the OUN curve. So for RHP, this will give a result 0. So there's no way to explain U and Eberle's result using that. But in our thing, if you use this temporal cell similarity, it is easy to see that it is basically encoding a memory. So this feature gets computed, and also these are two noise channels I will be using subsequently in the speed limit thing. This is called the non-Markovian amplitude damping channel, and the RTN channel, which is the random telegraph noise channel. These are, of course, these can be identified even with the BLP measure. And as you can see here, the present measure is also able to identify them. So it is consistent with the existing measures in literature. Now, having talked about a little bit of speed limit and basically in giving you a nutshell description of some of the basic identifiers of non-Markovian memory in evolutions, in order to combine them together and see what happens. So this, now we come to quantum speed limit. So quantum speed limit, of course, is defines a bound on the minimal time required for quantum system to evolve. And in the case of open quantum systems, basically one uses different distance measures of quantum states. So there are various versions of open system measures for quantum speed limits. Some of them belong to the category of the Mandelstam-Tamm bound, which are basically rely on the Hilbert-Schmidt norms. and the other which are also on the Margosa-Levitin bounds, which rely on the trace norms and operator norms of the generators. I'll just show you what those things are one by one. Some of the prominent things that we have used are basically this. So this was introduced by Prenyu, Holga and their group, where they bounded the evolution of speed limit of open quantum systems in terms of the relative purity relative purity. So this theta is basically relative purity here, cos inverse of relative purity here. And these are Krauss operators characterizing the noisy channel basically, because at the level of maps, one can actually think of supplementing the master equation by Krauss operator form, which again, to be fair about it, should be actually called a Sudarshan-Krauss form, if one goes into the historical roots of this subject. Now, this was a fairly, this was one of the first works in this direction, and but you can see it's fairly recent, 2013. Then this was followed up almost back to back with the Davidovich's group, where their ideas were similar, but again the methodology was different. So there, in fact, instead of this relative purity, they applied a more geometric measure, which is basically they relied on quantum Fisher information, which is basically comes when one tries to find out the distance between two states on which could be mixed in general on the Hilbert space. So then you have the Bourès matrix there, and if you expand that and keep up to the second order term, the square root of that is basically the Fisher information. So if you take the d by dt of that one, it is very easy to see why the speed should be related to the square root of the quantum Fisher information. So this comes from a purely geometric understanding. So this thing comes from a dynamical perspective. This comes from a geometric perspective. And these two were then combined together in the almost the same period of time by Defner and Lutz and their group, where they basically made a tight bound which has this form. And if you just throw back your mind into the form which I showed you for tau QSL for the case of generalized mixed states, you will see it's almost similar. The numerator contains this B here is basically the Bourès matrix, and the denominator has been changed. The denominator here, there was this variance of the Hamiltonian or the expectation value of the Hamiltonian. Here it is basically some of these operators which could be in the operator norm or the trace norm or the Hilbert-Schmidt norm, and these are basically this curly L rho T is basically the generator of the evolution. So one can write a generalized form of the master equation as d rho by dt is equal to this curl of L rho. So this encapsulates the open quantum system aspect. So you see, the numerator is the same everywhere. It is just the denominator which changes. And from this result that the operator norm is less, so one can see basically typically the 1 over operator norm here would maximize this thing. Here, of course, this Bourès angle is related to the fidelity. This is Kosakovsky's contribution, and which, as you know, is basically this for generalized mixed states, and it reduces to the overlap between the two states for pure states. Now that we have all the tools ready, we can simply unleash it on the models. So the first kind of model we have, see, in open systems is basically about whether the Hamiltonian system commutes with the interaction part or not. So if it commutes, then you see it is basically decoherence or dephasing without any dissipation. So such channels are called dephasing channels. So these are pure decoherence channels. And if the fellow, these two guys, the HS and HSR, don't commute, then there'll be decoherence along with dissipation, and that's a kind of a non-unital channel. I'll show you an example shortly. So this is a typical non-Markovian dephasing channel. So we start with a generic qubit state. It evolves like so, and it is easy enough to get the tau QSL analytically here. So here I have the relative purity perspective here. Similarly, for a dissipative model, there is this kind of a Jaynes-Cumming model for a two-level system that's notably coupled to a leaky single mode cavity. This model is very interesting and actually is worth the talk on itself historically also, because this is one of the very few dissipative models which can be solved completely, totally analytically. And this is sometimes called the Garaway model also, but if you really retrace its history, this was actually, this is one of the subset models which was introduced by Fredericks in the 1950s. So I would rather say this was basically the Fredericks Garaway model basically. But if you look at this structure from here, this has the same Lindbladian structure as I showed you for the case of spontaneous emission. Okay. Now, for simplicity, this is written as if, but this carries time dependency. So starting from the same initial qubit state, one can get the time evolved state here. You can see even here, the off diagonals are changing with time, but diagonals are also changing. If you just throw back your mind here, in this dephasing case, you will see the off diagonal, this PT here, this is causing change in this. This is actually the coherence. So this loss of this is decoherence, but there is no change in this diagonals, right? So there is no dissipation. Here, there is change in coherence and there is also change in dissipation. So there is decoherence and dissipation here. So tau QSL can be computed analytically in these scenarios, and we can basically here, we've been plotted this for 3 channels with respect to deviation from semigroup, quantum dynamical semigroup. This is the RTN, this is the random telegraph noise. It's a very beautiful noisy channel. Unfortunately, don't have time to speak about it. It's very beautiful. So this is the RTN, this is the OUN, and this is the non-Markovian amplitude damping. So as you can see, the basic first cut impression that is coming out is that as memory is increasing, the tau QSL is decreasing. So in effect, memory is speeding up the evolution, basically, which is kind of consistent with what we understand from the other aspects of literature. Now, speed limit has many roles to play in information theory. I'm sure the other speakers will talk about it. It sets the maximum rate at which information can be communicated, the maximal rate at which it can be processed, shortest time scale for control algorithms to converge, and precision in metrology. It also has an intriguing connection to quantum correlations, which I'll be brief about because I think I'm running short of time. Now, when we talk about correlations, the simplest thing we can talk about is a 2-qubit state, and the most interesting aspect is this correlation matrix here. So some aspects, because this audience knows these things very well, I will just skip. There's this teleportation fidelity, then this Bell CHSH inequality. This is all written in terms of the eigenvalues of the correlation matrix. This is a particularly beautiful result coming from the Horror case. And then we have this quantum steering, which again are connected with these eigenvalues of T. There's the 2 steering and the 3 steering. And of course, Wouter's entanglement concurrence. Now, again, when we go back to a model, we take the simplest non-trivial model, the non-Markovian amplitude damping. We pass our system through this. It starts from the Bell state and passes through this. And there's a huge complex variety that is coming on. Let me just explain it to you. There are many correlations that are plotted here. So for example, this black curve is the Bell inequality. This is B. This is the teleportation fidelity, this orange thing. then there are this is concurrence, then this is the 2 steering, this is the 3 steering. Now about fidelity, we find that there is something which I would rather say Gisin fidelity, which is basically like approximately 0.87, which tells us the maximum level to which you can define basically a local variable theory within quantum teleportation. So that is this line here is basically 0.87, and what we see is a pattern. These are, so this NMAD is a channel which is actually, if I may use a modern terminology, it's called P-indivisible channel. So these typically show a lot of recurrences. That is why they are very popular in the literature. So you see, these decay and then they start recurring. This recurrence is, this recovering is happening because of this information backflow. And the decay takes place in a certain pattern. The strongest form of this correlation decays first, and then the next stronger form till the weakest form comes in. And the recovery happens in a reverse fashion. Similarly, the same thing if we pass it through an amplitude damping channel, which I told you is basically a quantum dynamical semigroup, the pattern of decay. Yes? Hello?
Indranil, you are mute.
In the case of this, bolo. Okay, let me finish it, then we'll have some discussion. This is, in the Markovian case, of course, we don't expect any, I should use the word semigroup QTS limit. There is no recurrence here, but the decay happens in the same pattern. So this is the pattern in which this thing takes place. So first to decay is this fidelity of this less than 0.87, this Gisin fidelity. Then this bell, then 2 steering, then 3 steering, then this is the classical teleportation fidelity, 2 by 3, and then there is this entanglement. Now, if we use this thing because our thing focus is on speed limit here, so tau QSL, if we plot it with respect to gamma t, which is basically the decay channel, the decay parameter, and this is the dimensionless time here. For non-Markovian amplitude damping, we can see that it goes up and then comes down, and this point where this inflection takes place is exactly the point where entanglement starts recovering. Where is this concurrence? Yeah, this fellow starts recovering. So this is interesting that it kind of gives a signature that there is a connection between quantum correlations. There may be a connection between quantum correlations and speed limit. If we plot the same for a similar QTS limit, we don't see any inflection time. It is expected because there is no recurrence here. And the last thing which I have to say is basically an interesting connection of these things with coherence and mixing. So a few years from now, a few years before, this Singh and Arun, these people, they construct a very nice, Arun Pati, they construct a very nice connection between quantum coherence and mixing. There's a kind of a bound. So there, if we make use of this here in the speed limit time, we see that, for example, if we concentrate on this plot, this is for non-Markovian amplitude damping, and this is for the initial mixed state, and this is for initial pure state. All these jigglings are happening because of two things. There is actually an information backflow taking place, and there is also a kind of a balance being created between this coherence and mixing as the evolution takes place. This thing is given more justice by this kind of figure. This is the parametric trajectory of this quantum speed limit time as a function of this bound. This whole bound is called MCL. So we start with a maximal coherent state, and then we evolve it, and it goes like this. So these arrows gives us the evolution trajectory. So you can see there are points here where the tau QSL has multiple values for the same MC. This clearly brings out that this basically kind of a parking thing between coherence and mixing, which takes place as the speed limit influences and progresses. And this is very useful for a number of purposes. One of which I will highlight here is that it can be used operationally to distinguish between, say, for example, phi plus minus and psi plus minus states. So if you evolve this from, say, here we are evolving a Bell state, and we are evolving it using this non-Markovian amplitude damping. And it can be seen here that this curve, this blue curve, which is for psi, is different for the black curve for phi. Okay. And this red curve here is for a maximally coherent entangled state. And this kind of classification can be extended to even higher dimensional multi-qubit states like the GHZ states, which I will not be presenting here at the moment. So I finally come to my conclusion, which is basically I have tried to discuss quantum speed limit from the perspective of open quantum systems. Within open quantum systems, I've tried to concentrate on non-Markovian processes and try to see what is the impact of these processes on the quantum speed limit evolution. So this is a very interesting subject, and it is evolving, and I certainly hope there will be many more interesting results to come in the future. Thank you very much.
Hello, Indonil.
Thank you, Shubhashita, for such a wonderful talk. Thank you, Professor Banerjee. I think we can probably have one question before we move on to the contributory talk. If there's a question, please do raise your hand.
Is there any question?
Hello. Yeah, please. There is a question. Now, if there is no question, then let us thank Professor Banerjee, for this wonderful talk. Thank you, Shubhashita. Now, next, hello, am I audible?
Yes, you are, but the voice is breaking.
Hello? Okay, so our next talk is a contributory talk, and we are having Ms. Neha Pathania from Jamia Millia Islamia University Center of Theoretical Physics. She will. My voice is breaking. Hello. So she will be
Yes, sir,
talking
your voice
about
is breaking.
quantifying entanglement with coherence. Now, quantifying entanglement with coherence. Now, is it okay?
Yes, it's okay. Yes. You should continue.
So she will be talking about quantifying entanglement with coherence. Now, Miss Neha, you can start your presentation. And we have just 17 minutes and 3 minutes, 17 minutes for the talk and 3 minutes for the discussion.
Okay, sir. So are my slides visible?
Your slides are very, very much visible.
Yeah, okay, thank you. Yeah, okay. So hello everyone. I would like to thank Icqif for giving me opportunity to present my work. So my title for talk is Quantifying Entanglement with Coherence. And in this work, I've collaborated with my supervisor, Professor Tabish Qureshi. And this is the outline of my talk. So entanglement. Sir, I'm hearing my voice. Someone please mute me. Okay, so entanglement, as we know, it lies in the heart of quantum mechanics, quantum information processing, and quantum technologies. And Schrödinger, back in 1935, said it correctly as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. We say exists a correlation between these two particles such that if one particle is taken very far from the other and a measurement is performed on one of the particle, the other particle will get affected. So this correlation is entanglement. And this entanglement information is between these particles, the connection between these particles. So suppose we have two systems A and B, and the state of system A is written by psi, and for B it is written by phi. So the joint state of that system, if it can be written as the tensor product of psi and phi, then it is called a separable or product state. And if it cannot be written as the tensor product of these two states, psi and phi, for any psi and phi, then this is called an entangled state. Next, there are examples of entangled states. So we have Bell states, which are maximally entangled state, GHZ states, and for bosonic modes, we have mean states. Okay, so applications of quantum entanglement, we see entanglement is used widely as a resource for tasks in quantum information processing, quantum computing, teleportation, superdense coding, cryptography, etc. So possibly in every field in CO. Okay, so quantification of entanglement. So obviously to use entanglement as a resource, we need to quantify entanglement. And quantification of entanglement, we call it essentially the theory of entanglement measure, which acts as an ingredient in the quantification. So entanglement measure is any function of bipartite density matrices which satisfy certain desirable properties. And these are the postulates for a good entanglement measure given by Planu and Birmani. So the entanglement measure, it should not increase under Lqcc. And for pure states, this entanglement measure, it should be equal to the von Neumann entropy of the reduced density matrices. This entanglement should measure, it should be a convex function. And so this is for the mixed state, the convex function. And for any separable state, this density for any separable state, this entanglement measure should be equal to 0. For a maximally entangled state, this should be equal to log 2d, and it should not vary under local unitary transformations. So now we are going to discuss. So there are many entanglement measures which we know, but right now I'm discussing two entanglement measures which we have used to compare with our entanglement measure. So first one is entropy of entanglement. So entropy of entanglement is an entanglement measure for pure bipartite states. So it is defined as the von Neumann entropy of reduced states of one of the subsystem Because we say that von Neumann entropy is used in extracting information from a quantum system. So similar way, it's like extracting entanglement from a quantum system. So for a pure state, psi, it is given as E rho is equals to S rho A, and also equivalent to S rho B. So these rho A and rho B, these are the reduced density matrices for subsystem A and B, which we can calculate by taking partial trace. Next, we define I concurrence. So it was given by Woodward and Hill, and is basically for a measure for entanglement for pair of qubits. The concept of concurrence is given by Woodward. So they have defined for a joint state rho of 2 qubits is given in terms of the eigenvalues of this matrix. So the eigenvalues of this matrix, lambda 1, lambda 2, lambda 3, lambda 4. So these are in such way that lambda 1 is greater than lambda 2, and similarly, lambda 2 is greater than lambda 3 is greater than lambda 4. So this concurrence is basically positive. And this rho tilde, we calculate by taking spin flipping of this rho by using Pauli matrices. Now, this has been generalized by Rangta et al. For joint pure state psi of system AB, and we can write it is defined as C psi is equals to a root under 1 minus trace rho squared A. So obviously, this is basically again written in terms of reduced density matrices of the subsystems A and B. Okay, next we define Schema decomposition, in which our entanglement measure is based, which we'll discuss in the next section. So for any pure bipartite state psi AB, we can write it in the Schmidt form, in the Schmidt decomposition form as this. So this we have written in the Schmidt basis. Now these lambda i's, these are the Schmidt coefficients, and ui and vi, these we call the Schmidt vectors. The Schmidt coefficients are positive real values. And important feature of this Schmidt decomposition is that it provides a very simple recipe for computing the reduced density matrices. So you see that when you calculate the reduced density matrices of this, by calculating the trace of the density operator, you see that they comes out to be like diagonal matrices, and the eigenvalues for those rho A and rho B is the square of the Schmidt coefficients, and they are equal. So yes. Another important feature of the Schmidt decomposition is that it also states. So suppose if you're, so first I'll define what Schmidt number is. So suppose that, so these Schmidt coefficients, so if there are, we calculate the number of non-zero Schmidt coefficients. So that is called Schmidt number. So if we have like only one non-zero Schmidt coefficient, then the Schmidt number is 1, and that means that the state is separable. And if there are like more than one non-zero Schmidt coefficients, then the Schmidt number is greater than 1, and we call that state to be entangled. Okay, next, so this is mainly our work where we have introduced coherence as an entanglement measure. So let us talk a bit about coherence first. So it's a fundamental feature of quantum physics, which signifies the possible superposition between the quantum states, and a maximally coherent state is written in this form. And quantum coherence, as defined in the Baumgart's papers, it is defined as the sum of absolute values of the off-diagonal elements of the density matrix, which we can see here. So from here, we can also see that this coherence is basis dependent. Okay, so this is our main work. So what we did, we considered a bipartite entangled state, and we write it in its Schmidt form. So this Pi, these are the coefficients, Schmidt coefficients, and these Ai and Bi are the basis of two subsystems A and B. N is the dimensionality of the Hilbert space, but here, if the Hilbert space of both the systems are unequal, we consider it to be the the dimensionality of the minimum Hilbert space. So in for our case, we have considered it to be A. So yes, so next we calculated the full density operator for this above state, and the full density operator is just the outer product of the state with itself, and it comes out to be this.
Hello. Hello. You are muted, Miss Neha. Hello.
Yeah, hello, sir.
Yeah, your screen is visible.
So I'll just share my screen again. Hello.
You can proceed. You can proceed.
From here.
Yeah, you can proceed. It's got disconnected.
From here or from back, from how much time?
No, from here you can. I think it was last there in the expression.
Okay. Okay, let me have this in full screen. Yeah. So so this is the expression for entanglement coherence. And this measure we have now written in terms of the reduced density operator in this form. So reduced density operator simply by calculating the trace of this. And we can also see that this is a measure of purity of the reduced state rho. Okay, so one would also want to know that how maximally, what is the value of entanglement coherence for a maximally entangled state. So in the case of maximally entangled state, all the Schmidt coefficients are equal. Therefore, we can say that this Schmidt coefficient, so they are equal to 1 by root under n, and we can substitute it in our the joint state psi AB. So this we can see that in place of root under pi, this is 1 by root under n. And we can write a reduced density matrix based on this. So here we can see that these are the eigenvalues will now be 1 by n. Now this CE can now be written as, so we put the value, we calculate it for this maximally entangled state, and it comes out to be 1. So yes, so the entanglement coherence is 1 for maximally entangled state, and this is applicable for any Hilbert space of any dimension. And we can also see that for a separable state, this becomes 0. So this for the entangled state, this measure is bounded between 0 and 1. Okay, so we have also generalized it for the CE in any arbitrary basis for the reduced subsystem, and we can write it in this form. And the square of I concurrence. Okay, so we can also compare it with the square of I concurrence, which is given in the paper of Bhaskar and Panigrahi. So we can see the similarities between these two. This is also this value is also 1 for maximally entangled state in case of 2 qubits. Okay, so next. Hello. So yes, here lies the comparison. We have compared this with other entanglement measures, with the entropy of entanglement and with I concurrence. So we have basically calculated it in the normalized form, and we considered any arbitrary bipartite entangled state of 2 Q traits. And we see the behavior of our entanglement measure with these other two measures. So yeah, so we can see.
You have 1 minute.
Hello? Sir, I cannot hear your voice clearly. Yeah, so this state is maximally entangled for theta equal to pi by 4. And this other state is maximally entangled for x equals to 1. Okay, so here we have also derived a relation between unified entropy and our entanglement coherence. So for a given density operator rho, this is the unified entropy expression for unified entropy. So this R should be greater than 0, but it should not be equal to 1, and S should not be equal to 0, obviously, otherwise this will converge. So unified entropy it belongs to a generalized class of entropy, and this unified entropy held its importance as it can be can be reduced to other entropy measures like Renning entropy and this Thales entropy and Shannon entropy, etc., for different values of S and R. So this entanglement coherence of entangled state is related to the unified entropy of one of the subsystems, as C is equals to 1 upon N, S for R equal to 1 by 2, and small s for 2. And we can see that if this is normalized, then this is exactly equal to our entanglement coherence. Okay, so in summary, we can say that this entanglement coherence is an elegant measure of entanglement in the sense that it's always bounded between 0 and 2, irrespective of the Hilbert space dimension. It is intimately connected to other fundamental features of quantum mechanics, that is quantum coherence. So earlier work has been done in quantifying coherence with entanglement. And here we have quantified entanglement with coherence. So that's a nice one. And this normalized coherence of entangled state, it's also interestingly connected to unified entropy and quantum uncertainty, implications of which needs to be explored further. And yeah, also, so it needs to be proven that this entanglement measure does not increase under Lqcc. So we couldn't prove its monotonicity, that it doesn't increase under Lqcc. So if anyone in the audience can prove it, then it will be really great. So yes, these are the reference papers, so you can read them. This is our paper, which has been published in International Journal of Theoretical Physics. So yes, thank you, and yes.
Hello. Am I audible?
Yes, sir. Hello, sir.
You are not audible.
Yes. Thank you. Thank you.
So your voice is disconnected. Sir.
Am I audible now? Hello.
So your voice is cutting.
Hello. Is there any? Am I audible now? So I request if so I'm writing it down. Request the question on to next talk. I request to raise hand if there is a question, then otherwise we can move on to the next talk. Hello? Now, am I audible?
Yes, sir, you are audible.
Yes, sir, you are audible.
Okay. Okay. So if there is no question, let us thank Ms. Neha for this talk, and then we can move on to our next talk, which is from Mr. Priyabrata Dhar from the University of Calcutta. And he will be talking about catalytic transformations in coherence theory. Now, I request Mr. Priyabrata to present his talk.
Am I audible?
Yeah, you are audible. You are audible.
And my screen is visible to everyone?
Yes, it is at least visible to me.
Okay. So good day, everyone. My name is Priyabrata Char. I want to thank the organizer to give me opportunities to present my work here. Professor Devasis Sarkar is my supervisor, and title of my talk is Catalytic Transformation in Coherence Theory. So, a basic introduction of quantum research theory. Quantum research theory provides a powerful framework to perform various information processing tasks, which have no counterpart in classical physics. A fundamental need for any research theory is understanding its qualification and quantification. That is the quantum state is resourceful, and if it is, then how much resource it contains. The basic setup of any research theory involves free states, free operations. States which do not contain any resource are called free states, and free operations are such physical transformation which map free states into free states. States which cannot be prepared under free operation from free states are called resource state. Research states have wide application. Some important research theories are research theory of entanglement, research theory of coherence. The basic construction of research theory of entanglement involves separable states as free states and entangled states as resource states. And local operation classical communication, in short LOCC, as free operation. Application of entanglement include quantum teleportation, dense coding, quantum key distribution. Now, incoherent state. Arising from the superposition principle, research theory of coherence is basis dependent. So before going into any discussion, first we have to fix some basis. Any diagonal state with respect to this basis state is called an incoherent state. So they are of the form below. The incoherent states are free states in research theory of coherence. There are actually many free operation, more than one free operation in research theory of coherence. There are incoherent operation, strictly incoherent operation, physically incoherent operation, and maximally incoherent operation. They are generated from different approaches satisfying minimum requirement of being free operations. In multipartite scenario, the free operations are Licc or Lqcc operation. Licc operation is in LOCC protocol. If all parties are restricted to perform only incoherent operation, then the corresponding protocol is known as Licc operation. And if in a LOCC protocol, at least one party is restricted to perform only incoherent operation, then the corresponding protocol is known as Lqcc operation. Now, catalysis. Catalysis is originally brought forward from chemistry into quantum theory. So in chemistry, a catalysis is certain object that can trigger a chemical reaction which is otherwise impossible to obtain. And the catalysis remains unchanged even after the end of that chemical reaction. So in quantum theory, catalysis was first introduced in entanglement research theory. Sometimes an impossible transformation using LOCC psi to phi can be made possible by using an auxiliary system tau, and tau remains unchanged after transformation. The state tau is called catalyst state. There are many types of catalyst. here I describe two types of catalyst. One is uncorrelated catalyst. If there is no correlation between the system and the catalyst system after the end of the protocol, then the transformation, then the catalyst is called uncorrelated catalyst. The transformation is of the form below. And correlated catalyst is that if there is correlation between the system and catalytic system after end of the protocol, then the catalysis is called a correlated catalyst, and the transformation is of the form below. So after end of the protocol, we get a state chi sc, such that when we trace out the catalyst system, we get the target state sigma s, and when we trace out the system, we get our catalyst state. Now moving to the main result. First, I define catalytic IO. Catalytic IO is defined for a single party system S. It is defined as rho s to limit n tends to infinity, trace over c lambda n rho s tensor tau n c, with the condition that trace over s on every lambda n rho s tensor tau n c should give tau n c, and limit n tends to infinity mu n s c minus sigma s tensor tau n c over norm 1 is equals to 0. Here tau n c is a sequence of catalyst state, lambda n is a sequence of IO, mu n s c is rho s tensor tau n c when acted by lambda n, and rho s is our required target state. The catalytic LICC or a catalytic LQICC transformation can be defined similarly. The only difference is the system will be a multipartite system, and the sequence have to be a sequence of LICC or LQICC. Now, a sufficient condition for state transformation via catalytic LICC or LQICC. The sufficient condition is if there exists a asymptotic LICC or LQICC protocol with unit rate that transfers rho s to sigma s, then there exists a catalytic LICC or LQICC protocol that transfers rho s to sigma s. So the outline of the proof goes as follows. So we have to choose a error epsilon, and corresponding to that error, there should exist a natural number and a LICC transformation such that n copy of rho s by this asymptotic LICC transformation goes to capital gamma, such that distance between capital gamma and n copy of sigma s, the target state, is less than epsilon. Now we considering this particular catalyst state, it is actually a big state. And then we apply the following LICC protocol on rho tensor tau. A rank 1 projective measurement on the auxiliary system K is performed by A1 in the basis get K and announce the outcome of the measurement to other parties. If A1 obtain the result N, then all other parties apply the LICC operation lambda on their parts, and for any other outcome of the measurement, they do nothing. And then the state rho tensor tau transfers to the state mu. In the second step, A1 applies an incoherent unitary on the auxiliary system K to transfer N to 1 and I to I plus 1. So then mu1 transfers to the state mu2. And finally, all parties apply a swap unitary on their parts to transfer Sn to S1 and Si to Si plus 1. Then mu2 transfers the final output state mu sc, such that distance between mu sc and the target state tensor tau c is less than 2 epsilon. A sufficient condition for state transformation via catalytic IO. Again, the sufficient condition is same as of catalytic LICC or LQICC. There have to, if there exists a asymptotic IO protocol that transfers rho A1 to sigma A1 via unit rate, then there exists a catalytic IO transfers rho A1 to sigma A1. The proof is actually the same, only the classical communication part in step 1 will not be needed any longer, because there is only one party right now. Now I am recalling the definition of the relative entropy of coherence. It is actually a coherence measure and defined by the formula minimum over sigma belongs to all incoherent state, trace over rho log rho minus rho log sigma. It can be computed by the second formula is del rho minus s rho, where del is the dephasing map and rho s is the von Neumann entropy. Relative entropy have certain properties. It is coherence monotone, additive under tensor product. It is super additive and asymptotically continuous. Now, I shall prove that here that relative entropy of coherence is actually a monotone under catalytic IO transformation. So we consider an arbitrary chosen epsilon, consider an arbitrary chosen positive number epsilon. Now, corresponding to this epsilon, we should find a catalytic state tau a dash and a IO lambda, such that lambda over rho a tensor tau a dash gives chi a dash, where norm of trace a dash over chi a dash minus sigma is less than epsilon, and trace over a chi a dash would give tau a dash. Now, relative entropy of coherence cannot increase under IO due to the property of coherence measure, and using the additive property, also we get the equation 1, and from the superadditive property of relative entropy of coherence, we get the equation 2. Combining these two, it is clear that shear trace over a dash chi a dash is less than equals to shear rho a. And as relative entropy of coherence is continuous and trace over a dash chi a dash minus sigma is less than epsilon, therefore from 3 we can write CR sigma L is equals to shear rho a. Now this is another important result. I am recalling it. For any two pure states psi and phi under rate r greater than equals to 0, the asymptotic state transformation via IO is possible if r is less than s del psi by s del phi, and impossible if r is greater than s del psi by s del phi, where psi and phi are pure states. Next, this is a necessary and sufficient condition for pure state transformation under catalytic IO. A necessary and sufficient condition for a single party pure state psi that can be converted into phi via catalytic IO is s del psi is greater than equals to s del phi. If we assume the existence of catalytic IO, then as relative entropy of coherence is monotone under it, then clearly CR psi is greater than equals to CR phi, and which again implies S del psi is greater than is equals to S del phi. So conversely, if we take S del psi is greater than equals to S del phi holds for any two pure state psi and phi, then the previous result for r equals to 1 implies that a asymptotic state transformation with unit rate from psi to phi holds, and our theorem 1 suggests that there exists a catalytic IO protocol that converts psi to phi. Now, asymptotic coherence distillation, it is a very particular type of coherence state transformation. In asymptotic coherence distillation, using incoherent operation, we have to transfer n copy of mixed state rho to a maximally coherent state phi 2 with a rate r. The optimal rate of this asymptotic coherence distillation process under IO is known as distillable coherence and is defined by the following formula. Distillable coherence is also equals to the relative entropy of coherence. Now, asymptotic coherence distillation can be represented by the following way. N copy of rho goes to nr copy of phi 2 by a IO with a error epsilon. Now, again, we can transform phi 2 tensor nr to a pure state chi tensor n copy of chi via IO with a error epsilon, thus that CR of chi is equals to r. Hence, the total distillation process can be treated as rho tensor n to chi tensor n via an IO with an error epsilon. So this is actually a transformation with unit rate, asymptotic transformation with unit rate. Then there should exist a catalytic transformation with unit rate that converts psi to rho to chi, and hence there exists a catalytic distillation procedure. The optimal rate of the catalytic distillation procedure is again the CD rho. This can be proved by the following way. That CR is monotone under catalytic IO, hence CR chi less equals to CR rho, and then R is less than equals to CD rho, which proves that CD rho is the optimal rate. Now the definition of coherence of formation is given by the equation CF sigma is equals to minimum over summation over I S del psi I psi I. The properties of coherence of formation are: it is coherence monotone, additive under tensor product, superadditive, and asymptotically continuous. And then we can again prove that coherence of formation is also monotone under catalytic IO. The proof is same as relative entropy of coherence, so I skipped it here. And then the asymptotic coherence dilution process, it is actually the inverse process of distillation. It can be presented by the following way, and its optimal rate is known as coherence cost, which is defined by the last equation. The coherence cost is equals to coherence of formation, and by definition of distillable coherence and coherence cost, CD sigma is always less or equals to CC sigma, where equality holds only for pure states. Now we can redescribe the dilution process as n copy of chi1 goes to n copy of sigma via an IO with a error epsilon, such that CR of chi1 is equals to R. Again, it is a unit rate asymptotic state transformation. Then theorem 2 with this equation 5 makes us realize that there exists a catalytic dilution process. Now, if chi1 goes to sigma in a catalytic dilution process with CR chi1 is equals to R, then CC sigma is equals to CF sigma. Since coherence of formation is monotone under catalytic IO, then that less or equals to CF chi1. And for pure state, it is CF chi1 is equals to CC chi1, and for pure state, CC chi1 is equals to distillable coherence CD chi1, which is equals to CR chi1 again, and that is equals to R. So the optimal rate here is also coherence cost. Now we turn to the assisted distillation of coherence. In the task of coherence assisted distillation, proper and active involvement of two parties plays the significant role. Here, Alice and Bob can share many copies of a state rho AB with the objective to obtain coherence as large as possible at Bob's subsystem via a Lqcc operation. In this Lqcc protocol, Bob has the limitation of performing only incoherent operation on his subsystem B. The optimal rate of assisted distillation is designated as distillable coherence of collaboration and defined by the following formula. Now, the quantum incoherent relative entropy is defined by minimization over sigma AB belongs to quantum incoherent state, set of all quantum incoherent state, S rho AB parallel sigma AB, and it can be computed by S delta B rho AB minus S rho B rho AB, where delta B is the dephasing map on B's subsystem only. For a mixed state, CD distillable coherence of collaboration is actually less or less than relative and quantum incoherent relative entropy, and for a pure state they are equal and is equals to S delta psi B, where psi B is the subsystem of B in psi AB. Now again we can prove that quantum incoherent relative entropy is monotone under catalytic Lqcc. The proof is same as relative entropy of coherence, so I skipped it here. Now the catalytic, the asymptotic assisted distillation can be redescribed by the equation 7, where we n copy of psi AB goes to n copy of chi AB via a Lqcc lambda and error epsilon, such that trace over a chi AB is equals to zeta zeta B, where CR zeta B is equals to R. Again, it is a asymptotic Lqcc transformation with unit rate. Hence, there should exist a catalytic Lqcc protocol which transfers psi AB to chi AB. So, corresponding to assisted asymptotic assisted coherence distillation, there exists a catalytic assisted coherence assisted distillation. Now, optimal rate of this catalytic assisted distillation is again distillable coherence of collaboration. This can be proved by the like this, that relative entropy of quantum incoherent relative entropy is monotone under Lqcc, catalytic Lqcc. So CR A partition B psi psi AB is greater than equals to CR A partition B chi chi AB. Now for pure state, quantum incoherent relative entropy is equals to distillable coherence of collaboration. So CD A partition B psi psi AB is greater than or equals to S delta zeta zeta B. And CD A partition B psi psi AB is greater than equals to CR zeta zeta B. It is the definition of CR, and CR zeta zeta B is equals to R. Hence CD A partition B psi psi AB is greater than equals to R. So the optimal rate of catalytic assisted distillation is again distillable coherence of collaboration. Now, the conclusion. We have proved that corresponding to asymptotic I/O or asymptotic Licc or asymptotic Lqcc with unit rate, there always exists a catalytic I/O or catalytic Licc or catalytic Lqcc. Relative entropy, coherence of formation are monotone under catalytic I/O, and quantum incoherent relative entropy is monotone under catalytic Lqcc. S delta psi is greater than equals to S delta phi is a necessary and sufficient condition for single party state transformation from psi to phi under catalytic I/O. Using catalytic I/O or catalytic Lqcc transformation, we can perform coherence distillation, dilution, assisted distillation protocol with only a single unit input state. And the optimal rate of the above described catalytic procedures are same as their asymptotic counterpart. These are some references, and thank you.
Thank you, Priyabrata, for this nice talk. And now it's open to questions. If anybody has questions, we can take 1 or 2 questions. Please raise your hand. Yeah, there is one question. Okay, somebody is asking to keep the reference page on the screen. Okay. Anyway, if there is no question, let us once again thank Priyabrata for giving such a nice talk on catalytic transformations in coherence theory. Now I request our next speaker to Mr. Brij Mohan, who is from Harishchandra Research Institute, India, to give his talk. So he will be presenting on quantum speed limits for information and coherence. Right. So this will be our next second talk on quantum speed limit on this day. So I now request Mr. Brij Mohan to present his talk, quantum speed limits for information and coherence.
Hello, Indranil, can you hear me?
Can you hear me? Yeah, I can hear you. Thank you. Yeah, I can hear you.
Okay, I'll share my slide.
Okay, I'll share my slide.
Yeah, your slides are also visible. I think you are mute. You are mute. You need to unmute yourself.
Hello.
Hello.
Now you are audible. I can hear you.
Okay. Thanks, Indranil, for a kind introduction. So first of all, I would like to thank the organizers for giving me this opportunity to present my work. So the title of my talk is Quantum Speed Limits for Information and Coherence. This work I have done with Siddharth Das and Professor Arun Kumar Pati, who is my supervisor as well. So this is the brief outline for my talk. So in which first I'll discuss what is quantum speed limit, then I'll discuss what is quantum speed limit for information and then coherence, and then at the end I'll conclude my talk. So let's begin by asking this question: how fast quantum system can evolve in time? The answer of this question is given by the quantum speed limit. In short, we call it quantum QSL. So in quantum information theory, the quantum speed limit aims to address the question: what is the maximal rate of change of state of the quantum system in physical process? It provides the minimum time needed for a quantum system to evolve from initial state to the final state. Therefore, it sets the fundamental lower bound on the evolution time of the quantum system. So quantum speed limit for unitary dynamics. So the first quantum speed limit bound was given by Mandelstam and Tom in 1945, which is where the evolution time is lower bounded by TQSL, to where TQSL is h bar s naught by delta h. S naught is the cos inverse of inner product of initial and final state, and delta h is the variance of the driving Hamiltonian. And then later on, another bound was given by Margulis and Lewton in 1998, which is based on the mean energy instead of this variance of the Hamiltonian. So then there was a question which for estimating speed limit, which bound one should consider. Then this question is answered by Lewton and Topley in 2009. They said that the maximum one should take the maximum of these two bounds. They say the argument they have gave, they told that the bound which is easily attainable is tight, and along with that they have given some another regions as well. For that one need to look at this paper. So this is for the quantum speed limit bounds when you have a pure initial pure state and dynamics is unitary, and then you can extend this bounds for when your state is mixed, and for open system as well. For open system dynamics, I think the Professor Subhasis Banerjee already talked about in detail. So this quantum, as you can see, that these are the relations between energy and time. So this speed limit bounds provides an operational meaning to the energy time uncertainty relation. So they have many applications in the quantum information theory, such as in quantum metrology, in the charging of the battery, where you estimate how fast you can charge the quantum battery, in quantum thermodynamics, and in quantum control theory. So this up to now, this is speed. I have talked about the speed limit of the how fast state of the quantum system changes. Then one can ask about what about other quantities. For example, how fast the entropy of the system changes, or how fast the coherence of the system changes, or information, or one can say how fast the quantum resources will change in time. So I'll be answering some of this question, and then another question, is there any speed limit for them? So answer is yes. So first I'll talk about the little bit about the quantum dynamics. Let H denote the separable Hilbert space where the dimension of H may be finite or infinite. The state of the system is represented by rho, which is Hermitian and positive semi-definite, has a trace 1, and the physical transformation of the state of the system is given by completely positive trace preserving map, which is also called a quantum channel. The time evolution of the quantum system is evolving under a given dynamical process is given by the master equation, where rho dot is L acting on rho t, where rho t is the quantum state of the quantum system, and LT is a Liouvillean superoperator, which can be in general time dependent and independent. The Von-Neumann and now a little bit discuss about the Von-Neumann entropy. So the Von-Neumann entropy of the quantum system in the state rho is defined as minus trace of rho ln rho, where S of rho is interpreted as average information content of the quantum system in state rho. So if we'll take consider a quantum system which evolves in the time, then one can differentiate this S of rho 2 with respect to time, and then find the rate how fast then find the rate how this entropy of the system is changes with the time. So here is the first result of my talk. So for arbitrary quantum dynamics is describable as a time evolution, the minimum time needed for a quantum state rho t to attain entropy S of rho t, where rho t is the final state of the quantum system, is starting with the initial entropy S of rho naught, where rho naught is initial state, is lower bounded by where evolution time is lower bounded by TESL, which is nothing but the change in entropy divided by evolution speed of the quantum system, then along with this another factor ln of rho t, Hilbert speed of ln rho t, where lambda t RMS is defined as 1 over square root of 1 over t integral of Hilbert space norm of ln t of rho t square, and ln rho t of Hilbert space norm of this time the root mean square of this quantity defined as this, and this speed limit bounds holds for both finite dimensional and infinite dimensional system. So the now I'll talk about little bit about information. The maximum information of a finite dimensional quantum system with Hilbert space dimension d in state rho is defined as ln d minus s of rho, where we call I of rho as the maximum information, as it can be interpreted maximum amount of information that can be gained by performing optimal measurements on the quantum system. This is also called as measure of objective information. So similarly, one can obtain the bound for this quantity as well, speed limit bound for this quantity as well. So for arbitrary quantum dynamics, the finite dimensional quantum system describable as time evolution is its state. The minimum time needed for rho t to attain information I of rho t, where I of rho t is the final state starting with the initial state of I rho naught, where evolution time is lower bounded by TISL, where TISL is the change of information divided by root mean square evolution speed of the quantum system, along with this factor of ln rho t operator norm of rho t. So suppose we consider a quantum state rho t as initial time t is equal to 0. This has a maximum information according to this I of rho naught ln d minus s of rho naught, where rho naught acts on the Hilbert space of dimension d under any action of the erasure operation, which is a CPTP map. Any quantum state can be mapped to the ground state, which is a fixed pure state and has a least energy. Since the final state of is the quantum system is pure, then we can say that it has effective dimension 1. Then the final information of the final state is 0. Therefore, it can be used to state that the minimum time required to erase the information is given by t erasure I, which is equal to I of rho naught divided by lambda RMS along with this factor ln of rho t. So thus we can say that the Landauer erasure principle says that how much minimum energy required to erase the information or information of a bit or qubit. So our result says that what is the minimum time required to erase the single information of single bit or qubit. So the amount of superposition present in a quantum state is quantified by the quantum coherence. So quantum coherence is a crucial resource for several information processing tasks, including quantum computation in quantum thermodynamics and others, some of other areas as well. This is very important resource for in quantum information theory. So one can ask a natural question: how fast the quantum coherence of the given quantum system can be generated or destroyed in a physical process. So next we have obtained the quantum speed limit bound for the quantum coherence. As we know that there are several measures for quantum coherence, such as relative entropy of coherence, L1 norm of the quantum coherence, geometric measure of quantum coherence, and robustness of coherence, etc. So here we are using the relative entropy of the quantum coherence, which is defined as S of rho t and minus S of rho, where rho t is the dephased state in a reference basis, and S of rho represents the Newman entropy of the quantum state. So for arbitrary quantum dynamics, the finite dimensional quantum system describable as time evolution, its time, the minimum time needed for the state rho t to attain coherence of rho t, where rho t is the final state starting with the initial state, initial coherence, sorry, C of rho naught, where rho naught is the initial state. So then this evolution time is lower bounded by TCSL, where this is the change in coherence divided by speed divided by the speed of this diagonal part of the quantum system, and then there is a factor of ln rho td, and then evolution speed of the quantum system, and then there is factor of ln rho t. So where if we consider the dynamics is pure diffusion, the quantum speed limit for uncoherence applies for coherence generation and coherent degradation process. In particular, our bound answer how fast a system undergoes a decoherence for and completely dephasing process. This bound interpreted as the speed limit of decoherence, which means minimum time required for a coherent state to become incoherent. And if this happens, then this lambda TR, the speed of diagonal part of the density matrix becomes 0. So that's it. Then I'll conclude my talk. So we have derived the fundamental limits on how far the entropy of information and quantum coherence can change for arbitrary physical process describable by completely positive map. We obtain the lower bound and minimal evolution time for the change of in entropy, maximal information, and quantum coherence. The quantum speed limit for information also sets a generic bound on the rate of information production. We showcase an application of our main result answering the question, what is the minimum time required to erase the information by an eraser process in a general setting. The quantum speed limit on coherence for dephasing process answers the question how fast the system undergoes in decoherence. Thank you.
Thank you, Mr. Breach Mohan, for this wonderful talk on. Is there any question? Is there any question on the talk quantum speed limits for information and coherence? Please raise your hand, and we can take questions, and then we can move on to the next talk. Well, if there is no questions, so let us once again thank Mr. Breach Mohan for this talk. Thank you. And our next speaker, thank you, Breach.
Okay, I'll stop there.
Our next speaker is Ms. Rajni Bala from IIT Delhi, and she will be talking about layered semi-quantum key distributions and secret sharing. So this is going to be the last talk of the session. After the lunch break, we will again meet at 2 o'clock. So now I request Ms. Rajni Bala from IIT Delhi to present her talk on quantum layered semi-quantum key distribution and secret sharing. Over to you.
Thank you so much, sir. Okay. Just a second. Yeah. So is my screen visible?
Yeah, your screen is visible. Am I audible?
Yeah.
Your screen is visible.
Yeah. Okay. Thank you. Okay. So first of all, I would. I'm hearing an echo, sir. Yeah. First of all, I would like to thank the team of ICQIF to give me this opportunity to present my work in front of such a respectable audience. Yeah, so today I'm going to present my work, layered semi-quantum key distribution and secret sharing, which is done in collaboration with Suryansh Asthana and Professor V. Ravi Shankar. This is the brief outline of my today's talk. So let's get started with the motivation. Transfer of information securely is a task of a primordial importance, and one of the application, which has even reached to the commercial level, is the quantum key distribution. So with the help of quantum key distribution, one can share information securely between two or say the n parties. But if we look at the more practical scenarios and the situations, for example, it can be a bank or it can be a big company in which information is to be distributed, but different information should be distributed in a different layers. So that is, information is distributed in a network. So what is the corresponding ways for that? So there are actually two particular ways. One can be like, suppose there are n layers in a network in which keys are to be distributed, then n QKD protocol can be running in a parallel, but that does not seem to be a cost effective resource. So the other approach which one can take into account is employing the multi-dimensional entangled state. So the corresponding work have already been there in the name of layered quantum key distribution in 2018. But in this work, it is assumed that each participant have access to the quantum resources. But in a more general and the practical situations, that might not be the case. There might be the participants who are having only the restricted access to the resources, but one even then wants to share information among such participants. So the answer to the problem lies in the integration of the layered quantum key distribution protocols and the semi-quantum key distribution protocols. So that's what I'm going to present today. And whenever we want to distribute key in such a network, we are calling it a layered semi-quantum key distribution. This work is already there on archive. Interested people would like to look on. So before heading to these protocols, we just first have some general settings or the terminology which we are going to use. So whenever we have an Alice, so Alice is always supposed to be a quantum participant. So whenever we say quantum participant, she can prepare any state, she can perform measurement in any basis. And whenever we have a Bob, so that corresponds to a classical participant. And being a classical participant, Bobs can only perform measurement in the computational basis, and so can prepare states only in the computational basis. They have only this much of a resources. And the subscript I here corresponds to the ith classical participant. So Bob I is ith Bob. Now, classical participant can perform two operations. One is called control, another is called a reflect. So control operation is the classical participant will perform a measurement in the computational basis. They will note down the corresponding results and then send the post-measurement state back to Alice. The other operation, reflect, is the one in which classical participant will simply send the received state back to the Alice. Given these two operations, let's get started with the layered semi-quantum key distribution. First of all, I'll consider an illustrative example, and then we will move on to the generalization of the protocol. So as an example, we can consider a network of a three participant named as Alice, Bob1 and Bob2. So Alice is a quantum participant and the rest two are classical participant. And in this network, we have two layers. The first layer is the one in which key should be distributed only between Alice and Bob1. And in the second layer, key should be distributed among all the participants. And if that is so, so we employ this particular kind of a state that will implement this task. So this is a multi-dimensional state, multi-dimensional in the sense that the dimensionality of the subsystem, which will be possessed by each participant, is not the same, it is different. So with this knowledge, this is the basic procedure which will take place. So the first rectangle, the smaller one, corresponds to the first layer in which key will be shared between Alice and Bob1, and the bigger rectangle corresponds to the second layer. And this is the state which is used. Since Alice is a quantum participant, she can prepare this state. After preparing the state, she will keep first subsystem to herself. She will send second and third subsystem respectively to Bob1 and Bob2. Now, since Bobs are classical participants, so they have two choices. They will either perform control operation or they will perform a reflect operations. After that, what Alice will do, Alice will receive the subsystems from both the Bobs, right? So she has two choices. She may perform measurement on all the three subsystems in the computational basis, or she may perform a projective measurement over the given particular state. Now, with this projective measurement is used to check for the presence of an eavesdropper. So for the rounds in which none of the Bob have performed control operations and Alice has performed a projective measurement, so that data of those rounds will be used to check for the eavesdropper. And for the rounds in which the participant in a given layer have performed a control operation and Alice has performed a measurement in the computational basis, that round will constitute a key in that corresponding layer. So two different scenarios can be there for this case. So one can be in which only Bob1 have performed a control operation, but Alice has measured in computational basis. So that outcome of that round will constitute a key bit in the first layer. However, if both the Bobs have performed a measurement and Alice has also performed the measurement in the computational basis, that will correspond to the two keys, one in the first layer and one in the second layer. So how that will be done? So for that, let's go to the key generation rule. Now, by the state, we know like Alice and Bob1 have access to a 4-level system, while Bob2 have access only to a 2-level system. So what will these participant will do? Each participant will write their outcome in the binary representation. That is, Alice will write her outcome as this form, and Bob1 will write his outcome as this form, and Bob2's outcome is already in the binary form. So the symbol this A1 and B1 that will constitute a key in the first layer, and the symbol A0, B10, B2 that will constitute a key in the second layer. So in this way, keys can be shared in different layers simultaneously, employing only a single resource states. Now moving over to the next case, which is a layered semi-quantum secret sharing. So whenever one discuss about the key distribution, it is implicitly assumed that all the participants which are taking part are honest. What do we mean by like their individual behavior is honest? But that might not be the case in a more practical scenario. So there can be situations in which individual behavior is not honest, but if the participants are supposed to are constrained to behave in a collective manner, then they have to behave honestly. In such situations, keys are shared, and the corresponding thing is called the layered semi-quantum secret sharing. Again, we take an illustrative example, and we have a network of 5 participants, Bob1 to Bob5. Okay, so here all the participants are supposed to be classical. Sorry, I'm getting an echo.
I think there is some mic open. Please mute your mic if one of the participants is having mic open. That is why the echo is coming. Is it all right now?
Yes, sir. It is fine now.
Yes.
Thank you. Okay. Thank you. Yeah. So now we have all the participants to be classical because no individual participant is supposed to be honest. So it is the external participant Alice that will want to distribute a secret among these 5 participants. And in this network, we have 3 layers. So first layer consists of only Bob1 and Bob2. Second layer have all the rest of the 3 participants, and the third layer have all the participants. And the request state which will implement the task is a product state, and here this product state is a 4-level, like each participant will have access to a 4-level system. So this is how the protocol will be implemented. So Alice will prepare state psi, and she will send each subsystem to the respective participants. And again, because participants are classical, they have 2 choices, control or a reflect, and they will act accordingly. After that, upon receiving the subsystems from each Bob, Alice will either perform measurement in the computational basis, or she may like to perform a projective measurement in the originally prepared state, which will the data of the rounds in which none of the Bob have performed control operations will use to check for the presence of an eavesdropper. and the rounds in which all the bobs of a given layer have performed a control operation, that will constitute a secret in the respective layer. And to retrieve that secret, each bob of a layer have to act collaboratively. So how the secret will be generated? Just like in LSQKD protocol, in this protocol it's also each participant will write their binary their outcomes in terms of binary representation. So the ith bob, if bi is the corresponding outcome, they will write it like this. Now since each participant has access to only a 4-level system, so the only 2 bits of information will be there in their outcomes. And if that is so, now because we have a 3 layers, so a secret in the first layer which consists of only bob 1 and bob 2 will be generated like this. Similarly, secret in the second layer will be the modular sum operation of outcome of the respective participant, and so and same way in the third. The only difference is in the first 2 layer this bit at 2's place is being used, and in the third layer the bits at units place are being used. Now we have seen like how these keys or the secrets are being generated and shared in the 2 protocols, but does it implies the confidentiality of the secret being shared in the different layers? So yes, there is a confidentiality. How it comes from the 2 points. So first point is because especially in this LSQSS protocol, depending upon the outcome of one of the bob, other participant cannot infer what is the outcome of another bob. So that is one confidentiality at one of the level. And in the second case, the secret is being generated only by employing the binary digits at a particular outcome. Since none of the bob have access to the outcomes of the rest of the bob, so they don't know anything about the bits being employed. So in this way, the secret being shared in different layers remain confidential. Okay, now having access to these these 2 protocols and having particular illustrations for the same, now we move on to how we can generalize these protocols to share secrets or information in an arbitrary structure. So the basic steps of the protocol will remain same. The only difference will come at the level of the request state which is being employed to implement the task. And to obtain that particular state, we take recourse to this particular procedure. So if kappa is represents the network in which information is to be distributed, then this network is being characterized by 3 different numbers, n, k, and lj. N represent the total number of participants in a network. K represent the total number of layers in the particular network, and this lj corresponds to the number of layers to which each participant belongs. So as an example, if we take the first case of LSQKD, then we have a 3 participant, and from 3 participants, Alice and Bob 1 were belonging to the 2 layers, and Bob 2 was belonging only to the first layer. So the number of layers that is represented by the LJ to which each participant belonged. Now, given this information, let's move to the next part. So because in a network we have in total k number of layers, so the task, if we divide this task of getting a state into different parts, so we should have a request state which will distribute a key or a secret in a given layer. So for that, for a resource, we have for LSQKD, we have a state kind of a GHZ. So here J represent the number of a participant which are belonging to say the ith layer. And similarly for LSQSS, we will have a product state, and again J is the belongs to the participant which are belonging to the ith layer. But now in this network, we have actually the k layers. So the total, so the state which will implement the task in this particular network should be the tensor product of all the references state. But this is like no less than some k QKD or QSS protocol running in parallel. But this is not the end of a story. We then what we then next do, we club all the qubits which are belonging to the same participant together. So what is happening? So as we have said, like for each participant uj, it may belong to some lj layer. Okay, so it implies each participant UG has access to LJ qubits. So what we'll do, we will club all the LJ qubits together, and then we invoke the isomorphism between the Hilbert spaces. Now, invoking this isomorphism of the Hilbert spaces, the basis states of LJ qubits will map to 2 raised to power LJ dimensional single qubit state. So what will happen? Each participant is writing his state of LJ qubits as a single 2 raised to power LJ dimensional qubit state. Now, employing this mapping, the tensor product state, that a multi-qubit state, is mapped to the corresponding multi-dimensional state that distributes information in a given layer. So that's how one will obtain the request state that will distribute information in a network, a single one multi-dimensional state. And that's how we have get the corresponding two state which we have considered in the LSQKD and LSQSS protocols. Now, having obtained the...
Hello.
Yes.
You have just 1 minute time.
Yeah, I'm just concluding here. So next we go to the key generation rule. Again, in the same way, each participant will write their outcomes in binary representation. So this is the corresponding thing. Now in LSQKD, each participant is honest. So this outcome in itself will correspond to the key bit. So BIM is the outcome which is used to distribute in the K minus mth layer. Now considering examples from LSQKD, so BI0 was the one which was sharing a key in the second layer. However, if we have a LSQSS protocol, then we need, like, all the participants should behave collaboratively. So that is why key symbol is generated by taking the modulo sum operation. So modulo is over 2. So again, this T ranges over all the participants in a given layer. So here this thing will correspond to a key symbol in K minus mth layer. So in this way, we have a request state for arbitrary structure and a corresponding key and secret generation rule for the given network. Thank you.
Thank you, Ms. Rajniwala, for this wonderful presentation on layered semi-quantum key distribution and secret sharing. And now it is open for questions. We can take questions. If there is any question, I request you to raise your hand, or you can directly go to the mic and ask the question to the speaker. So if there is no questions, let us once again thank the speaker. For this wonderful talk. So, thank you, Ms. Rajani. And this brings end to the closer to the first sessions of 5th day of the conference. And we will going to meet after the lunch break at 2 p.m. Till then, goodbye. Bye to all of you. Thank you, sir. Thank you.
And all the speakers.
Hello, Archandra.
Hi. How are you?
I'm fine, thank you. Yeah, the Professor Goswami.
Yeah, can you hear?
Yes. Yeah.
Okay, good.
So, yeah, good afternoon all, and it's a great pleasure to introduce our chair, Professor Devamanta Boshali, and Debu, who is, can you hear me?
Yeah.
Right. People are handing over your mic. So Debu, as he's known to us for, I don't know, 2-3 decades, has been a prolific worker in the field of quantum optics. He's an experimentalist. And earlier he was at TIFR, but he's been at IIT Kanpur for many years now. So without further ado, I would request Debu to please chair this session. Over to you, Debu.
Thank you, Archana. It's a great pleasure to be a part of this online conference. I know that had it been physically organized, it would have been much more fun, but I think nevertheless, we get to see some of the best speakers around, including our upcoming speaker today, who is our one of the few quantum information experimentalists in the country right now, who has been doing a fabulous job. It's my pleasure to introduce Urvashi Sinha, who is currently professor at the Raman Research Institute, Bangalore, and is heading the quantum information and computing labs there. She's also associated faculty members of the Institute of Quantum Computing, Icqif, University of Waterloo, Canada, and the Center for Quantum Information and Quantum Control, University of Toronto, Canada. She got her PhD from Cambridge University, and she was also a Nehru Scavenger Scholar during those days. She's did her postdoc at Cavendish Labs, Cambridge, as well as at IECC. Her lab at RRI specializes in experiments on photonic quantum information processing, including quantum computing and quantum communication, primarily using single and entangled photons. She is heading India's first project on satellite-based secure quantum communications. I know about this in particular because I'm also a part of the ISRO's quantum computing efforts. So I'm very happy that she has agreed to give this talk today, and I'll give her the opportunity to present us on revealing new facets in experimental quantum information processing with photons. Over to you, Urvashi.
Thank you very much, Professor Goswami, for this very kind introduction. Can you hear me and see me?
Yeah.
Yeah. Right. So let me just go full screen. Okay. So everything is working. Yeah. So thank you very much. And of course, there is no question about agreeing to give this talk. It was so nice the last time we had this, which was a physical conference. I remember in Kolkata. It was a very nice conference at that time, and it is also very nice now. And it's just nice that we are able to talk to each other irrespective of, various circumstances. So even if it's online, it is a wonderful effort. So thank you very much to the organizers for thinking of me again. So the title of my talk, as was mentioned, is Revealing New Facets in Experimental Quantum Information Processing with Photons. And as was mentioned by Professor Goswami, so we do work on different areas of photonic quantum science and technologies. And, one of our focus areas is quantum communications, and we have several projects in that. We are also working on other aspects of quantum computing and information. But today I decided, to pick a few, recent results that we have from the lab over the last couple of years and tell you a bit about that. And so I go on to the next slide. Okay, yeah. So this is an overview of how things look in the lab when photos are being taken. Very nice, very neat. Okay, so the plan for the talk. So as I mentioned, I will be focusing on a particular theme, which we have, of course, been exploring for a long time now. But then on the results over the last couple of years is what I will be telling you. So the first thing, the main focus is on higher dimensional quantum information processing, given that, the conference is on quantum information and foundations. So I thought, I'll focus on this information processing part and in higher dimensions. And so the first thing I'll tell you about is a method that we have found of direct determination of different entanglement monotones used to quantify entanglement in arbitrary system dimensions using only one pair of complementary observables. I will tell you about the experiment we have done, which is the proof of concept for this using bipartite Q-trits, and we have very nice results which show that this scheme works very well. Then I'll go on to another aspect of higher dimensional QIP, where I'll talk about quantum state estimation and a new tool that we have established, which is called quantum state interferography. And just because, you know, our conference, the last F is on foundations. And so I'll just very briefly, over a couple of slides, tell you about a very recent result on a loophole-free violation of the Leggett-Garg and the Wigner form of the Leggett-Garg inequalities that we have done. But then, you know, it will be very brief because otherwise that would be the whole, it could be the whole talk. So that's the plan. So now why higher dimensions? Now, of course, you know, the audience is, of course, very well aware of the, you know, the requirement, but just as a reminder, this is a good example that I like to use as a reminder. So, you know, if we want to give some information which contains, let's say, 4 possibilities, we would obviously need 2 qubits to do that. And this is what I represent here. But then if I had a higher dimensional system, let's say a 4-state system, then that would be called a Q quad. And I could represent the same information using only 1 system. So essentially, the idea that is represented here is that as we go to higher dimensions, then we can essentially access the state, you know, the same complexity of the state space as we would do with qubits, but with smaller number. So we can decrease the size of the system. And this is, of course, very interesting. I mean, if you think about quantum computing, we have all been after this 2 to the 50, you know, as a number, 50 qubit processor and so on. And there's a lot of news on that from various establishments around the world. So this 2 to the 50 has been interesting to us as you know, what we would like to access. But if we change the 2 to 3, then the 50 would drop to something like 33. And then if we change it to 4, it would drop. So essentially, changing the denominator would drop the exponent. And that is, of course, a very nice motivation to explore what is possible in higher dimensions. Even in the domain of quantum cryptography and in key distribution, there are you know, results, especially in the theory domain, which tell you that you can have higher security and, you know, lower QBER if you go for higher dimensions. So there are lots of reasons why this would be interesting. And of course, there are, you know, different ways in which one could explore higher dimensions. I stick to photons. So in photons, of course, orbital angular momentum is, you know, a degree of freedom which is commonly used to explore higher dimension. So what we have done in our lab is actually come up with an alternative way of doing this, which is using the spatial degree of freedom of the photon. And this is what we call, you know, this, we are generating higher dimensional systems from down conversion directly. And I'll tell you more about that. Having said that, what is a Q-trit? Because Q-trit is important because our experiment is in the bipartite Q-trit domain. So qubit has 2 states, Q-trit has 3 basis states, and so you would form a linear, you know, combination this way to define the superposition. So one way in which you could, you know, access a higher dimension would be having a single photon incident on a multi-aperture system, you know, a plate, let's say. And then, of course, you do not know a priori which aperture it is going through. So it forms this superposition of, you know, a probability for being in 0, 1, or 2, which is the ABC slit positions, right? So this is one way of doing this. But we are not working on that. But having said that, these are previous papers which have dealt with exploring, again, the spatial degree of freedom, but by that approach that I just talked about, including work that I was involved in while I was a postdoc at Icqif. What we have done in our lab is a new way of establishing these spatial qubits. We call them spatial bin qubits. And this is called pump beam modulation. Okay, and this, of course, is a little bit of detail, and the experimentalists will, of course, appreciate this very quickly. But then just to give you a general idea, in down conversion, in spontaneous parametric down conversion, which is the main workhorse for most of our experiments in the lab, we have a pump laser, right, which is, of course, you know, goes through lots of optics. We skip that, and it is incident on a crystal which has a high nonlinear chi2 coefficient, and that gives rise to this pairs of photons, right? And that is what we call the spontaneous parametric down conversion. So 2 photons are generated. So having said that, usually the pump for down conversion has a Gaussian beam profile, Okay, and so then of course that is incident on the crystal, and your photons which are generated also carry through this Gaussian profile. What we have done is we have actually modulated the pump beam and made it, have this sort of a profile. So having a 3 aperture system in the path of the pump beam, we have changed the shape of the pump beam. And so now what is incident here is basically it looks like this. Okay, and so you can see my cursor. Can someone confirm that this is visible to you? The arrow, moving arrow. Sorry.
Yes, yes.
Yeah, great, thanks. Yeah. So then this is what is incident at the crystal. And so now what we are doing is using the fact that these daughter photons, as we call them, they carry through the property of the pump. Okay, and this is how it looks in the lab in lots of optics. Again, details. But having said that, this is a general idea. So I have a Gaussian profile, and that is what gets carried through by the daughter photons. But what I have done now is I have this sort of a profile at the crystal, and so the single photon profile at the detector looks like this. Okay, and so as a result of which I generate a 112233 correlation. So if the photon on the left, let's say there are of course 2, so left and right, let's say, so the left photon is passing through slit 1, and then the right photon would also pass through its corresponding slit. So when I measure a correlation or a coincidence measurement as a function of detector position, I would see peaks appearing precisely at those points. So 1 will correspond to 1, 2 to 2, and 3 to 3. And this is what we demonstrated in this first paper from our lab on this particular technique. And we saw that we have a very high correlation coefficient of 0.9. And this was our measure for correlation. Okay. However, having said that, what is important is that just to go on to the next part, we don't know a priori what kind of correlation this is, right? Now it is a correlation coefficient, it's a statistical correlation measure, but do we know if it is quantum correlation or not? So what we also did is we saw that, with just the pump beam, we don't get such a correlation. It is only when we measure it with the single photons that this correlation emerges. So that was already indicative that more is being captured at the photon level. However, now what we have gone on to do is measure this quantum correlation. So we have measured the entanglement that exists between these two Q traits, okay, that we have generated. But of course, that is something which we could have done anyway. And the standard way of doing that would be to do what is called quantum state tomography, which would, as you know, the number of measurements scales as n square. So if I have a 3×3, then, it could be a very large number that I need, like, almost 81, but then you could simplify a bit, but it's not a small number, and it scales very badly with dimension. So what we have done is we have come up with a new way of quantifying the amount of entanglement that can be present in bipartite Q-DIT system by using statistical correlation measures and relating them to measures of entanglement. So now we are not going through the tomography route. We have derived a monotonicity relation between negativity, which is of course standard entanglement measure, and sum of Pearson correlation coefficients for arbitrary dimensions. So this is very important that our method actually works for NED. Okay, and so now by measuring this statistical correlation in a complementary basis, so essentially it is just one set of measurements really that it boils down to, I can tell you how much negativity my system has. That is one. Then we have derived a relation between negativity and sum of mutual predictabilities for arbitrary dimensions. So mutual predictability is yet another standard statistical correlation measure. So now instead of Pearson, we can do this as well. And again, that also works out beautifully. Now we have shifted from negativity to another measure of entanglement, which is entanglement of formation, and shown how that is related to mutual information for arbitrary dimensions. So these are various relations that we have analytically derived between measures of entanglement and measures of statistical correlation. And as a result of that, what we have been able to do experimentally is a first direct measurement of an entanglement monotone. So a direct measurement which is not, essentially derived from our tomography results, which is what people usually tend to do. So this, what has happened in this domain is that, people have tried, many groups have tried to reduce the number of measurements that are required to, have a hold on entanglement. But what we end up with is lower bounds on various measures. Lower bound of entanglement of formation is a very popular one, but this direct measurement is what we have been able to achieve, and this is the reference for that. Do have a look. We have also been able to show experimentally that negativity and entanglement of formation are non-equivalent entanglement measures. And so what do we mean by that? We mean that, if we had a maximally entangled state and we quantified the deviation from the maximally entangled state, that our particular entangled state is capturing. So negativity would, what would you think? You would think that irrespective of the measure you choose, it would quantify the same deviation, but that's not true. In fact, we have shown that these are not quantifying equal amount of deviation from the maximally entangled state. And we could do this, we could measure both of them, in our experiment by using statistical correlation measures. And we have also shown, and so this then becomes a first experimental demonstration of this non-equivalence of different entanglement monotones in higher dimensions. So this is our work in which we capture the experiment as well as the theory applicable to pure states. And in this one, we have extended this to 2-qubit mixed states, again in arbitrary dimensions, again using one pair of complementary observables. But here we also have some interesting observations regarding not just NPT, but also bound entangled states. And I will not be able to get to details of all these, but the idea is to motivate you, to have a look at all these results. And then, if necessary, we could have discussions today or later as we go by. But then this is capturing the results that we have derived. So here, you see the relationship between mutual predictability and negativity. And so this essentially, this one comes from the Z basis, okay, and this term comes from the X. So these are the complementary bases that I'm talking about. And so since this is one, I mean, in our experiment, we can just measure this, because this anyway is bounded to one. It will not be anything different. So instead of introducing new experimental errors, we just concentrate on the X measurement. Okay, and so that's what we do in the experiment. And this is for the Pearson correlation, again 1 plus linearly proportional to n, and by assuming the form of the wave function to be this, that the mutual information is given by this quantity, and so that is how it is related to the entanglement of formation. So the entanglement of formation and mutual information actually are boil down to being the same in this case. So we have measured all these quantities, and then derived essentially negativity and entanglement of formation in this work. And this is how the experimental schematic looks in more detail, but then you got the flavor. But this is interesting. So here you have the singles as a function of detector position. So the singles basically show you the triple aperture. Natural expectation is that you would have this sort of a peak and little broadening because of imperfections. But then now, if you are going to measure the coincidence, so you have your detector at one slit position and you have the other detector moving along the plane, then the coincidence peaks would only show up at precisely the 1, 2, and 3 locations. Okay, and so this is what you can see here. And this is what the coincidence, in the interference plane. And this is important. So in the focal plane, you measure interference. That has been shown earlier to be, certification of entanglement. So this already is the first step towards saying that our system is entangled. Now we go on to actually quantifying the amount also, which, as you can appreciate, is important, because when you, especially in experiments, when we are dealing with situations where we are using this entanglement as a resource for various QIP tasks, we need to know how entangled it is. You can't assume a maximally entangled state and do your calculations like we do in theory. In experiment, it is never going to be a maximally entangled state. So we need to know what entanglement our system has. And so our technique will be very important and useful in finding out the amount without having to really do the whole tomography. So that is the general idea. And we are working on various other applications of this, architecture that we have, which is this bipartite Qt architecture. We are going to scale it up as well and establish various protocols now that the entanglement has been quantified. And this is a snapshot of various results, which, if people are interested to have a look. Okay, so now, we don't have a lot. So this, again, is for very young students. If you're interested from a holistic perspective, you can have a look at this article. Okay, so go on to the next part, which is about giving you a new, method to do quantum state estimation. So we have been talking about a new method of quantifying entanglement in the first part, and how we can do that and the experiment and the results we have. Now we are talking about a new way of estimating the quantum state. Okay, and that is based on using the phenomena of interference. Okay, and of course we know we have a special liking for interference as quantum information people, because most of what we do boils down to using some kind of interference effect. And so it's based on these three results, but then primarily on this one, but it actually borrows from these two as well. Okay, so why quantum state estimation? Now, wave function is used to completely describe a quantum system and is, of course, central to quantum theory. In theoretical calculations, one can assume a form of the wave function and proceed with the calculations. But what about experiments? For instance, if you have a quantum computing scenario, you want to know what it is that you're starting with, because then this errors will also propagate as you go on with your gate applications. So it's very important to know what is your initial state, right? So precision and knowledge of the state of the system leads to precision in all that follows. And also, as we know, if we know the density matrix, we can calculate many important quantities from it. For instance, the reduced density matrix gives us the entanglement entropy, as you are aware. So in our work, we use one of the most fundamental phenomena in quantum systems, that is interference, to devise and experimentally demonstrate a new method for quantum state estimation, which we call quantum state interferography. Okay, and our central question is it possible for us to have a black box approach to state determination? So we have a beam. Beam is just a representation. It's basically a state. We have a device and we read out the state. Can we have a device with which, without any change of internal settings by the user, we can determine the quantum state of the system? And so that is what we are answering here in our experiment and theory, where we have shown you how to do a single shot state determination. By single shot, we mean no change in the internal settings by the user. Okay, so having said that, of course, quantum state estimation is not a new problem. There are many approaches which have been established over decades, and this is the most common one, which is quantum state tomography, where, of course, just like in its biological counterpart, what we do is we measure projections of the quantum state along different projective measurements, and then we reconstruct the state from these projective measurements. So as was discussed, this is something which requires d square number of measurements. So in this paper, these authors actually brought it down to 5d minus 7 observables for pure states. Okay, and I mean, this is the general idea of how you would do tomography. I'll skip that. But then, of course, as you can see, it already motivated people to think about alternatives, because it just gets very unwieldy as you go to higher dimensions. So can we do a direct measurement of the quantum wave function without doing tomography? And this is one of the very important results in this, where people have used what is called weak measurement to do this direct measurement of the wave function. And this one was another one where one of them was a different state, and this one was the polarization state of light. Okay, and so this is what we would do in weak measurement. So one thing, again, not going into the gory details, but you have to understand that in order to do this, we would have a normalization which is already proportional to this quantity, and then this quantity is dependent on psi. So there is a bit of an interesting circular argument that comes in here. But then, having said that, people did carry this forward to many different applications and approaches. Then came this one, which compared between direct state measurement and tomography, and actually, tells you that this direct state measurement is much less precise than tomography. So again, putting a little bit of a question mark on whether this is really the way to go. And came up with an approach, a different set of authors, that strong measurements give a better direct measurement than weak of the quantum wave function than weak. So then followed a plethora of work on this thing of using strong measurements and also experiment and theory. Okay, so what we have done here is, as I said, we call quantum state interferography. This is an interferometric method using which an unknown quantum state can be inferred from the visibility, phase shift, and average intensity obtained from an interference pattern. Okay, so there is no weak measurement. It is not a direct state measurement. This is a new single shot state estimation tool method using interference as a tool. In direct state measurement, you have less post-processing, but you have more number of measurements. But here we have one set of measurements, one set of settings. And by post-processing, we can actually find out these quantities and derive the state. And this is good for us as experimentalists will, of course, also appreciate because, although, the common assumption may be that we love spending time in the lab and doing as many measurements as possible. The first part is true. We do love spending time in the lab, but doing as many measurements as possible is perhaps not true. We would really like to do the number of measurements that is necessary to get to our aim, because more measurements means more errors. And so we don't really like having more than the necessary number, because that would just propagate in the error. So this way, our technique would be very useful because we can minimize on the number of settings that we are measuring in. Okay. And this is a snapshot which tells you how it scales. Okay. And so this is with the dimension of the system. So quantum state tomography without assumption, requires these many number of settings. And so you can see it scales like this. So for a 100-dimensional system, it's 9999. Whereas, if you assume pure state, it will be lower. I told you about this 5D minus 7. But for quantum state interferography, we require D minus 1, okay, settings. And so you can see it scales very nicely. So the comparison is obviously very nice. So this has an obvious advantage as you increase dimension, and you will land up with only 99 as a requirement as opposed to 9999. And so this is the, the general, this captures the essence of what we have done, which of course has a lot of detail. And this is a snapshot of, the scheme. So having said that, I would like to ask Professor Goswami, do I have 10 minutes?
It's a 40 minutes thing. Yeah, I think you have about 7-8 minutes, obviously.
Okay, yeah. So I think, yes, just to have a heads up. So thanks. So now this is if this is your representation of the density matrix, then you can see that by measuring these two expectation values, okay, and sigma minus is my spin ladder operator, I can actually get A and B to the I theta. But now there's a catch here. I have to measure the expectation value of sigma minus, which is a non-Hermitian operator. So now this is the first thing. How do we actually measure the expectation value of a non-Hermitian operator? And this leads us to work that we did. This was done in collaboration, this theory work in collaboration with Arun at HRI and his then student, where we showed that we can measure the expectation value of non-Hermitian operators by using weak values. Okay, and so this is a theory work, and the general idea is that you can express a non-Hermitian operator as in a polar decomposition as a product of a unitary and a Hermitian. Okay, and so now if this is the operator of choice, it's essentially a product of these two. This guy is your unitary and this is your Hermitian, and so for the experimentalist, this is essentially just a half-fifth plate. At theta equal to 45, this becomes this, and then this is your polarizer, which is your standard projector. So now this is what we had done theoretically. But having said that, a catch again in the weak value, we need to, if you want to measure this, then this is a requirement. Again, this depends on psi. So we have to come up with a way where we can use this concept, but not necessarily do this particular measurement, because otherwise, again, the circular thing comes in. And this is what led to this paper, which is an experimental work, which we did, where we showed how we can measure this average of non-Hermitian operator with weak value, but using a Mach-Zehnder interferometer, and then essentially, breaking that circular argument. And so here you can see this was our scheme. Here you have the half-wave plate. Here you have the the projector, and again, skipping details. This is the maths is correct. So this is intensity as a function of the phase. This is what it boils down to. So you can see this expectation value of the non-Hermitian operator is hidden here. So by measuring this, you could actually infer that. And skipping the the details of the theory, but this is what we went on to measure, and we found that, matches very beautifully the measurement experiment and theory. And we also did the conventional weak measurement, weak value approach, and showed that, ours actually has less error in these regions, because naturally there the weak value shoots up. So we have better control. Now, these things come together to quantum state interferography, where we've combined all this knowledge that we have gained, during these pieces of work that we have done, and come up with a way to use this towards state estimation. Okay. Now, essentially, the idea is that if this is your representation of a mixed qubit state, so these are the three things that you would need to measure, that is theta, mu, and phi. Okay. And so these are the three things which you need to determine from the interference pattern. And again, math works out, you can trust me and then check it later. This is the intensity as a function of phase for the pure state, and this is it for the mixed state. So you can see that, from the pure, you only need the theta and the phi, but for the mixed, the mu also comes in, which is your mixedness parameter. And this is what it boils down to. So you can measure the phase shift, the average intensity, and the visibility, and these three quantities will give you the phi, the theta, and the mu. And that is what we went on to do experimentally. Lots of statistics, but then this is important. The fidelity was very nice. For pure states, we had 97 to 99%. For mixed states, it's always going to be slightly lower, but then still on an average 95, 96, which compares very well with quantum state tomography. Okay. And also we propose that this something which could be miniaturized. A miniaturized slit version could be made, and this is very exciting if somebody actually does this. So, by using slits, and then, these are two operators, the polarizer and the half-wave plate. Of course, to remind you, that is why we need them. And these sort of things have been done for other purposes. These sort of miniaturized devices do exist for, other approaches, other applications. But if this could be taken up, and that would be very neat. Then you have a little pocket-sized interferometer, which you carry around, and, you can measure the quantum state at will. So this would be a few millimeters in size, and it will, of course, work very nicely. And this scales very nicely, as I said, with dimension. And of course, that is something that we are very excited by, because we have shown you the details again. Math details I will skip here, but then you can see that by using D-1 interferometers, we can actually get the quantum state. And here we have shown you a way in which you can combine a horizontal and a vertical interferometry. And then by using only one such arrangement, you can get all these interference patterns. So instead of doing D-1, you can also do this by using just these two. And again, very nice if somebody comes up with the experimental demo for this part. We can also use QSI for measuring the state of a bipartite pure qubit, as well as its entanglement. And just to tell you that, it requires 2 settings and 3 patterns in QSI. Whereas, so if you want to quantify entanglement, we do it in a single experimental setup. So 2 interference patterns is all we need. QST would require 9 measurements. And if you do Bell violation, then you might say you require 3, but this is just a witness and it's not a measure of entanglement. So QSI actually can be used to determine an unknown quantum state of a qubit. We have already shown this experimentally with the single shot measurement, but then it can also be used for bipartite qubits for measuring its entanglement. And of course, in higher dimension, the beauty comes in with only D-1. And so, the scaling advantage is fantastic. And it should be, I would encourage my experimental friends in different, systems to explore this technique in higher D. And we are, of course, working on our, scheme in the lab using our system. Yeah. Okay, so since I have a minute or so, as I suspected, I will now switch gear a little bit because, the entire focus here was on our results in higher dimensional QIP, over the last couple or so years. So we talked about entanglement measures, a direct measure of entanglement monotones, and which scales beautifully in arbitrary D, both for pure as well as mixed states. Then we went on to talk about a quantum state estimation technique, which again is a single shot technique, which works very well in, of course, 2, but then beauty lies in higher D. Now we are talking about, just a couple of slides on this recent result, which I couldn't help showing a little bit, but then hopefully we have another conference in which, give the details on this one. And this is on a loophole-free interferometric test of macrorealism using heralded single photons. Of course, photons being the theme, this is where it comes in, but then this is not related necessarily to higher D, which was the focus of this talk. But this is something we have done very recently. And, this is our experimental schematic. And of course, the important point, 3 things that we have managed here is that we have done a test of macrorealism, which does not have, at least according to us, we have been able to address the known loopholes. And people in the community would know that, addressing these loopholes is always a very important challenge to meet when we talk about these tests of, macrorealism or even the Bell violation. Those tests, the loophole-free Bell tests were done in 2015. So this is the LGI counterpart of that. And what these results, of course, we're very happy about. So you can see that, this is for the LGI, the Leggett-Garg inequality, and the macro-realist upper bound is 1. And our experimental measured value is this, right? So 1.32 plus minus 0.04. So, we are, 8 times above the error value in this one, yes. And for the WLGI, which we don't really know whether it has ever been measured before, so here we have measured this to 5 times the error value. And so this is convincingly above the macro-realist bound. But the other thing we have done is we have actually found out what is the quantum mechanically predicted range for these quantities for our experiment. So found this out, taking our experimental non-idealities into account, because that is very crucial, because what you say is a 0 may not be a 0 if your error is, 10 to the minus 2. So that is the bound. So we have taken that into account, and this is very nice because you can see these match. So our experiment falls perfectly within the quantum mechanically predicted range using the experimental non-ideality. So we can say that not only have we given a loophole-free violation of the Leggett-Garg inequalities, which of course violates the concept of macrorealism, but we have also shown a perfect match with quantum mechanically predicted range for these quantities. Okay, so this one, of course, I wanted to keep it brief and I want to be on time. So I would like to then finish my talk and thank you once again.
Thank you. Perfect timing. Thank you for presenting all the work in such a timely manner. I'm sure there are lots of questions, but may I will actually ask you a question which is related to the very first part of the talk, where you managed to have the pump beam shaped to generate the qubits. So my quick question is, how do you confirm that you have a single qubit scenario versus a statistical scenario versus a single qubit scenario? What experimentally tells you that you are in one domain versus the other?
So we actually, of course, we precede this by doing coincidence measurements. So we are aware that we are dealing with a heralded photon source. So we know we are dealing with a single photon on this end when we have the photon on the other end. So obviously we are dealing with a single particle. So there we don't have this pump beam modulation. Then we go on to modulating the pump beam. And so then, of course, what we are doing is we are just essentially changing what should I say, the pattern that this photon will emerge with. So instead of a Gaussian, it is emerging as 3 peaks, right? And so now what we are doing, and this is something you will appreciate, we are actually putting the detector at one of these positions, and we are scanning the entire detector plane on the other side, and we are confirming that we get a peak only at one position at the micrometer domain. So naturally, we are dealing with a bipartite three-state scenario, right? But then, of course, one question that could happen is that is there any other further confirmation that this is a Q-trit? And of course, we have created a 3-state system this is, a nice demonstration of a three-state system, and these two are also nearly maximally entangled with each other. But then we could do further, and which is what we're working on now, further tests of, proving different ways of broaching this superposition, let's say, by changing the plane and so on and so forth. But that's a detail. But I hope that answers your question.
Wonderful. Thank you. So I think there's on the chat box, Shibashis has said that you would like to make a comment. So please, Shibashis, would you like to make a comment?
Hi, Urvashi, nice talk.
Thank you,
Can you hear
Shibashida.
me?
Yes, I can.
Okay, so this is about the first part where you have talked about this, this tomography and then entanglement detection.
Yeah.
I mean, measure of entanglement. So there is a work some time back, maybe during 2016 or 17, in fact, a pair of works, one from the Laflamme's group, and the other one I don't actually remember. These are both theoretical works. So basically what they have claimed is that if you take if you want to detect entanglement in arbitrary state of a given bipartite system, which may be 2 qubit, 2 qubit, whatsoever, the number of measurements that you will have to perform will be same as that for doing state tomography. But this is for the arbitrary state. Okay. So
arbitrary dimensions, Shivashida?
Not arbitrary. I mean, dimension is fixed. You can take, say, qubit or qubit, whatsoever. Dimension is fixed. But the state is arbitrary from that dimension.
Okay.
And single copy. You'll have to perform measurement on single copy of the state at a time. So the number of different measurement settings that you will require to detect its entanglement. I'm not talking about estimating the measure of entanglement.
Okay.
To detect its entanglement will be same as that you would require for state tomography. So,
okay.
So I wonder.
So your question would be how this relates to that?
Yes, yes.
Yeah. Okay. So first of all, of course, I would talk to you separately to get the exact references. But having said that, one thing that I suppose was, I didn't get much time to discuss, but then you can see that in our case, there is, one particular knowledge that is going into this, right? Which is that this is a pure state or a mixed state. So, when you say that their paper actually dealt with an arbitrary state, so there, this knowledge is not part of that, right? So they are saying that this could be anything. It could be pure, it could be mixed. But then in our case, so this is not in the same genre. So what we are saying is that if we have this partial knowledge about the purity of the state, then we can actually apply what we are doing. Because you see, I only showed you the pure state relations, but we have the equivalent ones in the mixed state, which I'm happy to discuss separately. And so then there, the knowledge of the type of purity does matter in our way of doing this. So this is not countering what you have said, because what you have said exactly boils down to saying that, if we don't have this knowledge, then best we can do is tomography. But then what we are saying is that if this knowledge exists, then we can actually do much better. And so what we would say from an experimental point of view is that, if I did one set of measurements to know the purity or the type of mixedness that my state has, then the rest of the time when I'm using this for any application, I can use this method to measure the amount of entanglement. That is the second difference, Shivashida, that one you're talking about detecting it. So it is more like a certification or maybe a witness type thing. Whereas in our case, we are telling you the exact amount. So, they are not contradicting each other for sure. But then, I would love to have the particular references so that, I can perhaps get back to you with even more focused comments on the comparison. Yeah.
Thank you.
Okay.
Thank you.
Thank you. Actually, I think we don't have enough time, although there is a question which I think, Urvashi, you should know so that you could perhaps answer to this question later. This is Ajit Iqbal Singh's question.
So I can write in the chat window then.
Yes.
Yeah.
Sure. I'll be going on to the next lecture because
Thank you.
We are run out of time. So thank you very much. Now our next speaker today is Srikant, and many of you here in the community know him already, but it's very nice to be able to introduce him. He received his PhD from IISc Bangalore, and then he has been a postdoc at the Center for Theoretical Studies, ISC, and then at the Light Matter Physics group in RRI before he joined his present position of as a faculty fellow in the Purnaprata Institute of Scientific Research. And he is currently assistant professor. And his research interests include foundations of quantum mechanics, quantum information science, cryptography, solar physics, philosophy of science. And today he will be talking about invertibility of maps and the quantum dynamical semigroup. Over to you, Srikant.
Am I audible?
Yeah, you are
David?
audible. You have to share
the screen.
Yeah. Yes, we are able to see you. Is this
Okay.
no? This is your 63rd slide. You have to go back to your.
Yeah.
Okay, you are aware of the time window, so I'll just ensure that you can go ahead with it.
Okay. Is it okay?
Yeah. Please go ahead. Yeah. Thank you.
I'm very thankful to the organizers, Professor Swapan Rana, Professor Ramesh Rahman, and Professor Indrani, and also thank you very much, Professor Debu Goswami, for your kind introduction. So today I'll be talking about the non-invertibility of the quantum dynamical map and the quantum dynamical semigroup. It's work that I've done with my collaborators, Dr. Vinayak Jagadish and Professor Francesco Petruccioni. So a brief overview is that we will be studying the mixing in a d-dimensional Hilbert space of the d+1 generalized to the qubit Pauli channels in a Hilbert space of dimension d, and determine the conditions under which the resulting mixture is a semigroup. And one of the results that we find is if we mix only semigroups, then we cannot produce an output that's a semigroup. And counterintuitively, we find that the mixing, in order to actually obtain a semigroup, which in a certain sense is, the quintessential Markovian group, you actually need to have non-invertible channels being mixed. So there was an earlier result that said that non-invertible maps can lead to a semigroup when mixed. So our result is that non-invertibility is necessary. Further proceeding ahead, we also study the mixing of channels which are characterized by a very specific decoherence function, which is a very natural form of the decoherence function that you can take that allows you to go from the semigroup form to a non-semigroup form. Also Markovian, non-Markovian, and non-invertible channels. And so the decoherence parameter here is n, and then we have a decay factor, which is c. So here, in this case, what we do is we evaluate the measure of invertible channels that's obtained by mixing all these channels. And we find that it increases super exponentially with the dimension d within its allowed range. And we also very briefly, I'll try to touch upon, depending on the availability of time, upon a certain convex resource theoretic perspective that we can take on the results that we obtain. So that would be non-Markovianity on the one hand and non-invertibility on the other hand when talking about quantum channels. Now, as is very known to this, very well known to this audience, but only for the sake of completeness, I'll briefly talk about open quantum system dynamics. So as we know, we generally have, for any closed system, a unitary evolution through which quantum systems evolve. So any density operator is acted upon by a unitary operator and thereby evolves to a valid density operator subsequently. So more generally, you have a dynamical map. So if you're talking about an open system, and it evolves the input density operator rho to rho prime. Now, while it does not need to be unitary, nevertheless, it should be linear and trace preserving. It needs to preserve the hermiticity of rho, and it maps positive matrices to positive matrices. Now, looking at the differential form or the differential representation, differential equation representation of such an equation, we have what is called the Gorini, Kosakowski, Sudarshan, Lindblad equation, named after the founding fathers of this area. So in this case, a system that's undergoing open system evolution through a map phi t is governed by the phi dot equal to L phi, where L is the Liouvillean or the Lindbladian, if you like, which is given in this particular form, where the G's are often called the noise operators or the Lindblad operators. So H is the Hamiltonian, the driver of the unitary evolution, and gamma, IT are the decoherence rates, are the Lindblad rates, are the decay rates, which for Markovian evolution will be positive. Now, if the map is divisible, then I can always find for, I can break it up, right? I can compose it in terms of an initial map and then an intermediate map to obtain the full map. And the intermediate map, which is phi evolving from T to TF, right? So if it has this structure, then it is divisible. Furthermore, if this intermediate map is completely positive, in such a map, the overall map is said to be CP divisible. Otherwise, it is CP indivisible, which is one definition of non-Markovianity. Now, a quantum dynamical semigroup is a particular kind of, one might say, quintessential Markovian evolution, which satisfies the composition law, namely, you have an evolution from of this sort, then I can always have this composition law where I can take the sum of these times and this would be valid. So in a way, it is like saying that I can evolve the system and then evolve the system again and I can compose it, which essentially says that there is no memory of the initial time. So this sort of a quintessential memorylessness is captured by the quantum dynamical semigroup, or sometimes just called semigroup for short. And what this entails is that the generator of such a map is so L into just T minus T naught, right? So I could, and L is a constant basically. So when it has this structure, so the QDS is then generated. In the GKSL equation, all the decoherence rates, gamma I that I talked about in the previous slide, they're all constants. So the question that we will be asking is, when we have a qubit space or a qubit space, Hilbert space, so what conditions do we need to impose on convex combinations of these qubit Pauli channels so that the resultant mixture is a semigroup? And surprisingly, what we find is that non-invertibility of the map is necessary. That is, the maps that are being mixed, they need to contain non-invertibility in order for the resultant mixture to be a semigroup. So this idea of mixing maps has provoked some interest in the last 1 or 2 years. So we had studied, for example, the convex combination of quantum channels in various details. So we had looked at qubit channels, and what we did was we considered mixing semigroups and non-semigroups, and we showed that the resultant set can contain CP indivisible Pauli channels, and that the set of CP indivisible or CP divisible channels are both non-convex, and we quantified the measure of the CP indivisible channels that you get. So the non-convexity of the set of generalized Pauli Markovian channels was also recently studied by Shubinska. Now, non-invertibility essentially means that you have some time, intermediate time, let's say T star, such that the map cannot be inverted. So we had earlier talked about the composition rule. So if you have a perfect divisibility, then I can always invert the intermediate map in order to get the evolution that goes from T start to T final, right? But if this inverse is undefined, then this constitutes a singular point. So here the decoherence rate, when looked at from the differential form perspective, the decoherence rate will go to infinity. But importantly, the dynamics will still remain perfectly regular. What would happen is that a set of input states will become will map to an identical subspace or an identical set during the point of singularity, so that it becomes non-invertible, and that's reflected as a singularity in the decoherence rate. Now, in earlier work, we had also studied the convex combinations of channels with singularities, that is to say non-invertible maps. And we had obtained certain interesting results in terms of, for example, the shift of the singularity, etc. But that will not be the focus here. But in two previous works, we had studied the fraction of Markovian channels that are obtained under mixing of Pauli qubit invertible channels. So continuing that line of investigation, here we want to ask the conditions under which a semigroup is obtained by mixing not Markovian or non-Markovian channels, but instead by essentially potentially even mixing non-invertible channels. So in specific, we will address the problem of mixing Pauli channels which are non-invertible, and we find that the resulting mixture of non-invertible channels can be invertible, and in fact it can be a semigroup. We will then evaluate the measure of the set of invertible regions when you mix non-invertible maps. So in general, Pauli maps is something that is well known, especially in the qubit case. So you have the map which is given by a mixture of, let's say, with probability pi, you have a particular Pauli operator acting. And with 1 minus pi, you have the identity operator that acts. And that gives us a Pauli channel in the x or the y or the z direction. Now, in order to create a semigroup, one can have two strategies. One is mixing the same type Pauli channel. Let's say, for example, just the sigma x dephasing channel or the sigma y dephasing channel, but using two different values of the decoherence parameter. We just need to play around, adjust them so that what we get is a quantum dynamical semigroup. The other would be to mix three different Pauli channels with suitable choices of the decoherence parameters and the mixing fraction xi, so that they're all tuned in order to produce a semigroup. Now, for example, let's say we consider the problem of mixing the same type of Pauli channel. So we could have, let's say, just the Pauli X dephasing channel, and we could mix two of them, let's say one with the decoherence function, which is P, and the other with Q. And for this map, we can correspondingly write down the differential form of the evolution, which is the generator form or the master equation. And one can compute the decay rates in terms of P and Q, and this is what we will find. Now, for the semigroup, the gamma, the rate has got to be a constant, and we can ensure that this is the case, for example, by setting P to have this particular form, and we can choose F to be this form and let Q to be arbitrary. In fact, it can also be a function that contains a singularity. It doesn't matter, because there'll be suitable cancellations that ensure that the quantity that we get here is essentially one can evaluate it and find that it's some, I guess, 1 minus A into C, this constant, the decay constant that comes in. An easy example here, for example, let's say we look at the Pauli X channel where we add two functions, two channels with parameter P and Q. And I choose P as per the recipe that was given in the previous slide, which has this particular form given in equation 11. So 1 minus E minus CT and Q. And I can have Q being arbitrary. And then evaluating it, what we find is that we obtain this equation 12, which is the master equation form of this map, and we can see that the rate is constant c by 2, which is the telltale sign of a quantum dynamical semigroup. So what we considered now was to produce a semigroup by mixing just a Pauli X and a Pauli X channel. But now what we will do is we'll mix the channels which are Pauli X, Y, and then Pauli Z. So in this case, for example, I have the decoherence functions given by Pi, and Xi would be the mixing fraction. And again, we can go through this whole, so I have this map. I can then write down the corresponding master equation, and the rates will turn out to be the following, that is gamma 1, gamma 2, gamma 3. So we have this equation 15, but equation 14 basically tells the simple structure that we have, which is essentially that you have these three variables A, B, C, and you toggle the plus and minus sign between them. So with this, we for a semigroup, as we said, all the rates gamma I should be constants, and this entails that A and B and C must all be constant, because, for example, we can solve for A, B, C in terms of the rates, and we get C, for example, equal to gamma 1 plus gamma 2 by 2 for all time, and so on and so forth. And a little bit of inspection will tell us that the only functional form of Pij that meets this requirement is this particular form. And what's interesting about it is that the decoherence function of a particular input channel that is getting mixed should be related to the mixing fraction also in this particular way. So the mixing fraction is Xi. Only then, mixing them in this way, would I be able to produce a semigroup. But we immediately see that with a mixing fraction which is of this form, the point at which it becomes half basically. So that would correspond to singularity. Alternatively, one can write this down in the form of a master equation, and we will find that at this particular time, the rate which is given here will blow up to infinity. So saying that in order to produce a semigroup by mixing three of the Pauli channels, we need them to be non-invertible. So the semigroup here, as a matter of passing, would correspond to Xi being equal to half, because then you'll get 1 minus e power minus Ct by 2, which when written as a in terms of master equation will never attain, you know, infinity in finite time. The rate will never become infinity. So now in particular, let's consider the equal mixing of the three Pauli channels. In this case, we have the mixing fractions would be 1 by 3 each. And each of the input channels are described by the same decoherence function, which is 1 by 4xi, as I earlier said. For xi, I just put 1 by 3, and this is the function that we learned. And of course, by design, this will lead us to a semigroup, but we also see that the associated rates, if you express them as master equations, we will find that the rates are given by this. These are not constant, and in fact, they diverge at this particular time, as we find by inspection, indicating that these individual channels are non-invertible. So you need non-invertibility of the input channels in order to produce a semigroup. So this generalizes for qubits a particular result of Shubinska, where the semigroups results via an equal mixing of the three non-invertible Pauli channels. Our result basically allows us to go beyond just mixing three semigroups, and that will be made precise in the following result, which is this. In order to produce a semigroup by mixing Pauli channels, the first point is that all the three Pauli channels have to be used. That is, if even one of them is missing, then one cannot produce a semigroup. And of these three Pauli channels, at least two have got to be non-invertible. So supposing only two Pauli channels are mixed, say for example, x3 equal to 0 without loss of generality, we set that equal to 0, but we've earlier shown that the corresponding decoherence functions will have this particular form, and putting any one of them to 0 would mean quite non-physically that the pi becomes infinity. So all the three rates, all the three Pauli channels have to be mixed with non-zero, fraction. And for an input channel to be a semi-group, as we said, you need to have the particular form 1 minus e power minus ct by 2. And therefore, it means because this would mean that the corresponding xi should be half. Therefore, now if minimally we assign the probability half to one of the channels, then the other two channels on average will have a probability 1/4, right, which is less than half, with which they are mixed. And that would imply that they are non-invertible. So even conservatively, if you make one to be invertible and the limiting invertibility, namely you make it a quantum dynamical semigroup, then the other two channels should necessarily be non-invertible. Yeah, so again, going back to another instance of mixing, we showed that when you mix these three different Pauli semigroups, you could actually produce non-Markovianity also. But a preceding result, which essentially says that you need at least two of the mixing groups to be non-invertible in order to produce a semigroup, implies that just by mixing semigroups, which was our previous work, we could not produce a semigroup. We could produce, in general, Markovian invertible channels. So in other words, all the channels there that we found were invertible. One could ask the question whether in the resultant mixture, there is also a semigroup that's found, and the answer in light of the preceding slide's result is that no, you cannot, one cannot. Now, just to put this in perspective, one can look at other slightly contrasting results that were obtained vis-a-vis non-Markovianity, right, as against non-invertibility. So when you have finite mixing of two Pauli semigroups, it always results in a non-Markovian output. This generalizes a result of Wodarski and Kruszyński, where they only consider a uniform mixture of two semigroups. And then they show quite interestingly that you obtain a non-Markovian channel. In fact, what is the eternal non-Markovian channel? A generalization says that any finite mixing of these two channels will also lead to non-Markovianity. And in particular, we want to say that our result here does not contradict another result of Wodarski and Kruszyński, where mixing of two CPTP projector channels leads to a semigroup. So CPTP projector has this particular property that the channel can be considered as as a mixture of a CPTP projector and the identity channel. And clearly, the Pauli channels that we are considering don't have that CPTP projector structure. Now, whatever I have shown in the previous slides in terms of mixing qubit channels in order to, non-invertible qubit channels in order to produce the semigroup, it can be generalized to the case of qubit channels. So that is what will be done here. So qubit Pauli channels are based on the concept of mutually unbiased spaces, as was introduced by Nathanson and Ruskay. In this case, what happens is the way the construction proceeds is that we have these d+1 orthonormal bases in this d-dimensional Hilbert space, and they have this MUB structure, namely that the inner product square is 1/d for any two of the MUBs, distinct MUBs. Now we construct the rank 1 projectors based on their eigenstate, and then one can introduce d+1 unitary operators U alpha of this form. And a general, a depolarizing qubit channel can now be constructed. So the way we do it, we have a convex combination of I, Pauli X, Pauli Y, and Pauli Z. Something analogous can also be done in this case. But the particular special structure that was there in the context of Pauli, qubit channels has to be generalized in the following way, as given in equation 18, where P alpha is any of these depolarizing probabilities. And in particular, supposing we define this mathcal U alpha in this particular fashion as given in 19. So for a particular Pauli channel, so you have a d-dimensional Hilbert space, we have these d+1 Pauli channels. One of these particular, if you like, dephasing channels, if that word is okay, can be defined in terms of these operators as given here in equation 20. So our strategy here is that we take these d+1 channels, and to each of them we assign the probability xi, that is their mixing fraction, and then we mix them and then look at the resultant mixture and look at search for conditions under which the resultant mixture is a semigroup, quantum dynamical semigroup. Now one can perform the following exercise, and one can evaluate the eigenvalue spectrum of the mixture, and that is shown. Actually, the Pauli operators themselves will turn out to be the eigen operators for this map, and the corresponding eigenvalues would be given in the following way, as given in equation 22. So the condition for this to produce a semigroup is that sigma I should be an exponential, like e power minus RT, where R is a constant. So we need to get the structure. So all we will be doing is looking at the constraints on the X's and the P's so that this particular thing is obtained. As in the qubit case, we can do the same thing. One, to produce a semigroup, what we do is we can mix two or more channels of the same type. By the same type, I mean, for example, a Pauli X or a Pauli Y or a Pauli Z. So in the case of qubits, you will have d+1 channels. So one can mix 2 or 3 channels of the same type by adjusting their probabilities and their mixing fractions in such a way that you produce a semigroup. The alternative is that one can mix all the d+1 channels with suitable corresponding decoherence function, and each channel, of course, itself could be a mixture of versions of the channel with various PTs. So that possibility obviously exists. Now, example of the first point about point 1 that we gave you, which generalizes the example of the qubit instance that we given earlier, which is that it's the same thing, that you need to mix the same type of channel with two different decoherence functions. Let's say P could be the decoherence function of one, and Q could be the decoherence function of the other. And for the resulting map, one can straightforwardly find that the eigenvalues turn out to be in the following way, the corresponding eigenvalue. And again, to get a semigroup, that is to say, in order to arrange that lambda I is equal to e power minus a constant into T, we can let P to be a function of this form. We need to have P in this form and allow Q to be arbitrary. So P will be the decoherence function of one of the channels, and Q will be the decoherence function of the other channel. And we basically engineered it in such a way that lambda I will turn out to be this constant, which can be checked by just directly plugging in these values. And of course, we have just mixed two channels, but you can mix more of them. But the idea is the same simple one, that we can tune the P's, Q's, and all these mixing decoherence functions in such a way that the eigenspectrum, the spectrum of the resulting channel, has this exponential form. Now we can come to the second instance, which is perhaps more interesting, namely that all the d+1 channels are mixed. So in this case, the eigenvalues of the resultant map as before. So in each of the d+1, directions, if you like, the Pauli dimensions of the d-dimensional Hilbert space should have this exponential form in order to have a semigroup. And from equation 22 that was earlier given, we see that the sum has d terms, and therefore, again, as in the qubit case, by inspection, we find that the only choice of the input channel functional form is that the PI, that is the decoherence functions of the channels that are getting mixed, should have this particular form. Again, the main thing to note here is that the decoherence functions PI are dependent on the mixing coefficient. So if the decoherence functions are already given, then they should be mixed in the right proportion, in this way, in order that the resultant mixture can be a semi-group. But again,
Srikanth, I'm sorry to interrupt, but you only have about a minute or so because the last 5 minutes are reserved for question and answer.
Okay. Thank you so much, Devu. Somehow I was not keeping track of the time. Yeah. So anyway, just to go through this quickly. Here again, I'll just state the theorem here and the following theorem. The results are roughly analogous, kind of straightforward generalizations of the qubit case that I had spoken in some detail earlier. So the theorem here, or the main result here states that all the d+1 qubit Pauli channels must be mixed in order to produce a semigroup. As in the qubit case where I'd shown, if even one of the d+1 channels is not participating in the mixture, then you cannot produce a semigroup. And earlier we had shown that of the 3 channels that are being mixed, at least 2 should be non-invertible. And the corresponding result here turns out to be that of the d+1 channels in the d-dimensional Hilbert space, at least d channels must be non-invertible. Yeah, so here again, what we did was we actually, now let's say we mix these channels. Now, if they are invertible, one can show that is to say that the particular form as given in equation 28 is the form that we consider for the mixing of potentially non-invertible channels. And if the parameter n exceeds this, then the channels, what one can show is that the mixture is also invertible. And whereas if n is chosen to be smaller than this quantity, then the resulting mixture is necessarily non-invertible. And so we studied in this range. So in this range, depending on the choices of x that we make, we obtain a fraction of channels which are invertible and those which are non-invertible. And what we find is that the fraction of channels that are invertible is given by this particular function that is given in equation 27. And essentially it comes by determining what are the you have to integrate over each of the xi's. One can find the lower and the upper bound based on the requirement that the mixture has got to be invertible, and performing that integral then takes us to this, and then there's a normalization factor. All of this put into picture gives us that particular fraction. And I think with this graph, I will actually stop. So we can essentially see that the variation of the invertible fraction as a function of t, choosing n. So some amount of fine tuning is needed in order that n falls within this range, which is the interval d square by d square minus 1 comma d by d minus 1. And therefore we find that as the dimension is increased, and within this range, we find that the invertible fraction actually increases super exponentially, like it goes as d power d. And okay, so in conclusion, we studied the set of qubit Pauli channels and the general conditions to produce a semigroup by mixing them. A semigroup cannot be obtained by mixing only semigroups, and rather counterintuitively, you need non-invertibility among the input channels to produce a semigroup. And considering that semigroup is Markovian according to almost all definitions of quantum Markovianity, the requirement of non-invertibility appears to be surprising. And also our results imply that in the context of the family of qubit Pauli channels that we consider, non-invertibility is a kind of a convex resource in the sense that mixing invertible channels can never produce non-invertibility. On the other hand, a mixture of non-invertible channels can lead to invertibility, and one can actually obtain the fraction of invertible channels that you get. So convexity of invertible channels may be contrasted with the non-convexity of the set of quantum Markovian channels. On that basis, earlier in the Markovian case, we argued that CP indivisibility doesn't yield a convex resource theory, but by contrast here, it seems that non-invertibility is a kind of a convex resource. So thank you very much. And thank you, Debu, for reminding me about the time limit.
Okay, thank you. Thank you. There are quite a few questions. I don't know how much we'll get to, but we'll try our best. See, there are some on the chat box, which we'll come to in a minute. There is one hand from Bihalan Bhattacharya. Please go ahead.
Am I audible?
Yeah.
So thank you very much, Professor Shrikant, for this nice talk. I'd like to ask that whenever you are considering these non-invertible dynamical maps, so in case of non-invertibility, the kernel of the map is non-trivial. I mean, non-trivial means it's not zero-dimensional. So can we comment something on the dimension of the kernel in this case, whether it is image non-increasing or something like that?
Oh, okay. Yeah, I think you're actually right. This particular aspect we were planning to look at this moment. So what we have done at this point is that we've checked that the non-invertibility that we have on the map level, it remains regular.
Okay.
And on the level of the master equation, that is on the level of the generator, it blows up. But I think you're quite right that in terms of the kernel, there are other aspects. Actually, determining, you're quite right, because of the fact that the kernel is a bit non-local. So one of the things we've been saying is some of the clean results that we are able to obtain by looking at the maps and the singularities. I mean, that is something that we are actually studying in terms of the kernel.
Okay, in that sense, you can connect also divisibility and information backflow notions as well in the same setting in this.
Oh yeah. Oh yeah, absolutely. Yeah, for example, you're quite right. I mean, so we have mostly looked at CP indivisibility, and in many of these cases, actually, it also boils down to P indivisibility. So you're right. Yeah, absolutely. Yeah, that's a very interesting point.
Thank you very much. Thank you very much.
Okay, thank you for the paucity of time. I think we'll have to stop the discussion here. But there are two questions on the chat box. Shrikant, if you could kindly address them on the chat box, that will be very kind of you.
Oh, yeah, sure.
Please do that. Okay, so we can go on to the next speaker. Our next speaker is actually one of the questions is by the next speaker, so it's all right.
Oh, okay.
Our next speaker is Arvinda, and Arvinda did his PhD from Pune Praja Institute of Scientific Research, Bangalore. His area of interest include quantum information and computation, quantum foundations, quantum information theory and computation, quantum many-body theory, quantum chaos, and philosophy of physics. Currently, he is affiliated as assistant professor in IIT Tirupati, and he will be talking on the maximally entangled and entangling unitary operators and its role in constructing a quantum ergodic hierarchy. So here is Arvind. We can see your slides.
Can you hear me?
Yes, we can now hear you also. So I'll let you go ahead with your talk.
Yeah.
Yes.
First of all, I thank the organizers for inviting me to this wonderful conference, and thanks Professor Goswami for introducing me. And this is the work which I did with Suhail and Harold, and the major references are here. These are the two papers, which is independent, two different results, but combined on the field of constructing maximally entangled and entangling unitary operators. Okay, let's begin. Why? What is the motivation? We know that quantum many-body systems are ubiquitous in the sense that it is in quantum information theory, quantum chaos, people are looking, and then condensed matter physics, and of course in the quantum computation, because in some sense, what is quantum computation? If you ask, it is a controlled many-body system. and it is playing a very prominent and crucial role in understanding the black hole physics and also in the string theory. So with such a broad interest, what are the problems? The basic and fundamental problem is what termed as a curse of Hilbert space dimensionality, because the dimensional grows exponentially, dimension of the Hilbert space grows exponentially. So it's too difficult to numerically tackle anything. And the one important problem is the lack of minimal exactly solvable non-integrable models. So, many-body non-integrable models, which will help us to analytically analyze few functions or the few physical quantities. So one of the main motivation is to look into the minimal model, minimal non-integrable many-body model, which is in some sense solvable. The some sense in the sense that we need it may not be exactly solvable in the way the solvability is defined, but still some of the quantities of physical interest, whether can that be physically tractable, analytically tractable, and can we make any substantial statements over that. So this is one of the motivation which I'm having. Is it clearly audible? I have to reduce my voice. So is that fine?
No, it's fine. Perfectly. Please go ahead.
Okay. So, okay. And another, because I come from the quantum information theory, and the one motivation personally which I was looking into is that where does and how does I can combine the tools from quantum information theory into the other physical systems, especially in quantum many-body systems, many-body physics, where what aspects of the quantum information theory plays a crucial role in the many-body physics. It has been already explored in the condensed matter physics and quantum gravity in the various literature. So this was the second motivation which I was looking into this field. And the third one, since I come from the quantum foundation as well, so in this conference, till now we have been heard about many talks on the entanglement of states. And in the first talk here itself was characterizing the entanglement of the states. Professor Urbasi explained in detail, and entanglement of the measurement, like network non-locality, whatever the talks which we have been listening from last 2 days, is because of the kind of entanglement of the measurement. So my question was that there is a third aspect of a physical theory, which is the dynamics. So is there any features of the entanglement of dynamics which is helping us in some way in many-body systems? So under these are the broad motivations which made me to look into these problems. Okay, since it is many-body physics, we will be starting with some diagrammatic frameworks. Especially in this work, we use the diagrammatic framework. Mathematically, we could say that category theoretic framework or tensor networks. What people use the different languages. So let's define. Let's begin with the unitary operator defined and the bipartite Hilbert space, where Q is the local dimension, local Hilbert space dimension, and this is the unitary operator, and here we are representing operator element. So, and the dagger is represented in the red color. So the Lqcc carries the quantum system, for example. So, and the unitarity diagrammatically is represented by contrasting the lower legs, and or other words you can use that UU diagram for identity, it goes up, and these are the identity. So the unitarity is being represented in this form diagrammatically. So what is the system which I am considering? The system which I am considering is the many-body circuit, quantum circuit, in which the unitary is acting on two sides. So it is a one-dimensional chain, one-dimensional spin system, in which of length L, and in every two sides, unitary is acting in two sides, and in the half of it, see, the two layers constitutes one unitary operation, in the sense that first it acts on, for example, let's take the first unitary, first acts on 0th and half position, and in the next time the unitary acts on half and 1 position. So these two comprise one unitary step, and this diagram, for example, comprises of two unitary steps, and here time is discrete. So we are considering the discrete evolution, just like in the unitary dynamics. Recently, for example, Sycamore and other have considered, Google Sycamore and other people have considered these type of structures. And in the literature, the people have tried to ask the question that can the solvability be expected in such systems? Initially there were very few results where the randomness was introduced by using the random unitary operators in this circuit, and they were able to characterize at some large Hilbert space limit the entanglement entropy, the dynamics of the entanglement entropy. But our question was not for random unitaries. There is a fixed unitary, and for any dimension, any local dimension, need not be very high local dimension, can still solvability be expected. Okay, so this is the circuit model, and you can what the Aquila et al. And Bertini, what they introduced. If you see from horizontal direction, this is the evolution. This represents this equation 2, the unitary represents evolution in the temporal direction. But you could even view from the circuit evolution in the spatial direction, from, for example, from right to left. This represents the evolution in the spatial direction. So the evolution in the spatial direction is represented by UR, where UR is a realigned, a reshaped matrix, which I will be going to explain in detail what it is. But let's think that, so what it is, one way it is evolution in the temporal direction, another way evolution in the spatial direction, and the trace be equal. The Bertini et al. In this paper, they imposed the condition, suppose this UR1, the operator, normally, the reshaped operator normally is not a unitary operator, but suppose that unitarity is being imposed, an extra unitarity is being imposed on such a unitary operator. So let us take a unitary operator whose realignment is also unitary, and they defined as a dual unitary operator, and they show that it is possible to characterize the correlation function exactly. That's what the result of Berkeley. So they define the dual unitary operator, that the unitary operator which remains unitary after realignment. So what is realignment? Realignment is the matrix reshaping, basically. So for example, we all heard about partial transpose. The partial transpose is very familiar in quantum information community. So partial transpose is one type of matrix reshaping. So realignment is another matrix reshaping. In fact, in the entanglement detection, this is also being used in the initial days. So, for example, what happens, how it looks in the matrix, suppose this is a unitary operator and these are the blocks, and you are reshaped matrix, looks just each block will become a column. Okay, so if we impose this matrix, that's realigned matrix, reshaped matrix, realigned matrix, also unitary, then diagrammatically what it becomes is represented in equation 6. For example, you see the unitary operator. So this is what the diagrammatic representation of the unitary operator. Whereas if we assume that even the reshaped one remains unitary, then this is the structure which it takes. So what are we interested? We are interested. Let's assume there is an operator at the spatiotemporal point in the lattice, and then we evolve with some unitary operator, which I've already described, and there is another operator. Let's assume the operator which is having a Pauli structure. So for this operator, we need to calculate. We need to calculate the correlation function. So, which is this diagram is essentially the correlation function. And remember that here in every edge is connected. Means every edge is connected. That means we have taken the trace. So that essentially every edge is connected. Mere unitarity of the operator produces this type of structure. So here is the operator, and this forms a light cone. This is called the light cone. And now by assuming, imposing the duality structure, that this structure, what happens for any operator which is lying inside the light cone. So this is the light cone. So any operator lying inside the light cone, you can simply see that the correlation vanishes. So the correlation of any between any two spatiotemporal operators vanishes inside the light cone. So then what happens, the correlations on the light cone reduces in a very simple way, and which is merely the power of a completely positive map. It means it reduces to a function of CPTP map, and the many body property reduces to a function of just a unitary operator acting on two particles. That's what it reduces to. And these are remember here we are tracing it over the system. So these are also called as complementary channels, whereas in the usual channels you will trace over the environment, but here you are tracing over the system, so it's called complementary channels. Okay, so the superoperator representation of these channels is nicely given, and the dynamical characteristic of or what in the classical ergodic system, there is an ergodic hierarchy which starts from ergodic, weak mixing, Cologro, Bernoulli. And let me say that because in the last track there was a lot of mixing with that. So here mixing means I am also going to use the mixing more frequently. So the mixing here is that the correlation decays exponentially. So it comes from the classical chaos. So and the Bernoulli is the highest, which is as random as very high random in the chaotic system. So these people, Bertini et al., were able to characterize from non-interacting to mixing, and the characteristic merely depends upon the eigenvalue of the superoperator. Okay, after that, there were many people started to look into calculating other functions also in the dual unitary circuits. For example, OTOCC has been calculated from a spectral form factor, dynamics, computational complexity, and many other things. And also, Fuzzy et al. Have shown that computational complexity, these dual circuits has computationally supreme compared to classical quantum computation. Okay, so now this brings me to the what is so special about these dual unitary operators. So if I look it from the quantum information perspective, that brings me to let us consider the unitary operator and its Schema decomposition, and define the operator entanglement of which Zanardi did in 2000 itself. So defining some kind of entanglement of the operator, how entangled is, and it can be defined as explained in the equation 19, where gammas are the Schmidt values, and the Schmidt values are singular values of the realigned operator. And note that this is maximum if and only if UR1 is also a unitary operator. That means what in the Mayborn literature they were calling the unitary operator are nothing but these are the operator which is having the maximal operator entanglement. At this point, I would like to stress that we all know that maximally entangled state is very familiar, and it is mathematically also it is very simple to construct. For example, if it is a state, we just implies that we will just write the gammas are equals to 1, and it will become the maximally entangled state. But in the dual unitary operator, constructing the maximally entangled operator is very difficult, and we don't have any complete characterization for example, dimension greater than 2. Only for 2 qubit case, the complete characterization dual unitary is done, but not for the higher operator. But when the Bertini proposed this model, we did not even had many models which is dual operators. Means how we didn't know how to construct the dual unitary operators itself. Okay, so let's come to what happens in the on the light cone. So this is the operator representation of the light cone, and we imposed a further structure. So what is the further structure? We defined what is called T duality. So we defined something called T duality because we imposed the structure that let us assume that partial transpose is also unitary. So diagrammatically, if I assume the partial transpose is also unitary, this is what it reduces to. And if we go back, correlation vanishes even on the light cone, and that produces what is I'm going to tell that. So, but before that, what is this T-duality corresponds to in quantum information theory? So this corresponds to what is called the operator entanglement of US, where S is the swap operator. So ultimate connection emerges from defining the entangling power. So let's define the entangling power. Entangling power is an average entanglement produced by an unitary operator acting on the pure product states, which is chosen randomly in some R measure or some measure. Which has a nice form in terms of operator entanglement and operator entanglement of US. And this is maximum if and only if both EU and EUS is maximum. That means an unitary operator is having maximal entangling power if and only if it's both realignment as well as the partial transpose remains unitary. So those systems for any unitary operator or whose realignment as well as the partial transpose is unitary is called the two unitary operators. And we prove that all eigenvalues vanishes, and which gives rise to the Bernoulli systems if and only if the unitary operator acting on the two particle is two unitary operators. What is its information theoretically? So information theoretically, these two unitary operators, or if we take the state operator isomorphism, is nothing but the four-parted Ame state, absolutely maximally entangled state. It gives rise to Ame states. And we know that now, except for qubit dimension 2, for all equal dimension, Ame states exist, including the four-parted dimension 6. It was open question, but recently Arul, Carol, and they have filled that gap. I think Carol is going to speak more about that. Further, sorry, just a minute. Okay. Further, Professor, how much time I have? Sorry. Can I?
You have about 5 minutes.
Okay, thank you.
Sure.
Further, it's not just the Bernoulli. In many other aspects, how the entangling power is influenced. That's also been investigated, and we were able to provide a sufficient condition for mixing. Here, the mixing, as I already said, that correlation decays exponentially. So, for example, whenever this EP star, whenever the entanglement of entangling power is greater than EP star, which is just the quantity depends upon the dimension of the local system, then it is guaranteed, the periodic system is guaranteed to be mixing. And also how many modes under what entangling power, how many modes the operator, how the correlations are decaying, and how many modes it will be decaying also is calculated, and gives a nice steps. And comprising all these things, what we can write as a kind of phase diagram. For qubits, we don't have four-partite Ame state for qubits, so there are no Bernoullis for the qubits. So only Bernoulli systems or Ame states exist only for q greater than 2. And whenever entangling power is greater than this EP star, it is guaranteed that the system is mixing. And also furthermore that we considered the average single particle average spectral radius, and it turns out to be a function of 1 minus EP, where EP is entangling power, and this FQ is some fudge factor which we could not analytically exactly calculate. Okay. Then the question is how to construct. Of course, there was a method to construction using the permutation operators, which is Sivashish and others. So what we were looking is for that is there how to construct only the dual unitary operators. The one of the and study its dynamical characteristics. One of the construction is using the block diagonal operators. Let's consider the block diagonal operators and use the swap operator, and we show that this forms the dual unitary operators. And only issue is that its entanglement is always less than or equals to EP star. They by themselves may not be in the mixing, but you can use the local unitary operators to make it mixing, but that's a different story. And an explicit channels. So what is the nature of these channels? Channels which we obtain is also be calculated for this type of unitary operators. And okay, and then we were able to construct the exact analytical model motivated from classical cat map. It is an Hadamard matrix, so this is the, and we show that this 27, that is a unitary operator, operator elements is given, is dual for all even for all dimension. Actually, sorry, not just all even q. It is for all dimension. There is an error in that. So and it remains two unitary for all odd dimensions. So it is dual for all dimensions, and it remains two unitary for all odd dimensions. So this is the one first explicit model which we have constructed, and of course, and we calculated for even dimension what is its entangling power and what is the structure of dynamics and everything. And one more method which we actually provided in this reference is a numerical algorithm which is on the space of unitary operators, which will be enables us to construct a dual unitary operator. So this algorithm is of two parts. One is let's consider a unitary operator. Just draw it in a random way and consider its real element and take its closest unitary operator. So this second part is what we call taking closest unitary operator, and the closest unitary operator is given by the polar part of the polar decomposition. So the complete map runs is to take a unitary operator and realign it and take its closest unitary operator. And continuous iteration, we show that it leads to dual unitary operator, both numerically and analytically. And what happens? We also show that analytically that let's define the Salis entropy like this of an operator u, and we show that the Salis entropy monotonically increases under the influence of this map. Also, if we, for example, these are the distributions of entangling power distribution of the dual unitary operators produced through that map, the numerically produced through that map, and you can see that this is the average entanglement, and this is the EP star. That means after which the system is guaranteed to have the mixing behavior. So we can we want to show that there are quite a huge amount of dual unitary operators can be produced from this this map, whose entangling power is significantly high, so guarantees the mixing and other properties in a significant way. So yeah, this is how the construction is. There are various other constructions which we have recently come up using the combinatorial designs and some other structures, but I'm going to stop here. Thank you. Thank you very much. Hello.
Thank you very much. It's an excellent presentation of and that too within time. So I really thank you for that. There is immediately a question on the chat box, and this time I would request Ajit Iqbal Singh to come online and ask the question because he has not been able to do that.
No, I can see that. I have opened it, and it is a very valid question. Madam, it is correct that what we call the T dual is nothing but the biunitary operator. We only recently come to know that. We were not aware, but Sundar has wrote this in around 1996, even before Vicari, Reuters, and Musto. Yeah, exactly. Sundar, Kodialam, and Shruti. I am discussing with Shruti and Kodialam to make it in more rigorous way, but in the community, people were not aware of it. Very recently, we come to know that. So yeah, I'm just recently come to realize that they used to call it as biunitary. And there is a one different, what the biunitary is only T1. That means block transposed. Only the block transposed is what they call the biunitary. But here even the T2 is, but it is necessarily same. I agree with that. Yeah, that's the answer. I hope that that's answered, Professor Ajit Iqbal.
As far as I can tell, at least on chat box, there are no other questions. Does anybody else have a very quick question to Arvind?
Yeah, Arvind, I have just a quick question.
Yes, yes, Pani.
Yeah. So this operator entanglement, you haven't properly defined. Give the expression. Is it very? When you say this operator entanglement, how to calculate it? Means what does that mean actually? Physically.
Yeah, see, this physical meaning of this one is at around 2000 when they defined itself is in one way people have tried to understand it, but the other way is I'll just come up in the four-part.
You come up with some expression, no?
Yeah, that expression. Yes. But in the four-party case, it is easy to understand. Let us consider this is the four-party scenario. I am writing it in this way. It's any four-party state. What happens if you take this unitary operator? Just imagine it is acting on A and B, and A prime is maximally entangled, and B prime is maximally. This cut, that is A prime versus B prime B, is guaranteed to be maximally entangled because of unitarity of U. Whereas, sorry, that is guaranteed. That maximally entangledness comes because of the dual. If the unitary operator, its realignment remains unitary, then only this cut remains maximally entangled in the state version. This is one way, but there is another ways also. But for example, how much entanglement sharing is needed in order to implement this unitary operator? For example, swap is also dual unitary operator.
Okay.
So some confusion is still there in the community. It still needs to be explored. What is its physical meaning?
Swap also is dual unitary. No?
Swap is also dual unitary. Yes.
Okay. Thank you. It's really a nice talk.
Thank you. Thank you. I think we're also.
Aravinda?
Sir. Oh, okay.
Yeah. So can you go to these plots where you plotted this entangling power? The end.
This one, right?
No, later. There was this. No. After that, there was this graphs, right? This in the end.
Yeah, this one.
Yes. So I just want to know. So this is on your horizontal axis. These are entangling power of unitaries, right?
Yeah. Horizontal entangling power. Yes.
Yeah. So I just want to know the peak one. For example, in Q equal to 3 case. Okay, this peak one. What sort of unitaries they correspond to? Do you have any idea?
Peak one means this peak of the.
Yes. Entangling power. Yes.
No, maximum entangling power or just the peak one.
Just the peak one here. Yeah.
Just the peak one. Peak one I don't know, and we are not interested.
No, because why I'm asking, because in our work we have used only, of course, these permutations, right?
Yes.
There we have used permutations to come up with the maximum entangling power there. Of course, that is only restricted to permutations. So,
but here, I think what you are asking is the one which is coming close to one. That because that is what the one which is having maximum entangling power. Okay.
Yes.
That is a few structure is enabled, and we know in fact there were some exact forms also available, which I could not present in this talk. In fact, what this open question was there, which Carol is going to speak, four-party dimension 6 question in the quantum scenario, 36 officers case, that in the beginning a numerical solution is obtained by modifying this algorithm. Okay, so in this algorithm, whatever this algorithm we have given in this work, so proper modification of this algorithm, Suhail did some modifications, the group did some modification to obtain numerical solution, and later they converted it into some nice looking forms. So
I see. Okay. But it is not definitely permutation, right?
No, definitely not permutation. Yeah. And only one thing is that which we are going to conjecture in our, we have some conjectures that for qubit q equals to 3, all the operators which is having maximal entangling power is locally unitarily equivalent to permutation. Whereas for q equals to 4, we ourselves have found out one unitary operator which is not locally equivalent to permutation operator, which forms the exact quantum designs.
Okay.
But for 3, we could not find out, and we in the literature nobody has found out anything which is not local unitarily equivalent to permutation operator.
Oh, I see. Yeah. Okay. Thank you.
Thank you.
Okay, Arvind, thank you for the nice discussion with Shivashi's at the end. I think we have finished everything a little bit late, but I think good enough within time. Thanks all the speakers in this session for maintaining time and having a wonderful discussion. I'll give it back now to to Archan.
Thanks, Devu, for conducting this session very smoothly. We have finished on time. And so we are now about 25 minutes away from the next session. So please come back at 16:20. Nice. Thank you.
Okay, thank you. Bye.
For a full screen at Adobe.
No, I don't know. Unfortunately, I'm using Mac.
Perhaps this is the thing. Okay, I hope. Oh, that's strange. Okay, Control L. Okay, that's easy. Very good. I'll share the screen. Okay, I hope that I'm sharing it now. Yes?
Yes, you are.
Okay.
Fantastic. So since you have two parts in this talk, I think let's start now. Looks it might take a while. So our first speaker is my own scientific father, and it's a great pleasure to introduce Professor Marek Lqcc from University of Gdańsk. He is the director of International Center for Theory of Quantum Technologies here, and probably he will tell you a few words about the center itself. And today he has two topics. That's why I think we should start promptly. He will revisit wave-particle complementarity of a single photon and Figner's-Friends paradox. Thank you. Please proceed, man.
Many thanks, my scientific son, and for the nice introduction. I'm very happy to be back in India, virtually, unfortunately. I'm 3 times vaccinated, so don't worry. Let's say the only viruses that you can get are computer viruses from me. Okay, so I'm very happy to be at this conference and to see so many friends. I'm very sorry that I did not attend to many lectures because this is just a normal week of work, and this was a busy week of work. And the funny thing is that this session, let's say until the very end, is only my friends. I have a paper with every speaker, who speaks after me, and so this Tomek invited me to say a word about International Center for Theory of Quantum Technology. So we were established relatively recently in 2018, thanks to European money channeled by the Foundations for Polish Science, FNP, and this is a super great non-government organization, an independent foundation, and we have won kind of competition for the money for creating a center. And we have very many people from India working in the centers, which may be an interesting information for the organizers. And we thank for them because, let's say, like everybody in the center, they are fantastic. Okay, so let me go to this subject. So I want to talk about two things that kind of were consuming me and my group in recent times, and this is things related with interference experiments with single photons, which supposedly give some versions of Bell's theorem, and the other thing is the problem of extended Wigner's friends, and this is very much related to Howard Weizmann's talk, which was in the first day of the conference, and unfortunately I heard only the second half because it was a little bit too early for me. I overslept. So let's say the abstract you can find in the abstract book of the conference, so I will be not reading it. So let me go to part 1, which is wave particle complementarity, detecting violation of local realism with photon number resolving weak homodynamic measurements. And this is my team with whom I worked, and all of them are from our center. Our center is big enough to find, let's say, a group of talents which can work on a specific problem. Okay, so we got interested somehow in a quite, let's say, as a matter of fact, I was interested for years in the Tan-Walls-Collette paper of 1991, in which they claimed that, and here I put a lot of inverted commas because I hate this term, that they discovered non-locality, this is the term that I hate, of a single photon. And they suggested the following Gedanken experiment. In 1991, it was a Gedanken experiment. So I hope that you see my cursor, which was in a form of a hand. Do you see, Tomek?
Yes.
Okay, very good. So the idea of this experiment is that we have just one photon in beam S. Okay, in beam S is one photon, in beam T is nothing, vacuum, and then we have a 50-50 beam splitter, and so the photon comes out in a superposition of being in B1 with B2, or if you like, the modes B1 and B2 share a single photon excitation. From the point of view of quantum optics, it is that the modes share a single photon. Okay, and then this superposition, let's say, arrives at two measurement stations, of course, for Alice and for Bob. And it is well known that if Alice and Bob just measure something, they won't get anything. Okay, it just aim at detecting the photons. So there must be something added to have a interferometric effect, because otherwise it is just anti-bunching, if I can say it, in a lot of inverted commas experiment. Okay, and the idea of Tan-Walls and Collette was a typical idea of quantum optics people. Why don't we try a homodyne measurement? Okay, so here comes and what I stress already in this experiment, it was let's say in this Gedanken experiment, it was tacitly assumed that this is a weak homodyne measurement. So this alpha is here is a coherent state of the local oscillator. Okay, and here comes the local oscillator for Alice, and here is a 50-50 beam splitter, and they were observing the counts. Really, they were observing the intensity, but now we are in a situation in which we even observe photon number resolved counts in the detectors. We are, let's say, almost 1/3 of a century later now, and they showed that there is a Bell inequality which is violated and by those homodyne measurements, and therefore hooray, as they claimed, there is a non-locality of a single photon and everybody is happy. Okay, what I want to say that 3 years earlier there was a similar, not that similar, but a related paper by Grangier, Potasek, and Yerke, 1988, in which instead of having here a single photon and a 50-50 beam splitter, they were using down conversion radiation. Okay, so just into this B2 was fed this output of a down conversion, and into B1 was fed this output, and then it's just 2-mode down conversion. Okay, and then the system of measurement was exactly the same, and they also claimed that we can violate Bell's theorem and so on. Okay, but unfortunately this is not true, because the Bell inequalities on which both papers were based were inequalities from a paper by Reed and Walsh in 86, and those inequalities they are not Bell inequalities because they contain additional assumptions. So Bell's inequalities are Bell's inequalities when the only assumption is local realism, randomness, independent randomness of the local measurement settings, and what else? Let's say, so we have the independence of the settings, we have local realism, that's everything. And local realism is of course a compound notion of first realism, and then that this realism has a local nature in agreement with Einstein's causality. Okay, and of course we usually assume that this independence of the settings and randomness of the settings is a kind of obvious assumption. So we really test localism and realism. Okay. And what is very important, that those experiments were Gedanken experiments at the time when they were announced, but they are lovely, fantastic achievements of the 21st century, and I think the group that really pioneered in those techniques. And what is very important for my talk, they actually did those experiments. Okay, they just did it. Okay, this was the group of Walmsley, and there are 2 papers in 2014 and 2020, and they used photon number resolving transition edge sensors, which are superconducting and so on. So it's a fantastic technology. And they have let's say, very good photon number realization. So those experiments are now possible. And so this is additional motivation aspect, except for the fact that we were doubtful that really there were violations of local realism in the experiment. And so you may ask, I said, well, I was criticizing the inequality, that it was had additional assumption. But well, so you now expect that I will show you the inequality. What is the additional assumption that it shouldn't be there? No. I will show you the final end of any claim that this Tan-Walsh Collette experiment is an experiment which reveals violation of local realism. And why? Because of that. I hope that I will go down. Okay. And also, let's say, just to tell you something about urgency of this question. So the question is already urgent because we can do it. And therefore, sooner or later, and quite a lot of people are claiming if there are non-classical effects that involve a single photon, then it's definitely much easier technique than those that involve two or more photons, and therefore a lot of people will be kind of tempted to try them in some quantum information protocols. Okay? So that's the motivation why we started to work on it. But also, then when we looked at the literature, and we were a little bit horrified after we already knew that the original interpretation of the experiment is wrong, that those experiments ended up in textbooks. So, for example, in Milber and Walls, 2007, on page 264, we have the following statement: some of the most striking features of non-locality of quantum mechanics may be demonstrated using phase-sensitive measurements on field produced via single photon. These effects may not be explained classically using a particle, wave, or hidden variable theory involving local causality. Okay, so just look that if students who are taught according to this book, if they fail to repeat this statement, they get a low grade at their examination. Okay, because it contradicts a very famous book of so the situation gets a little bit more dangerous if you realize that the claim is weakly, let's say doubtful. Of course, if one shows that a Bell inequality is not violated, or the Bell inequality is not Bell inequality, still you don't have a proof that there is no Bell's theorem. But I will show you, let's say, the decisive proof. And then there is a book which is in Springer, and Springer, say that's wow, very highly, let's say, regarded scientific publishing house. They own Nature now, okay? And there is a book, the story of light science from early theories to today's extraordinary applications. And a version of the Tan-Walls experiment is there, okay? And it is based on a paper in a New Journal of Physics, not of this author, of other authors, but as we highly criticize it in this archive. By the way, it has been accepted for publication early this week. Let's say, so as you see, it's very deeply into kind of common knowledge in quantum optics that this is here we can have very nice experiments. So let us look at the theory. So it's very easy to calculate the probabilities, because the initial state in those two beams B1 and B2. Okay, I hope that I will. Okay, so here, okay, it's of course the superposition of photon beams in the second beam and in the first beam. Okay, and there is unnecessary I, but my younger colleagues they love this I. Okay, it can be removed by any phase, so don't worry. And then the quantum predictions for having, let's say, in detector C, just look that the detectors D, and it's a nice accidental conditions, are those, let's say, straight ahead, and C are kind of, they are playing, as you will see, much less prominent role. So B are straight ahead, beyond the beam splitter, and C are reflected from the point of view of this single photon. Okay, they observe the reflected beam. Okay, and then you can calculate the prediction. Is a very easy calculation, and so that's for K photon in C, L photon in D of Alice, and then R photon at C, and S photon in D of Bob. And then just look, you see, and of course you, let's say, as you'd expect, there is a different in phases. So we, oh wow, no locality, blah blah blah, and so on. So it sounds great, and one immediately thinks about Bell's theorem, because it's a sinus of the difference of two very far away phases. Okay, and of course I have to stress that the local oscillators have to be phase locked, so it is not so that they can be independent. So there is really a definite difference in the phases of the local oscillators, and the phases are defined by the local oscillators. Of course, alternatively, they could have been defined by some phase shift on the single photon. Okay, and just look, there is an interesting thing that if k equals to L, that means that at Licc you have equal number of photons in the detectors, there's no interference. Okay, and the same, of course, symmetrically for Bob. And this is a very important thing for us. Okay, and then let's say after, when you look for something like a week at those formulas, suddenly you have an idea that there might be a local realistic model, overt, precise local realistic model of those effects. Okay. And the thing is that, just look, so as you see, there are some sets of events in which there is this sinus, and we can call them, let's say, interference events, and there are some sets of events for which there are no, there is no sinus, so they are flat, no matter what are the settings, and then you have a lot of possible photon numbers, okay, related with those probabilities. And it turns out that you can build a local realistic model for fixed values of k and L. Whenever they are equal, and Rs, they are trivial because there is no dependence on the local phase. They are just local realistic model is just the probability of such an event to happen according to quantum mechanics. Okay, for this. But when we have an interference, then everything that is flat in terms of this difference of the phases is covered by trivial local hidden variable models. But when there is a dependence, we adapt a model by Jan-Åke Larsson, or Larsson as people mispronounce him, which was first outed in my paper with Jan-Åke and Holkjat and Ertz in 1999, and in a different context. And Jan-Åke invented a very trivial model of which is precise local realistic model, which emulates quantum predictions for 2-qubit singlet, however, at the price of detection efficiency to be lower than 2 over pi. Okay, and we simply we build such Larsson models for certain subsets of events. Okay, and so let me go to the Larsson model. So let's say it's asymmetric, and okay, and let us assume that it's Alice, okay, and she has not a 100% visibility. No. Sorry, not even 2 over pi quantum efficiency at her. Okay, and so every qubit carries such a map that lens at her. Every qubit carries such a map in which there is a region for having result -1, a region for having a result +1, and 0, that means no count. And Bob's qubits get only counts plus or -1, and they are not sinusoidal anymore. They are simply such territories in which only one can happen, and then just imagine this plus situation. And locally, in the case of Bob, the map is shifted. Map also gets the concrete value of the hidden variable. Okay, map is shifted by θ2, and at the Alice's side, map is shifted by θ1. And then, if you overlap those two graphs, then you see that there is an overlap, okay, of plus results, plus for Alice and plus for Bob, which has an area, overall area, which is proportional to the sinus. Okay, because just look that the integral from here is a certain value of the sinus of the difference of the theta's. Okay, and that's the lovely idea of Janoka. And we simply apply those models not to 1 and minus 1 and 1 events, but into K and L events, which are different. And instead of, and here in this region of no detection, we still assume total no detection and bobs. No, total no detection. And then, of course, you symmetrize the models because they are totally asymmetric. Okay, so each such Larson-like model predicts events which are of that form plus swaps of because everything is let's say must be symmetric, and so we build the whole family of such models, and it turns out that they make sense as long as the local oscillator strength is below 0.87. And why it is so? Because we need those 0,0 events. If alpha is beyond that we have too little of those 0,0 events. Why? Because alpha gives more photons, and so that there are less vacuum events. Okay, in the detectors. Okay, but what is lovely? Okay, we cover a whole region predicted by Tan-Walls-Colette for violation. So the problem is gone. Okay, and what perhaps I will tell you that if you work very hard, and it's still open how much you can squeeze out from this technology, you can increase this number. If somebody wants to make a master's degree or something, let's say, it's something like 2 months work, and that, we know that you can increase this, but not too much. And so let's say, and so this is our negative input to the subject, but let us go to the positive input to the subject. So we use Clauser-Hahn inequality, but straight ahead Clauser-Hahn inequality. No, without any of those assumptions that are in Widwall's paper, just straight ahead. And as events A, we take 1 photon detected and at the straight ahead detector, okay, and 1 in the reflection beam, and 0 photons in the reflection beam, okay. And A prime means that there is beam splitter in, and the beam splitters are now not 50-50. So the optimal reflectivity will be calculated, okay. So they are not 50-50, and the local oscillator is on. Okay, and the prime events are identical in terms of detection: 1 photon in detector 1 and 0 photons in detector which observes reflection at the homodyne device. Okay, but there is no beam splitter and no local oscillator. So it is just observation of the photon. Okay. Which is and of course similar events for Bob, and then we can show the violation of localism. This is those ideas of observing such events are already in the Hardy's paper of 1994, but let's say he used them in order to show that you can use his famous paradox to show violation of local realism. And what I will tell you later, there is also one more asterisk concerning that. But in our research, we just confirmed that it's the optimal. And concerning optimality, there is a fantastic thing, and I challenge anyone to understand it. that there is an optimality condition. Alpha squared, the power of the local oscillator in the on setting, must be equal to the reflectivity of the beam splitter. This is necessary condition for optimal settings. We don't understand it, but it's lovely. And it also goes into other experiments. And so Tan walls call it original. And what is very important, R cannot be 50%. So 50-50 beam splitters are completely excluded. And which is covered by our model, but our model does not pertain to this situation when we have off settings. But even in this on-off settings, you can't get anything if you have 50-50 beam splitters, which we tested. Okay, we made a numerical scan for optimality. And what is very interesting that this experiment of Grangieri, Potasek, and Yerki, we have shown that the claim that there is a violation of local realism when one uses 50-50 beam splitters and constant local oscillator strength is unfounded. And what is then we moved, of course, into on-off situations and not 50-50 beam splitters. And then it turns out that under such a situation, there is a violation of local realism in the Grangier-Potasek-Yerki experiment. Okay, we do not have full model. We spent something like, I don't know, 3 weeks thinking how to build the model, but we failed. But at least for the simplest parts of simplest family of counts, we have an exact precise model. Okay, and let me come back to 1994 paper by Lucien, who will be at the end of our session. Okay, he considered a little bit more, let's say, broad situation in which we do not have one photon, but we have a superposition of a vacuum and one photon hitting the entry beam splitter. So in the exit of the beam splitter, we have the following state. Okay, so this condition that we were discussing earlier was P equal to 1. Okay, and it turns out that using not Hardy paradox but straight ahead Clauser-Horn inequality, you can have strong violations up to P equal to 1. So up to this, but at P equal 1, there is no violation. But wait a second. But what is very important in case of Hardy paradox, when we are approaching P and already you are quite far away, then basically there is no violation. It's 1 millionth or something like that. Okay, but surprise, surprise. As you know, Clauser-Horn inequality has two sides, right-hand side and left-hand side. Okay, so we call it max side and min side. Okay, and it turns out that let's say the right-hand side violation go to 0, and they are 0 at P equal to 1, so exactly 1 photon, but left-hand side, as you see, grow. So this is the first showing that there is really a violation of local realism at P equal to 1, that is at the call it case. And so the idea of Hardy to have those detections is great, but let's say what is very important in case of Hardy's paradox here, let's say the readouts will be basically flat at the border between realism and, let's say, infinitesimally above into the non-realistic case. But okay, so as you see, now the situation, we hope that is clear. All those results were published in a series of papers, or are being published rather, One is published and two were accepted in this week in New Journal of Physics. So let me move now into the second topic, which is related with one of the first lectures of the lectures. This is Physics and Metaphysics of Wigner Friends. And subtitle is Even Performed Pre-Measurements Have No Results. And this is in collaboration with Marcin Markiewicz. And this is published, fortunately not on April the 1st of 2021 in Physical Review Letters. And the motto that we use in this paper is the statement by Bohr, the unambiguous account of proper quantum phenomena must in principle include a description of all relevant features of experimental arrangement. And Bohr was always stressing that the element, let's say, a very relevant feature of measurement is that it is done by macroscopic device. Okay, so, and the motivation was a series of paper. The first, let's say, the problem of Wigner's friends was reintroduced by Frauhinger and Renner in a paper that, let's say, then there was, let's say, a no-go theorem for observing independent facts by Czaslaw Bruckner. Then there was an experiment with, let's say, according to me, very misleading title of the publication, Experimental Test of Local Observer Independence. There was nothing about results, measurement. Okay, so. And it's also related to Howard Wiseman and others paper. And I must tell you that the paper with which I agree most, and let's say is the last one, because it's a no-go theorem for Wigner's friends, and the thing is that what we did, let's say this paper is very much in the spirit of Bell's theorem, and we want to go out of it. So our friends will be, there will be nothing local about our friends. Of course, they will be local. The locality will be irrelevant. Okay, and so let me discuss, let's say, modern look at this motto by Bohr. Okay. So a lot of people, and this is the Einstein, not born by Bohr, the Einstein-Bohr debate, they saw tension between unitary evolution and measurement. Okay. I must confess, I don't see the tension. If you see, okay, you suffer. And of course, there was a 1930 solution which says that a measure made by von Neumann and then Lüders in 1951, he made it a little bit more precise, is that measurement implies the state update, okay? And state, the way I understand the state is the knowledge about the system. It's never state of the system, but this is one of the misnomers that we use in quantum physics. Okay, but and later, let's say people try to understand this, and surprise, the leader in that, according to me, perhaps my knowledge of history of physics is not good enough. But if you look into this book about quantum mechanics, written by Bohm himself, but 1 year before Bohm became a Bohmian, there is a fantastic, most beautiful description of the theory of decoherence, of the role of decoherence in quantum measurement. And this line of thought was perfected by Jurek in 1980s, and he's famous for making all that very, very precise and a lot of very important theorems about the role of environment in quantum measurement. And I have to stress that Fritz Haacke, who I was a postdoc of him for a short while. Also contributed very important works into that, and I had the pleasure to be a co-author of one of them. They started the first work was with the walls, the same walls that I mentioned in 1987, and I have no time to dwell on that, but they are very important. They have a little bit different look than Jurek's. And I dedicated this part of my talk, and also my physical regulators is dedicated to Fritz Hacker, who passed away in 1919. Okay, and so what is very important, I will be doing analysis which is interpretation neutral or minimal. That means that quantum state is a theoretical specific description by density operators of statistical ensemble of equivalently prepared systems. So we do not, this is something that I share with Bohmians and whoever, okay, whoever works in quantum mechanics. So this is a minimal interpretation. If you don't agree with this interpretation, then you cannot make predictions in quantum mechanics. Okay. And I have to warn you about the. I hope that I have still something like 6 minutes. Tomek, will you allow me?
Yes, definitely. You have actually 7.
I have to also warn you that Wigner's friends are not those Wigner's friends which were discussed in those 4 papers, because Wigner's friend was an idea such that, let's say, a friend makes an experiment in a sealed laboratory, and therefore Wigner, before opens this laboratory, thinks that a friend is in a superposition of seeing result plus, and the system is in the result plus state, and seeing result minus, and system is in the result minus. And then Wigner opens this and sees that only one thing is the case. Okay. So that's the Wigner's description. But Deutsch made a let's say a modification in 1985, and this is Wigner performs a measurement on Friend's lab in a basis which is complementary to Friend's basis, and that's the source of trouble in all that. And so this is really, they are not Wigner's friends. Okay? And in the first paper of Frauhinger and Renner, which was the source of all that activity, one thing is undefined, and this is a little bit related with my question, which I asked to Howard at the end of his talk. So in there, they had undefined status of measurements by Friend, because in quantum measurement theory developed by those persons whom I mentioned, let's say we have either we can have either proper irreversible quantum measurement, and then there is the coherence involved, or we can have reversible pre-measurement, which is in principle reversible. Just look at the following. Let's take let's say polarizing beam splitter. So pre-measurement is correlating. I said polarizing beam splitter, so there are 2 beams coming out. So if we have a photon of a certain polarization, if after the beam splitter, the polarization starts to be correlated with the exit of the polarizing beam splitter. And so this is the pre-measurement. And the final measurement is that we take a very huge detector, which is a macroscopic device for which we pay $100,000, and it clicks. Oh, and so that's measured. Okay. And okay. And so we want to show an inconsistency of the Deutsch-friend concept. And as I have less and less time, I invite you to read our paper. We try it to be as user-friendly as possible. So in step 1, we show that if we use the standard measurement theory, let's say that simply Deutsch-friend is impossible. Okay, so let's say this concept doesn't work, and this means that in the case of those 4 papers that are mentioned at the very beginning, those effects that are studied do not exist. Those correlations do not exist. Okay, now. So standard measurement theory with decoherence does not allow Deutsch friends and this Deutsch scenario to show anything interesting. Everything decoherence and there's nothing interesting. Okay. Now in step 2 we give this concept of for the Deutsch friend a second chance. We assume that there is no decoherence in friend's lab. And friend has a hallucination of an outcome. Okay, I call it a hallucination because in the pre-measurement there can't be an outcome. It's only a correlation. Okay, so I call it hallucination. Okay, but then because Wigner makes his measurement in a complementary basis, it's kind of extended complementary basis, which takes to account. Also friend. This hallucination is counterfactual because it's erased. But if had Wigner used a measurement basis which agrees with the measurement basis of friend, he would have received the same result. So this result has a counterfactual nature. It would have occurred had situation been different. That was actually okay, and that's the pure definition of counterfactual. And then there's we give a third chance for Wigner's friends. Consider that they are counterfactual outcomes. Okay, so. There is a pre-measurement, but still, let us assume that Wigner's friends have some hallucination. Okay, okay. Let me skip this. And I will show you why it is impossible. Okay, so I assume that the virtual friends somehow see outcomes, even in a transitory manner. Okay. And we showed and of course friends make only measurements because if they decohere, then there is nothing interesting. Okay? And we use something which always amplifies things that are strange in quantum mechanics. We use not let's say Bell-like situation or two-particle situation, but three-particle situation. So let us assume that here are 3 labs shared each time by friend who is sealed within the lab, and then there is out in the lab, within a kind of sealed zone of the lab, and then there is a Wigner, okay? And so there are 3 identical labs, and we send a GHZ state to those labs, okay? We don't care about any distances between the labs. And this is, of course, obviously the GHZ states, and that's the basis number 1, okay, of the qubits. Okay. Now, virtual friends make pre-measurement in a fixed basis, and what is very important, this is not this basis that this is here. It's a complementary basis to this one. And then Super Wigner measure the joint system of S and F, okay, the system and friend in each of the local labs in a fixed, and again fixed, effectively complementary basis. And so. Just look, I recall you we have fixed this basis 0, 1 with the subscript 1, but here I have 2 complementary bases, okay? two different complementary, they are fully complementary bases. I think this is okay. So, and of course, we ascribe outcomes plus minus 1 to those. And just look, the friends pre-measure in basis tree, this one. And they have some initial state, and they correlate themselves with the state. Okay, but the super Wigners measure the system of friend correlated with the with this system, super system of friend, but in a basis L2, which is this one, which is effectively complementary. And I will explain to you. Just look. This is the L3 in which was measuring friend, but there is a transformation matrix. Just it does not have any subscript because it is just straight ahead qubit transformation matrix to another basis. And then it's very easy to see that if we expand GHZ states in basis 3, okay, and just for the systems, then it has some components. Okay, some amplitudes. But if we assume this trivial, no, I don't have to, this trivial interaction of the friends with the system, then after interaction of friends with the systems, it turns into something like that. And it's identical in the form. Okay, so just look that those amplitudes and those amplitudes are just for qubits. So probabilities, let's say whether they are, the probabilities are simply identical. Okay. So probabilities, if Wigners are making measurements on SM in basis SM, just on the qubits, are, that means without friends, are exactly the same as with friends, if they are allowed to. And so we have, it doesn't matter whether we introduce here friends or Wigners, provided the settings are identical, we have the same situation. And then obviously we go into such a situation that we take arbitrary let's say phase dependent basis, okay, and then we know that the GHZ function, correlation function, looks like that. It's this product of the local results. We take for friends, for Wigners, we take the measurement basis, which is equivalent to no phase shift, and for friends, pi over 2 phases. So we have such correlations, okay, and such relations between them. And then if we introduce actual results by Wigners and the counterfactual results by virtual friends, okay, then they must, if quantum mechanics is okay, they must follow such algebraic equation. And then it's straightforward to see that this is square of the product of the counterfactual results of the friends is -1, and therefore it is imaginary, and that's the end. That's the end of the last chance for.
Thank you very much
for Deutsche Wigner friends. Okay, so I think I have used all my time.
Yes, exactly. So thank you very much. That is indeed the end also of the talk. So thanks, lovely talk. And since we are really tight on time, maybe just a very urgent question, if there is from someone. I don't see. So the link to Marek's and Marcin's paper is on the chat. So please go ahead, and I'm sure this was a great introduction to that. Thanks, Marek, again.
Thank you.
Let's move on. Our second speaker is Professor Arun Kumarpati from HRI. Arun, are you around?
Yeah, I am here. Yes.
Okay, great. Thanks. So could you share your, Marek? Could you stop sharing your slides?
Yeah. I'll try. I'll try to do all that you request.
Thank you.
Did I?
No.
No.
No. You're still sharing.
I'm clicking on zatrzymaj udostępnianie.
Oh,
okay.
That sounds good. Oh yeah, that's it. Thank you very much. So yes, Arun, could you please turn on your slides?
Can you see?
Yes, perfect. Thanks a lot. So our second speaker, as I already mentioned, is Arun Kumar Pati from HRI, well known to everyone. So since we're a bit delayed, please go ahead.
Okay, thank you, Thomas. So can you see my full screen?
Yes, all good.
Okay. So let me thank the organizers for inviting me to this event, and this is going very nicely, very well organized, and very profound and interesting talks are there. So I hope everyone is enjoying. So today I'm going to tell about one of our recent work on quantum speed limit for observables, and this work has been done in collaboration with one of my students, Brij Mohan. So I'm going to tell this today. Okay, so before I go to main result, let me try to motivate a little bit. So quantum physics has several limitations, and these limitations could be due to the structure of quantum mechanics, or it could be due to some operational formalism, or could be due to dynamical limitations. And from dynamical point of view, we know that there is a limit on this evolution speed of a quantum system when the system undergoes unitary evolution. And that essentially arises due to the uncertainty relation that we are all familiar. Like if you use the Robertson uncertainty relation, you can show that the celebrated Mendelssohn term bound actually is a consequence of that. And the bound on the quantum evolution speed of a physical system, typically in the literature, you call it as quantum speed limit. And this QSL sets a lower bound on the evolution time, and this bound entirely depends on the energy fluctuation and the shortest path connecting the initial and final points. So one of the early motivation, in trying to derive this kind of bound was essentially due to the fact that there are several people trying to prove some kind of time energy uncertainty relation, but there are no successful, there is no successful derivation about that. We all know that. So there comes this result by Mendelssohn and Tom in 1945, which is quite old result, and that tried to give some kind of time energy uncertainty relation, and as a consequence, that also sets a bound in the speed limit. So what is this quantum speed limit all about? So when we have a quantum system initially prepared in some state size 0, and it evolves by some unitary evolution to a state at time t, which you denote as psi at t. And this evolution, when it is governed by Schrodinger equation, on the quantum state space, which is typically your projective Hilbert space, the actual path may be some arbitrary path in the state space. And on the state space, you can always connect these two endpoints by a shortest path, which is called geodesic. And from geometrical consideration, it should be clear to all of us that the actual path that the system is taking during evolution is always greater than or equal to the shortest path. And this statement is actually, one can check very easily, is actually a consequence of the Robertson uncertainty relation. So the speed limit that people usually talk about is given this expression that t is greater than this TQSL, which is compactly expressed something like this. So it's not S0 by twice delta H, or this, you take maximum of this. So here you see two different kind of expression. The first expression is due to Mendelssohn and Tom, which was discovered in 1945. And in 1998, Margulis and Levitin, they tried to prove a different bound, which involves average of energy, not just the variance of the Hamiltonian. And that looks like this. So this bound on the time actually determines the minimal dynamical evolution time required for a quantum system to evolve from some initial state to a final state. And if you look at this expression here, so what is S naught? S naught is, as I said, this is the shortest path connecting the initial and final point. And that is essentially, if you take the overlap of psi 0 and psi t, which is also known as Bargman angle in the literature, that is essentially cos of S naught by 2. And that S naught is essentially twice cos inverse of this quantity. And delta H is your familiar variance in the Hamiltonian, or delta square is variance, which is essentially S square average minus H average square. And here you see this epsilon naught, that is essentially ground state of the energy of the quantum system. Okay, so even though the first bound was discovered by Mandelstam and Tom in 1945, it was quite interesting to notice that the notion of speed of a quantum state was not really not really defined till 1990, and this was actually done by Anandan Arnav in this year, and they defined the speed of a quantum system using so-called the notion of Fibonacci metric. And in 1991, I also tried to define a notion of speed of a quantum system using something called norm distance between any two quantum state. And if you use this Fibonacci metric, that is essentially looks like this. So if you consider a quantum state at time t and a state at time t plus dt, then the infinitely small distance between these two nearby states is given by this quantity. So it is essentially up to this scale factor, it is essentially 1 minus fidelity of these two nearby quantum states. And that is essentially your infinitely small distance or infinitely small Fibonacci metric that you can define on the projective Hilbert space. And once you have a defined distance, you can define the speed. The speed of quantum transportation on the projective Hilbert space is essentially ds by dt, and that is simply twice delta h over h bar. So you see, it is not just the Hamiltonian that governs the speed. It is actually the fluctuation or the variance in the Hamiltonian that decides how fast or how slow system is going to evolve. So this is the interesting definition that was given by Anandan and Arnav, and that was quite remarkable paper. And as you can see that if you want to see how much distance this system has actually traveled in the projective Hilbert space, you can do the simple integration, and you can say that yes, the system actually travels total distance, which is essentially the integral of this delta h over dt. Okay, and you do this integration from 0 to t. And as I said, from geometric consideration, if you imagine that this actual distance s is greater than the shortest distance, then you can show that this bound is actually a consequence of this. Okay, and it's not just a heuristic argument, it is actually a rigorous consequence of the familiar Robertson uncertainty relation. Okay, so you may ask the question, given this kind of relation, can you design some Hamiltonian which will drive the system along the shortest geodesic? If you can do that, then you will say yes, you can drive your system along the optimal path. Okay, and this is one of the pressing questions in this area of quantum computing, quantum control, or maybe quantum sensing, and many other directions. People are trying to apply even quantum thermodynamics. People are trying to apply this quantum speed limit and trying to see how best they can control, how best they can drive the system from some initial state to some target state. Okay, so in early days, in 1993, I tried to find a class of Hamiltonian which can drive the system along shortest geodesic. So essentially what was shown in that paper was that if you consider a two-state system and you have some Hamiltonian, and you can impose some condition on the Hamiltonian, and you can show that the total distance traveled by the state during arbitrary time evolution is actually the shortest path connecting the initial and final point. So that gives a very beautiful geometric meaning to probabilities of two-state quantum system. And now if you ask the question, can you measure the speed of quantum evolution? Because this speed is not just the speed of particle in ordinary space, it is the speed of the state, quantum state on the projective Hilbert space, which may look abstract, but is not really abstract quantity. You can actually measure this quantity. So again, one of my old paper in 1997, along with Anandan, we tried to show that if you have this so-called Josephson junction, the zero voltage tunneling supercurrent is actually geometric quantity, and that superconducting current is actually proportional to the speed of the state vector on the projective Hilbert space of the quantum system. And that means by measuring the supercurrent, you can actually measure the speed of quantum evolution. So this is quite interesting result, though many people may not know, but I think this is very interesting result that we found in 1997. Okay, so let me, with a little background, let me come to the central theme of my today's talk, and that is about quantum speed limit for observable. So all these years, if you look at the literature, usually talk about the speed limit of the quantum state. That means you are dealing with Schrodinger picture. And in Schrodinger picture, we know okay, what we have is we have to evolve the observables, and we have the equation of motion, which is Heisenberg equation of motion, and we have to define some kind of speed limit for observable. So in that sense, it is natural to ask how fast an observable evolves in time, and can we derive some kind of speed limit for observables. So with that motivation, we try to do something. And another motivation for studying the observable speed limit is the following, that it can have application in trying to understand operator growth in many-body physics. For example, if you are dealing with many-body physics or complex quantum systems, one of the pressing questions is how to understand the universal operator growth hypothesis. Because if you start with a simple operator in many-body physics, because of the interaction Hamiltonian, the operator can grow exponentially complex. So the complexity growth is really exponential. So how fast that complexity grows in time, maybe this kind of speed limit will give a bound to that. So that is another motivation. So the observable of quantum system tend to grow over time, and they become more and more complex as the system evolves in time. And our speed limit may provide some non-trivial bound in that direction. And what we want to do is we want to put a non-trivial lower bound on how fast the observable evolves in time. And that will define the maximum rate of evolution of the expectation value of the observable of a given quantum state during the dynamical evolution. And when we talk about dynamical evolution, it could be unitary, it could be CP map, or it could be Lindbladian, anything it can be. And it establishes a limit on the minimum evolution time that that is necessary to evolve between different expectation values of the observable of the quantum system. Okay, the first result I try to show here is about the speed limit for unitary dynamics. So we know that in the in Heisenberg picture, we have this equation of motion for the observable O, and H is Hamiltonian, and O depends on time. And using this equation of motion, what you can do is you can try to apply the uncertainty relation, and then you can find that the time the system observable takes to evolve from some initial average value to some final observable value is actually given by this kind of expression. And this right hand side, this quantity we have here, is h bar over twice delta h, this integral, this quantity, we call it TQSL for the observable. And that gives a non-trivial bound for the speed limit of the physical quantity. And to see some interesting connection, so you can imagine that your observable is not just a arbitrary observable, but could be some kind of, for example, if it is dealing with qubit system, you can have define your observable to be something like n dot sigma, and that will satisfy the condition of spherical identity. So for this kind of self-inverse observable, you can simplify this expression, and that limit looks like something like this. And we tried to also obtain a different kind of bound because this bound may be hard to do the integration and may be difficult to compute. So we found a different bound which is given by this, the change in average value of the observable and its modulus divided by this norm of this quantity, which is the observable at initial time times the Hamiltonian. And also we tried to obtain a different bound, which is also given by this, not the Hilbert-Spin norm, but the trace norm. So we can combinedly write this two bounds as minimum over either this or this. And in addition to unitary dynamics, we try to derive the speed limit for linear dynamics also. So suppose your observable evolves in time in open quantum system, and we have this kind of equation of motion for the observable, where L is your Friedmannian. Then you can show that they respect this bound, and that will tell you the maximum rate of the change of the average of the physical quantity for the open system dynamics undergoing this linear dynamics. And if you define this lambda t as the time average version of this norm of this quantity, then you can give a bound which is again non-trivial bound that depends on this change in the physical quantity between two times divided by this quantity. And this is essentially the evolution speed of the observable, and this is your speed limit for the observable for non-unitary evolution or open system dynamics. And if you want to describe your dynamics using Krauss operator formalism, then also you can do that. And that's where we have this observable speed limit or dynamical map. So suppose you have a quantum system, initially prepared in state rho, which can be pure or mixed state, doesn't matter. And let the dynamical evolution is governed by CPTP map. And the CPTP map is described by a set of Krauss operator like this, and they satisfy this identity. And we know that the dynamics of the observable in the Heisenberg picture is given by this kind of expression, because if we know that your state evolves like rho goes to sum over IKI rho ki dagger, the observable evolve in this fashion. And then you can prove that the speed limit for the observable is given by, again, change in the average quantity in its modulus divided by this quantity, where this lambda t is time average version of the norm of this operator. And the quantity that you see on the right hand side is essentially your speed limit or quantum speed limit for the observable undergoing this CPTP map. And we also try to actually apply this in some physical context, and that I'm not showing here, and that actually respects this bound. And we try to apply in different contexts. So one example is in the context of quantum battery, which is attracting a lot of attention over the last several years. And quantum battery is a microscopic energy storage device that was introduced by Lqcc and fans. And as I said, over several years, a lot of theoretical work has been done to strengthen this novel idea of quantum battery and enhance its non-classical features. Like whether you can use coherence or entanglement to charge the quantum battery, a lot of things are happening. And quantum battery can easily outperform classical batteries because of several quantum advantages you can claim. And essentially, these quantum batteries consist of many quantum systems with several degrees of freedom in which you can deposit or extract work from it, and then you can use later on for your purpose. So if you consider a battery with Hamiltonian HB and you charge it by switching on some field Hamiltonian SC, then total Hamiltonian of the battery you can write like this. And the amount of extractable energy from the quantum system by unitary evolution is usually called ergotropy of the quantum battery, which is given by the average of the Hamiltonian HB in state at time t minus the average in the initial state. But the same thing you can also imagine as the average of this HB at time t in the initial state minus HB at time t0 in the initial state. And then you can ask in the Heisenberg picture how fast you can charge the quantum battery. And we found that if you use our bound for unitary dynamics, you can use this bound, and also you can use this bound, where this is your operator norm, and this is your Hilbert-Smith norm, and this is your trace norm. So you can use any one of the bound and try to answer this question: how fast your battery takes to recharge, And as another application, I would try to apply this observable quantum speed limit for two-time correlation function. For any arbitrary pure quantum state, we can define this correlation function, which is essentially denoted as C of AT and A0. And that is essentially AT A0 average minus AT average and A0 average. And for closed system, our AT is essentially this, and for open dynamics, this AT is essentially this. And you can use this bound for unitary dynamics, or you can use this bound for open system dynamics, and you can answer this question that how fast this two-time correlation function actually evolves in time. And this can have, again, interesting applications in many-body physics. So a lot of possibilities are still there. We have explored a few, but I think this will have very interesting applications. As one more application, we try to see how fast the commutator between two operators in two distant regions actually evolves in time. And this quantity is of great importance in the context of Lieb-Robinson bound. And this bound provides a speed limit for information propagation about the perturbation in the many-body physics system. And this essentially gives an upper bound for the operator norm of the commutator A and B, where A and B are specially separated operators of a many-body quantum system. So what we try to tell you is that even in non-relativity quantum dynamics, one has some kind of non-locality structure analogous to notion of finiteness of the speed of light in the electrostatic theory. So this, if you look at the commutator and look at the operator norm of this quantity, that is bounded by this, where the C and A are some suitable constant, and the B is known as Lieb-Robinson speed or velocity, and D is the special separation between two sides in the many-body system. And essentially, this tells you that this is bounded by this quantity. Now, we like to answer the following question: that how fast this commutator actually changes over time. So that question can be answered very easily if you use our speed limit. So while the Lieb-Robinson bound leads to speed limit of information in quantum system, the quantum speed limit for observable can answer the question how fast the commutator actually changes for observables belonging to two distant regions in many-body scenario. So here we would like to derive distinct speed limit bound for the commutator between A, T, and B in the Heisenberg picture. That will tell you how fast that changes in time. So if you define this quantity, that is commutator between two observables in two different regions of many-body system like this, then we can use this quantity OT and try to see its evolution, because you see this is essentially anti-Hermitian operator. So I times this will be Hermitian operator, and you can apply either you can think of evolution in this fashion for closed system, or you can imagine evolution of this fashion for open system, and you can apply our result, and that will tell you that yes, indeed, that there is a non-trivial lower bound, how fast this commutator changes between two distant regions. Okay, so just to summarize, what I try to convey you is that quantum speed limit for state evolution actually plays important role in quantum theory, quantum information, quantum control, and quantum thermodynamics. Now, if you want to describe quantum dynamics in the Heisenberg picture, then you cannot use the standard quantum speed limit for the state evolution. You have to define the speed limit for observable. With that motivation, we try to derive some interesting results. And what we did is we tried to prove quantum speed limit for general observable, for unitary dynamics, as well as for Lenzbladian or completely positive dynamics also. And possible applications includes quantum battery or probability dynamics, growth of two-point correlation function, or time development of commutator and its connection to Lipschitz Robinson bound. So when I mentioned this probability dynamics, I had not actually included, maybe due to time limitation, but essentially we tried to show that if you choose your observable to be a projector, you can actually obtain the standard, Mandelstam term bound from our bound actually. So that is consistent with what you know already. So in future, we hope that these bounds can have useful applications in quantum metrology, quantum control, or even detection of non-Markovianity, or maybe in quantum thermodynamics and charging and discharging of quantum battery, and many more areas of physics. Okay, so with that, I thank you all. If you have any question, I will be happy to answer.
Thank you, Sharon. So yes, we do have questions. Sibashish is the first one. Please go ahead.
Okay, Harun, nice talk. So I have a naive question. So basically, in speed limit, it is the dynamics that plays the main role, right? I mean, now if I have a given dynamics, be it unitary dynamics or let's say open system dynamics, if I look at the speed limit in terms of state vectors or in terms of density matrices, it provides you some kind of limit, okay, on the speed of how the state changes or something like that. Now here you are talking about speed limit in terms of observables.
Yes.
Now we know in quantum mechanics that these observable and state, these are the basically dual description, right? In terms of the Heisenberg picture, Schrodinger picture. Now physically, what is it that you would like to expect, or you expect that the speed limit of observables will provide you? I'm not talking about their values, but physically, what kind of features the speed limit of observable would provide that cannot be captured by speed limit of states and vice versa?
Yeah, so try to apply, like if you want to, as I said, if you want to describe the two-time correlation function, how it changes in time, in that maybe easily, of course, I mean, both are equivalent, we know that, and maybe, I mean, my feeling is that both the description are useful, but maybe this description may be useful in some certain physical context. Like if you want to answer the question that how fast the two-time correlation function changes in time, maybe our bound maybe easily, you can handle it, or maybe you can calculate easily. So but whether you can give a completely different description, that I'm not very sure. Maybe wanted to deal with that we are trying to explore actually. So maybe in open system dynamics something might happen, but I don't know that. So.
Okay. I mean, of course, for calculation purpose, of course, sometimes this will be helpful. Like, in the case of this, checking the commutators different times, that will be helpful here.
Yeah.
Okay. Thank you.
Yeah.
Thank you very much. Next one was Aravinda.
Thanks, Professor. This is a very nice talk. As the field limits depends upon the dynamics, do you expect some quantum chaotic dynamics has some different limits compared to non-chaotic dynamics, or any such statements to this?
Yeah. So. So in context of chaotic dynamics, there is this notion of scrambling of information. So if you start with this out of two-time correlation function, then that gets really complicated. So how fast it tend to be complicated? That kind of question may be not answerable in Schrödinger picture. Maybe maybe not using standard quantum speed limit, but if you use our speed limit, maybe you can answer that question. So I'm hopeful that we're trying to think along that direction. So we're trying to apply the speed limit for the observable in the context of scrambling and trying to see if that is making some sense. Yes.
Thanks.
The answer to your question is maybe yes. Yeah.
What I mean to say is that this could provide would it provide another way of characterizing the chaotic system?
Possible. Yeah, that may be possible. Yeah. Again, I wanted to check that, but I think there is a good chance. Yes.
Thank you very much. Next one is Professor Majumdar.
Yeah, hi Arun. So nice talk. Yeah, so my question relates to, it's partially related to Shivashi's question, and more specific.
I could not hear.
Yeah, we cannot hear you. But you're not muted actually, so maybe just some connection thing. Let's wait a second.
What the question that Subhasis asked regarding that how QSL is related to observable, so it can be useful in the transitions where the observable changes, and QSL.
I'm not able to hear. Can you tell loudly or something? I don't know. Some noise is coming. Hello.
Yeah. Now can you hear me?
Yeah. Now we can hear. Yes.
Yeah. So I was saying that regarding the Subhashi's question, I was saying that QSL to observables is helpful for the transitions when we are undergoing from one state to other. Then, of course, the evolution would be limited by the quantum speed limit, and then QSL is helpful. Yeah. Thank you.
Thank you. Hey, actually, then since we still have a few minutes, I also.
John, are you there?
Yeah, sorry for the misconnection.
Okay, you're back.
Sorry all. But I don't know how much I managed to convey. But it was to do. Did you hear?
No, I could not hear anything. So can you?
So it was partially to do with one of your last remarks that you made, that if you have projectors for observables, then the limit reduces to the Mandelstam bound. To my understanding, the Mandelstam corresponds to the QSL for
again lost.
I think he's there, but
right.
I could not hear. Archan, I could not hear your last part of your statement.
Yeah, can you hear me now? I'll try one last time.
Yeah, now I can hear.
Yeah. So the Mandelstam limit corresponds to the Hamiltonian, not the fluctuations of the Hamiltonian.
No, the fluctuation one, not the bound which involves only Hamiltonian, that is Levitin, Magloss-Levitin bound. I'm talking about ML bound.
Okay. So I missed that. Anyway, thanks. So look forward to discussing more with you at some later time. Thank you.
Okay, thank you. Yeah.
Thank you. Do we have any other questions, comments? I would like to ask one actually. So, this Mandelstam bound essentially tells you that the time to it has to be taken to evolve the system from one state to another is inversely proportional to the standard deviation of energy, right? And these other people, Margolis, they have the energy. I think the energy I can understand, because you pump more. So imagine you push something, you kind of push harder, it evolves faster. And is there such a simple understanding also for this energy standard deviation of energy or energy variance?
Yeah, because you see, I mean, as I said in the beginning, you know, when a system evolves in time, we know that, of course, it evolves according to Schrodinger equation, and Hamiltonian does play a very important role. But it is not just Hamiltonian. It is actually the variance which drives the system, you know, along the trajectory, you know, in the state space. So
in this projective space.
Yeah. So in the projective Hilbert space, if you define the distance, if you define the speed, it is not the Hamiltonian. It is actually the variance. You know, so variance is more fundamental quantity which decides how fast the system evolves. So I would say I would put the Mendelssohn term bound on more fundamental footing compared to Margolis Levitin bound. You know, so because it is quite natural. You know. Of course, I mean, we can derive from different perspectives this Levitin bound, but to me, the empty bound is more fundamental because that directly comes from geometry and from the uncertainty relation, you know. Yeah.
Fair enough. And in open system dynamics, then can you also think in terms of, I don't know, that you have, when you have an open system, then essentially you can pump some energy from the environment into it, and so it could evolve even faster, or I think I think a lot of work is still there. Yeah, right. Does it have? Okay, there is this kind of interpretation. And in mathematics, which is the quantity that replaces the variance of energy?
Yeah, so you can define, I mean, different some effective variance, not exactly variance, some effective looking like variance. So that we have done also for open system dynamics. Yeah, I did not include here, but yeah, we have that kind of, and other people also, other groups also have this different results also. Yes. Yeah.
Okay, so we have one more question. Thanks a lot. The last question, please go ahead. Manirul Ali.
Hello, Arun. Thanks very much. This was a wonderful talk. Actually, I have the question related to this open system dynamics. So in open system dynamics, we know that I mean, it depends on the interaction of the system and in the environment, and the environmental spectra, coupling, what kind of coupling we consider. So once those things actually drives the dynamics. Actually, what type of dynamics will be in the open system. So do we have any control once these things are fixed? Then this quantum speed limit, I mean, in quantum control theory, we can understand, we can do something by some external pulse or something like that. This is my first question. Second one is that in open system dynamics, sometimes we have an initial state and there is a target state, for example, the thermal equilibrium state. Then you want to know how fast it will reach to thermal equilibrium. But there are other certain situations where in very ultra strong coupling situation, there can happen something like that. You cannot reach to thermal equilibrium. So in that scenario, even if you wait for a long time, your target state will not reach. So can you please put some light on these things?
Yeah, so we thought of this question, you know, trying to apply speed limit and how fast, how much time, does it really take infinite time, or does it, there is some long but some finite that we try to explore, but we don't know yet the answer. And coming to the first part of your question, yeah, so I think a lot of paper, they try to explore how this speed limit depends on the coupling strength, or depends on, say, you know, spectrum of information. Like Subhasis, he had a talk also on open system dynamics, you know, speed limit. So many people are actually working on that. So yes,
but it is but it is
Mhm.
really a quite important question actually, and very interesting topic actually. And and thanks for your wonderful talk.
Thank you.
Thank you.
Thank you very much. Thanks from all of us.
Thank you. Yeah. Take care.
Let's move on. Thanks a lot. See you. Our last speaker is Dr. Armin Tavakoli. Armin, are you around?
Yes, I'm here.
Yes, oh, great. Thank you very much. Please share your slides. And I had a quick look. So you're from Icqif, Vienna, right?
That's right.
Working, and the title is Entanglement in Quantum Communications. And I saw you're a postdoctoral researcher with Markus Huber. So please welcome Armin. Go ahead. Thanks.
My slides are visible now. Is it?
Sorry?
Are my slides visible now for you?
Yes, but it would be great if you could make them full screen.
So, it's not full screen. Okay. Maybe I did it the wrong way. So what about now? Good.
Yes, much bigger. Yes, thank you very much.
Okay.
Go ahead.
So thank you all for giving me a talk in this conference, and good morning and good afternoon, wherever on the planet you may be. I will give a talk entitled Entanglement in Quantum Communications, and it is broadly based on the two archive posts that I'm showing here. This is work done together with my collaborators in the group of Stefano Pironio in the Free University of Brussels. And in this work, we are interested in addressing a union between two very basic resources that we use essentially paradigmatically in quantum information science, namely entanglement and quantum communications. These two resources have been studied separately for a very long time in a very diverse manner. The perhaps seminal, certainly most famous scenario in which we study entanglement is something that looks like this. You have a source that distributes an entangled pair to a pair of parties, and these parties can perform some measurements represented by an input arrow on each, and they observe some outcomes, which are represented by an output arrow on each. Scenarios like this, when you perform local measurements on shares of an entangled state, they are famously used very broadly in scenarios like Bell non-locality, quantum theory, device-independent quantum information protocols which spans cryptography and random number generation and so on. Within this scenario, we have entanglement, and it's the thing that makes all of these very interesting forms of physical phenomena possible. But for sure, in these scenarios, the fact that it doesn't feature communication is essential to all of these types of physical phenomena. Local measurements on entangled states without communications. On the other hand, here on the right, we have what you may call the seminal, or at the very least, the ubiquitous scenario for quantum communication. This was what Tony Asin called the point-to-point scenario in his talk yesterday. And it's a scenario in which you have a sender and a receiver. And the sender can prepare different types of messages. They can be classical, they can be quantum, and they are sent over a classical or quantum channel to a receiver. And the receiver can, just as in the entanglement scenario, perform different measurements represented by an arrow and observe some outcomes. And now you can investigate correlations between the outcome of the receiver and the input of the sender. And in a very similar spirit, this type of scenario serves as a basis for many, many different forms of quantum information protocols. Naturally, it's the self-evident platform for quantum communication advantages, but it can also be used for quantum certification protocols, quantum contextuality protocols, and is also famously used for various forms of quantum key distribution, such as the BB84. Here, the essential feature is that you have a communication channel, but your devices are not quantumly correlated. That is, at most, which has typically been done in the field, you assume that your devices are either independent or classically correlated. So what you have in a gist here is that on the left, you have the seminal scenario of entanglement without communication, and on the right, you have the seminal scenario for communication without entanglement. In this talk, we want to know what happens when we merge the two. But let me first talk a bit about the standard scenario for communications. That is the thing that has been researched for a very long time by now. The standard scenario looks like this. Again, you have a sender and a receiver and a channel that connects the two. Now I'll give their inputs and outputs some names. So on the left here, the sender will receive some input that we call X. And this is translated into a message that is sent over a channel. The receiver takes some setting Y, performs a measurement, and determines the outcome B. Naturally, if you want to say something interesting about the physics that's going on in this scenario, you need to say something about the channel that is connecting them. The reason is simple. If you don't say anything about the channel, the sender can just copy X, send it over the channel, and then every single probability that you can imagine between B, condition X and Y, can be generated within an essentially trivial physical model. If you want to do interesting physics, you have to assume something about your system. So far, the most popular and widely most well-researched scenario has been the one in which the alphabet of the message that goes over the channel is limited. In classical scenarios, it means that messages are bits, tricks, quarks, and so on, but no more. In the quantum scenario, it means that messages are 2-level, 3-level, 4-level quantum systems. And by virtue of the Hall-Level theorem, from which it follows that a quantum d-dimensional system cannot carry more than a classical d-dimensional system, the comparison is valid. And many times, for the sake of simplicity of treating the problem, as well as for physical motivation, it's imagined that the two devices, the sender and the receiver, are connected by a source of classical shared randomness. This is the analogy of a hidden variable in Bell non-locality test. It's essentially a string of correlated bits that the parties can use to stochastically coordinate the strategies, the messages and decodings that they are running. And the fundamental question in these scenarios that you need to answer in order to do any of the multiple applications that you can imagine for these problems is to say, what are the correlations, that is, the probability of the outcome B, given the message X and the measurement Y, when the sender and receiver are classically correlated. That is, they are allowed shared randomness and a quantum channel. This scenario is very well understood by now, and it has been studied for almost 2 decades. What we want to do is to take a natural step beyond this. We want to merge the concept of quantum communication with that of entanglement. So what we do here is that we have exactly the same scenario, but we are swapping the shared classical randomness for a source of quantum correlation, namely a source of entanglement. So now an entangled state is distributed between the sender and the receiver, and the sender now has to process this into a message of a limited dimension that is sent over a channel, and then the receiver receives both a message over the channel and a share of the entangled state. And this can be jointly processed into a final outcome. In this scenario, we have entanglement, we have quantum communication, and we distinguish between the scenario in which the channel is supporting a classical message and a quantum message. We will see that our methods can actually be used to tackle both of these cases. And in a very similar spirit to before, the fundamental question for essentially any protocol that you might be interested in a scenario like this will be, what are the possible correlations when the quantum devices are quantumly correlated? That is, when they share entanglement. By now, the natural association that I believe many of you has already made is, isn't this a lot like dense coding? And the answer is, of course, yes. This dense coding is the most famous, perhaps the only famous, special case of a problem like this. I quickly remind you what it is. In an ordinary quantum communication protocol, the upper one, in which you don't have entanglement, you only have quantum communication, we know that by the Hall-Level theorem that you can send an input, you can encode it into a qubit, send it to a decoder who tries to make a guess for what your input was. If you have a qubit system without entanglement, you can only distinguish 2 symbols. That is, the fact that you have a quantum message doesn't help you. The dimension limits your ability to say something. But famously, if you additionally allow the sender and the receiver to share an EPR pair, a maximally entangled state, then the qubit can suddenly support twice the amount of information. The decoder can distinguish 4 different symbols from the encoder. The standard way of phrasing this phenomenon is that dense coding doubles the classical capacity of a quantum channel, in this case, an identity channel. So we already know from this spectacular and famous example that the combination of entanglement and quantum communication dramatically changes our ability to create correlations between senders and receivers, and it constitutes the most powerful communication resource that quantum mechanics offers us. So therefore, it's natural to try to explore it beyond the simple scenario that is dense coding. So let's now look at what for us is the simplest scenario in our picture. Our picture is different from dense coding. Dense coding has one specific aim, that is to perform information recovery. The sender creates a message, the receiver wants to recover it. But in quantum communications, there are much more diverse forms of correlations. You can have, for example, you can have situations in which the receiver is interested in multiple different questions, here indicated by Y, about the nature of X, and B is the guess for the answer of those questions. And in the simplest scenario in our picture, you're allowed arbitrary messages, you're allowed arbitrary questions and answers, but your channel that connects you is just a qubit one. You are not allowed to have higher dimensional messages, and you can have entanglement to assist you. So in this simplest scenario, let's distinguish three very basic resources. The first one is dense coding. That's the same as using the famous protocol. You use a qubit channel and the maximally entangled state to substitute for 2 bits of classical communication. So dense coding is the same as doubling your classical capacity. But you can imagine a generalized dense coding picture in which you again have access to an EPR state, but now you don't try to double your channel capacity. Instead, you try to have more general unitary encodings. So once the particle reaches here, you perform some unitary and send it over the channel. But these unitaries now, they are not necessarily constructed such that you can extract 2 classical bits as in dense coding. Interestingly, we find this rather non-trivial result that the most general correlations that you can create using general unitary encodings and a maximally entangled state is actually isomorphic to a standard communication problem in which you have no entanglement, so this part vanishes, but the channel is substituted by a 4-dimensional quantum one restricted to real Hilbert space. So there is a very simple isomorphism between generalized dense coding and the real quantum communication. But in full generality, there is an even more powerful resource, and that's the one we are really interested in, which I simply call entanglement-assisted qubits. That is, the fact that you could, in principle, use an unbounded amount of entanglement in the source and irreversible encodings. You could imagine that you have a very high-dimensional system coming here, and somehow you have to jam this very big system into just a small qubit, reasonably losing a lot of coherence in the process, and then send it over here, where one share of the very high-dimensional system is measured together with the just 2-dimensional quantum system coming over the channel. For this most general resource, we don't know a simple isomorphism, like in generalized dense coding, that takes us back to a standard communication scenario. In fact, it's not even clear that this is useful. Why would we even need very high-dimensional entanglement and then destroy the coherence by jamming it into just a qubit? Is this even clear? These are the basic questions that this new scenario demands us to answer. It turns out that the answer is yes. High-dimensional entanglement, even though you lose the coherence, is actually a useful resource. And the way to showcase that actually all these 3 resources are very different is through an example. So here we will go beyond the dense coding case. This is done through a specific game, and I will just sketch you what the main idea is. It consists of 2 parts, just to make it a bit more accessible. In the first part, Alice has 2 binary inputs. So you have 2 bits here, 00, 01, 10, and 11. Bob here has 2 possible questions. The game is that known as a random access code. So the job is to recover with B, bit number 1 or 2, depending on Y, on Bob's side. But Alice, of course, doesn't know which bit Bob is interested in a priori. And your resource is a qubit channel assisted by entanglement. So as often as you can output the bit number Y of Alice, you win the game. Part 2 of the game is that we actually have 1 more input on Alice, which we call number 5. And we have 1 more setting on Bob, which we call number 3. And when you run setting number 3 on Bob, the job is to perfectly distinguish the input 5 from the other 4. This can be viewed as a state discrimination. You want to deterministically flag that right now in this round, the message definitely was either 5 or 1 of these 4. This can be viewed as a constraint on top of the random access code. So in this game, how well can you perform? What we find here is that our 3 resources, dense coding, generalized dense coding, and fully general entanglement-assisted qubit communication or quantum communication perform very differently. Dense coding is again a replacement of the smaller quantum resource in favor of double resource for the classical capacity. This can give you a certain success probability. In the generalized dense coding, you can outperform this. It's not a one-to-one mapping between the capacities and the correlations. But the most interesting part is that if you use a higher dimensional entangled state, specifically the entanglement of two four-dimensional systems, you can, in spite of having to cram your four-dimensional system into a qubit and send it over the channel, outperform even this form of generalized dense coding. So what Alice would do in a strategy like this is to receive two shares, two qubits coming her way from the source, and then use a collective unitary, bin one of the qubits, so throw it away, and send the other one to Bob. What this example is meant to teach us is that higher dimensional entanglement is in fact a resource for lower dimensional quantum communication. Or in other words, that entanglement-assisted communication problems are much richer than just the famous dense coding scenario. So knowing that the dimension is a resource, we are faced with a very natural task, which is how can we characterize in full generality the predictions of quantum theory in entanglement-assisted communication problems? That is, scenarios in which the state here is assumed to be of unbounded entanglement. That is, it could be qubit, it could be infinitely many qubits, whatever. There is no assumption on the nature of the entanglement. There is only an assumption on the channel itself. What we want to do in general is to determine whether a given correlation, so a probability of observing B given input X and Y, is compatible with a quantum model for any input-output scenario. So any alphabet you have on your inputs and outputs here, any given message dimension, that is the size of the message allowed over the channel, and we want it to work both for classical and for quantum messages. So when your channel is supporting an integer message or a quantum state. And in fact, we present methods that can resolve this in terms of a converging hierarchy of semi-definite relaxations of the task. I will sketch a little bit what this could look like. The gist of it is something like this. This is the picture to have in mind throughout. So what we try to represent here is the space of possible correlations that you could observe, PB given XY. Here in red, I have put the entanglement-assisted set when you have classical communication. And naturally, this is a subset of the entanglement-assisted set when you have quantum communication. Naturally, classical is just a special case of quantum. And then you could imagine that you have some linear function, like the dense coding one. How often do I recover the message of interest? Or another one, like the one I presented in the previous example. This is represented by this black arrow here. What the task is that once you give us a task like this, the linear function, and you ask, what's the best performance a quantum model or a classical model could ever do? We want to pinpoint that number. So to do this, we need both inner approximations and outer ones. Inner ones, they go from the inside of the set, for example, the red one, and try to approach the boundary, for example, as this purple curve here. Outer approximations come from the outside, like the orange one here, and try to approach the boundary. And ideally, we want these two to match exactly at the boundary. The way we do this systematically is through semi-definite relaxations of the problem. So we give you a hierarchy, and the more computational power you're willing to spend, the more accurate outer relaxations can you get for your set. I will briefly sketch what this can look like, and I will do it in the simple case, which is more accessible, namely the case in which we want the classical message assisted by potentially unbounded entanglement. We in fact have two methods for addressing these questions in full generality, and I will discuss them both immediately. One is based on the well-known Navasquez-Pironio-Assin hierarchy of semi-definite relaxations. So it's essentially amounting to restricting it to a bell-type problem. And you can easily see why this occurs for a classical message. So imagine you have a classical system. Your quantum entanglement is being shared, and what you have to do as a sender is to take this quantum system of arbitrary dimension and map it into a classical message that goes over the channel. The most general channel that takes you from a quantum system to a classical one is a measurement. So that measurement we can call A here. It has some outcome that we call M, and based on the setting X that the sender takes in the scenario. The outcome M is relayed over the channel. So on average, the receiver, Bob, is getting a state that looks like this. You make the measurement, you get the outcome M that is sent over the channel. But at the same time, this measurement is influencing the particle that the source distributed to Bob. And that influence is represented by this. That is the measurement on Ali's side, and then you lose that system and replace it with the message. And this has to be average over all your message symbols. So what can the receiver do once the message arrives? Well, the most general thing you can do is to first read the message. This can be done classically, and then adapt your measurements in order to measure the quantum particle. So first you do that, and then you use M as a setting. So you end up with something like this. You read the message, and then you use the message here to condition your measurement. So the matrix, the probability distribution takes a form like this. And this should remind you a lot of the correlations you get in a Bell scenario. But it's also crucially different because the outcome here is appearing as an input on the other side. There is signaling in this problem. But from a technical point of view, this is essentially an NPA type matrix. So we can recycle the NPA hierarchy to address these types of correlations. This is the lucky and sort of simple special case. We also have a quantum analog for this. That is when the message that goes over the channel is a quantum d-dimensional system. This is a bit more nasty, and I won't outline it here. I will just say that this is based on using Krauss operators, based on the unitaries that you can use here in the quantum to quantum channel now, to parameterize the message system explicitly. But for the details, I'll have to refer you to our paper. Then we give a completely different method that also resolves the same problem. And I will tell you why you need both of them in a moment. This time, it's not based on NPA type relaxation. It's instead based on a completely different concept that we developed a toolbox for in this other paper, informational restricted correlations. So here the idea is that you have an ordinary communication scenario, and you want to talk about how much knowledge needs to be transferred from a sender to a receiver in order to explain physical correlations. So in our scenario, we have this. We have this the entanglement, again, perhaps infinite dimensional, and then you have a classical or a quantum channel of dimension d. We now ask, how much knowledge could a system like this ever allow the receiver to get about the sender's input? Very much in the spirit of dense coding. So you had a message, you use your quantum resource, and you try to output exactly what the message was. So you want the output to equal X. How often can you do this? This is what you do perfectly in dense coding with 4 symbols. And it's also the same as state discrimination with the minimal error, essentially. So in fact, you can use state discrimination as an information quantifier for a problem like this. So you can talk about the information I that is made accessible to the receiver through an optimal measurement. So you have the min entropy in the input of the sender here. This is just a function of the probability from which you sample X, and you can, without loss of generality, just take it to be uniform, so you can forget about this. And then you have the conditional min entropy. That is how much knowledge you have about X, the input, once you have performed your measurement. That is how often you can get this quantity right. It's known that this type of entropic measures relate immediately to a state discrimination problem. That is, they are one-to-one with the thing we call PG here, which is exactly the probability of doing state discrimination optimally. So what we want to do is to make a connection now between this scenario, which is the one of interest for us, and this information quantity. And we make 2 very simple and rather reasonable observations. The first observation is that if you have an entanglement-assisted classical channel of dimension d, you can at most transmit log d bits of information. This is essentially a one-shot version of Hollevel's theorem, and it's very intuitive. We know that entanglement doesn't boost channel capacities, so you can't send more than d different symbols, and nothing changes in this one-shot regime. And very much the same for the quantum case. That is, if you have an entanglement that is supporting a quantum message of dimension d, you can at most double the capacity of your channel. This is well known in cases where you have asymptotic limits, and here it's also true in the one-shot case. So based on this, we can use information relaxations to address the problem we care about, namely that of entanglement-assisted correlations. What we do is this. This is the scenario we care about, entanglement and a quantum or classical channel. We relax it to an informationally restricted scenario. That is, we replace it with the ordinary, without entanglement, communication scenario. But now the assumption on the channel is not based on dimension, it's based on how much knowledge you can transfer between Alice to Bob. This we can do because of our observations. And then we can use the toolbox that we already have developed in the previous work I mentioned for informationally restricted correlations to efficiently bound the correlations you get, and you can efficiently compute an upper bound on this scenario that you care about. So the two methods I've given you are very different, but I'll give a quick comparison and tell you why they are both interesting. On the left here, you have the NPA one. This one has the huge benefit of being converging. That is, if you go high enough in our hierarchy of increasingly expensive computations, you will eventually hit the bound you care about. You will converge. And this is not the case in the information-based approach. We have a counterexample, and it's not expected to be, because the relaxation we made here from the scenario of interest to the information-based one is not tight. However, it turns out it's very nearly accurate for practical considerations. And those practical considerations are exactly what motivate the information-based approach. This you can see here in the second row. If you take a look at how expensive it is to compute something with these two methods, you see a big change. So the SDP that you need to evaluate in the case of classical communication scales like this. So here you have the number of inputs on the sender, the inputs on the receiver, and the outputs on the receiver. And here is the dimension of the channel. This you can compare to the information case, which is the same, except that it doesn't depend on D at all. You can go to very high dimensional systems and not pay a price at all in terms of the number of operators that you need to employ. If you go to the quantum case, the scaling with a converging hierarchy becomes even more unattractive. That is, you scale quadratically in the dimension, whereas in the information-based approach, you stay unchanged. You're still independent of the dimension. So if you want to treat not the smallest system, but even something mildly larger, then you can get very practical methods of computing things using the right method. But on the left, you have in principle a full solution. So I want to conclude by giving you just one of the applications that you can use this for. Perhaps the simplest one to envision is an application towards device-independent dimension witnessing. This is a topic that received a lot of attention over the past decade. The idea of a device-independent dimension witness is that you want to have a scenario like this, the ordinary communication scenario without entanglement. And you want to say that by inspecting the data that I measure in the laboratory, I can deduce a lower bound on the dimension of the system that was sent over the channel. And I want to do this without making any assumptions on the measurement devices of the receiver and the preparation devices of the sender. In that sense, it's device independent. And many examples of these are known, many experiments on this have been made. However, the crucial thing to recall is that in the device independent paradigm, you don't want to make any explicit modeling. But the typical way of approaching this in a standard communication scenario is in fact making a critical assumption. And that is the one that we have been highlighting all the time here, namely that the devices are not quantumly correlated. At most, they are classically correlated, or they are just independent. A fully device-independent certification of a quantum dimension ought to take into account the possibility that quantum theory could correlate the devices without using the channel, that is, by using entanglement. And we want to showcase that this can be relevant using our methods. So here we use a witness for dimension that was presented in the original work of Gallego and co-authors in 2010. So basically, this scenario, you have 5 settings, 5 different preparations, 4 different measurements, and 2 outcomes. And for each pair, X and Y, you can assign a correlator or an expectation value to your outcome. And then you give them some suitable signs so that they happen to be an optimal test of classicality. This is derived in the work of Gallego and others. And what they did is that they used the standard scenario without entanglement to assert bounds on how well you can perform the task if you have a 2-dimensional, 3-dimensional, 4-dimensional, or 5-dimensional classical message. Note that if you have a 5-dimensional classical message, you just send the whole X over the channel and you trivialize the problem. So you have a nice hierarchy like this. Then they would put the quantum case. So here in the quantum case, you substitute. So the classical message is now a quantum 2-dimensional system, then a quantum 3-dimensional, quantum 4-dimensional, and a quantum 5-dimensional. And you see that you consistently have an advantage. So 8 for classical systems, somewhat higher than 8, and so on. You always have this quantum advantage. So if you violate, say, 8 in your experiment, and you assume that your model is classical, you would conclude, well, then I definitely have at least a 3-level classical system. And in the quantum case, you would say, well, if I'm bigger than this number, then for sure I have at least a 3-dimensional quantum system. But if you have entanglement involved, everything changes and you can spoof these conclusions. So entanglement demands revisions, and these are what we are computing. Here in the upper one in blue, I'm giving the method that we are using. So the MPA one and the information one. In the first case, you have classical message, but you could have quantum correlations between your devices. This boosts the ability of a classical message all the way up from, say, 8, which was the performance here, to this number, which is even stronger than the quantum one, in fact. So if you say you go to the lab and you make a measurement on a classical system and you observe that the score was 9, then you could incorrectly conclude that this is a 3-dimensional classical system. But actually, it could just be a 2-dimensional one assisted by entanglement. You can spoof the conclusions, and this continues likewise. This also highlights the methods that I was talking about before. So what you see here is that in the absolute smallest problem, that is when you just have a 2-dimensional communication, the NPA, which we know is converging, indeed outperforms the information-based approach by a very small edge. But as soon as you go to a 3-dimensional one, it turns out that information is just more handy from a practical point of view, meaning that we couldn't go high enough in computer power in order to beat the limit that we get easily from an information-based approach. And this continues doing so. These bounds are essentially tight, over 99% accurate. Now we have the same problem also in the quantum case. In the quantum case, only the case of a 2-dimensional message is interesting, because if you have a 3-dimensional one, you could do dense coding and send 9 symbols and thus trivializing the problem. But an entanglement-assisted qubit, you end up with a value like this. So you can again spoof by a long shot the results you get from an unassisted qubit. So your dimension witnesses certainly need to take this possibility of entanglement into account in order to be fully device independent. So I want to conclude with a brief outlook and say that the main message that I want to give you here today is that with these works, we are trying to initiate a systematic study of communication scenarios with entanglement that go beyond the standard questions of capacities. That is, how well we can do information recovery over a channel. We are interested in the general correlations that quantum mechanics can predict when you have access to the most powerful communication resource. In fact, we wrote a whole second paper in where we really highlight that we really have a lot of questions and a very small number of answers to this. So here you have a very long list of open problems that we hope to address, but we are certainly not numerous enough to do it ourselves. I want to highlight just 3 of them here. These are my personal favorites. So the first question is there a sufficient entanglement dimension? One of the main results we have is that you don't need to have a symmetry between the channel dimension and the entanglement dimension. But do you need the case in which you actually need infinite entanglement to reach the full power of quantum communications? Or does there exist a threshold always once you know your scenario? For this, we have absolutely no idea so far. The second question is the relationship between capacities and correlations. In general, capacities are a special case of correlations. Those are the ones that amount to how well you can recover a message over a quantum or classical channel. Quantum correlations, on the other hand, could be more general. You could ask multiple questions. But it's natural that if you have a high capacity, you can also produce strong correlations, simply because you can send more information. So what's the relationship between these 2 resources? This is something that we're interested in exploring. And finally, we based our whole investigation on the common assumption that your channel has a limited dimension. But in recent years, there have been many explorations of semi-device independent quantum information in which you try to go beyond the dimension. For practical purposes, the dimension has some problems. For example, no real qubits arguably exist. They are all higher order processes. can we base entanglement-assisted quantum communications on another assumption than the quantum dimension? So with that, I will thank you for your attention.
Thank you very much. Here we go. Manik, please go ahead. I have a question from Manik.
Yeah, I mean, thanks for nice talk. So I actually have some question. Can you go back to the your second slide where you define the scenario? Yeah, this one. Yeah, this one. Yeah. So you see, as you have correctly pointed out, that dense coding is striking because the qubit, according to Holevo theorem, can only send 1 qubit of information, but with the assistance of entanglement, it doubles up. But this scenario, like a right-hand side scenario, this communication advantage, Holevo theorem doesn't apply here, no?
So it does. So Holevo's theorem, it tells you that if you send, well, this is a corollary that you're interested in here. And it's that if you send a qubit over this channel, as compared to sending a bit, you can't extract more information.
No, but I can do another task.
Right, you can, but you can extract correlations.
We can extract
do more sophisticated tasks.
Exactly. So my point is, when we want to compare with dense coding, isn't it better to compare the scenario where on Bob's side there is no input? There is only one input at Alice's side, X, and on one output Bob, B. That now look into B given X, and not only that one quantifier, that this mutual information. It could be arbitrary payoff. That should be.
You're suggesting that what should you compare to the dense coding?
Dense coding is Alice has some only input X, and Bob only has output B, no input.
Yeah.
This is the dense coding, standard dense coding scenario, because if I have different input, I can perform decoding different non-commutating measure. But in dense coding, only single measurement is performed.
Right. So what's important to keep in mind is that dense coding is a specific protocol, right? It's the protocol in which you use quantum resources to send 2 bits. But once you send 2 bits, you can post-process them arbitrarily to answer multiple questions. So indeed, even though dense coding only contains a single quantum measurement, a Bell state measurement, you can then use the knowledge that you get out of this in order to answer multiple different questions. For example, if you have a scenario in which you have, say, 4 inputs, like the one I gave here, this one in part 1, the random access code.
Yes.
If you have a scenario like this, you say, I have 2 questions, but I can still use dense coding for this. I can send the whole input with dense coding and then classically post-process the outcome to answer both questions perfectly.
Yeah, that is true. That is true. But what is my point is, what I'm trying to point out, that in dense coding, so whenever you are saying like one theorem, you have come up with that this information can be log D, but there you are only considering only mutual information, the state discrimination problem.
Yes.
In earlier sense, you are calculating correlation, but look into correlation, there could also you can get more.
Yes. Yes, that's the problem we're trying to solve, right?
Because when you are comparing this log D and 2 log D, that is only you are considering only information extraction. That's all. Retrieval, but correlation could be much more general.
Exactly. That's why I have it as one of the big open problems that I'm interested in. These 2 things shouldn't be equivalent, but they are very much related, and I want to understand how.
Okay. Thank you. So just I want to point out, very recently we actually did some work. I'll share with it you. You can have a look.
Oh, I'd be happy to see.
Thomas, you are muted probably.
Oh yeah, good point. Thanks a lot. So thanks for this. Thanks for the answer. Thanks for the question. Let's go to the second one. Please go ahead, Bhattacharya.
Thank you. So I'd like to ask that in case of NPA hierarchy, we can link with some physical principle like local orthogonality. So in your case, this kind of hierarchy, can we link with some physical principle like that?
So you want to derive the correlation sets from first principles, basically.
Right.
That's
so in case of NPA hierarchy, local orthogonality can be linked with like exclusivity principle. That kind of physical motivation can be there. So in case of your hierarchy, can we associate some physical principle?
That is nice. I have not thought about this. Since we can connect our classical problem to NPA, maybe. The quantum one we can also connect to NPA, but it's a more sophisticated version of it. So there, I honestly don't know. So what type of principle would you imagine here?
I don't know. Also, I'd like to know that actually.
Oh, yeah, that's nice. We should add that to our many questions and a few answers.
Okay. Okay. Thank you very much.
Thank you. Do we have any other questions? Okay, thanks, Armin, for this lovely talk and great pace.
Thank you for having me.
Thank you very much. Thanks to all the speakers. Now I give the voice back to India.
Thank you, Thomas, for chairing the session. Thanks. So we will meet again at 7 p.m. So in Indian time, 19 p.m. Okay. Thank you all.
So this is the last session of today's program, and in this session there are two famous speakers. First one is Professor Adam Cavallo, and second one is Professor Lucian Hardy. So, and I think Adam Cavallo needs no introduction because he can be called a man of quantum contextuality. He has done so many famous works, and especially he gave a proof of quantum non-contextuality with 18 vectors in 4 dimensions in the spirit of Kochen and the Staker. He's currently a professor at ETSI, I think it is in Spain. He has done a lot of important works in contextuality and non-locality, and he has been very popular. As I know, he is also very popular among the students community of India. So over to Adam.
Thank you for the introduction. Can you hear me?
We can.
Okay.
Share your screen and start.
Yeah. Do you see my screen?
Still not. It's coming, I think. Yeah. Yeah, now I see. But you can enlarge it. Or you can make it full screen.
It is full screen in my computer.
Okay, it's okay then. Yeah.
Okay. Thank you in the first place for the invitation to today's amazing conference, which is amazing number of speakers in these peculiar circumstances for the planet. So really thank you for the invitation. Today I would like to talk about some new results on quantum contextuality. My plan is first to make an introduction and explain what is quantum contextuality and especially why is important. And then I will present two results. One is a loopful-free test of contextuality, probably the first loopful-free test of contextuality using two species of ions. And then I will move to a new theoretical result on magic sets that I think is also very interesting. So let's start. What is quantum contextuality? Contextuality is a feature whereby measurements cannot be thought of as revealing pre-existing values. There's a recent review paper on quantum contextuality. You have a reference down. But actually, the crucial question is, when is contextuality surprising? And the general answer is whenever there are reasons to think that the system we are measuring possesses pre-existing values. A particularly important case is this one. Suppose a system that is submitted to sequential measurements, in this case of two observables, A and B. And whenever the measurements, each of them, when repeated, yield the same result, even if each measurement is carried out using a different device or a different method, we have reasons to think that there is something in the system that is encoding the outcome of this, in this particular two measurements. For instance, in the slide, we first measure A and we get the outcome A. Now imagine we measure again on the same physical system A, and again, you get the same result. But then on the same physical system, you measure B and you get this B bar result. Fine. But then you measure again A and you recover the original result you got. And you can measure again B and recover the original result you get from B. So whenever you observe this behavior, you might be tempted to think that in the physical system, there's information encoding these two results. And this idea leads us to a more precise concept, which is the concept of ideal or sharp measurements, which are defined as those that yield the same result when repeated and do not disturb any compatible or joint measurable observable. Okay. So an example of an ideal measurement in classical physics is this one. You have a piece of wood and you want to measure the length of one of the sides. So, I mean, the measurement yields the same outcome when you repeat the measurement in the evening. And the measurement does not disturb any compatible observable, since performing or not performing the measurement in the upper one does not disturb the outcome of the measurement in the lower side. So what I'm trying to say is that actually the concept of ideal measurement is what most people think measurements are. But most measurements are not ideal. Even in classical physics, most measurements are not ideal. For instance, if you want to measure the resistance against pressure of a certain material, the standard way of doing is by putting this pressure and just noticing when exactly the material breaks. But this prevents you to make measurements of other observables afterwards. So this is a kind of example of a semi-destructive measurement. And arguably, most of the measurements involving quantum systems are not ideal. And this is one of the issues why there are not so good experiments on contextuality. I will add on this later. But this leads me to the following observation. Both in classical and quantum physics, observables can be measured using ideal measurements in principle. Okay. Moreover, both in classical and quantum physics, any coarse graining of any observable can be measured using ideal measurements. I mean the following. Imagine observable X, which has possible values 0, 1, or more than 1. You can either design a device that measures X ideally, so you can repeat and so on, but you can always measure the same observable by sequential measurements using a device that tells you whether X is 0 or not. And then afterwards, a second measurement telling you whether X is 1 or not. And afterwards, a device telling you whether this X is more than 1 or not. And each of these devices in the right-hand side are ideal measurements. Okay. In principle, both in classical and quantum physics, this is possible. So my point is that actually, as a notion, the observables in classical and quantum physics are ideal observables, those that can be measured through ideal measurements, and moreover, that allow any coarse graining of them to be measured through ideal measurements. Okay, what is a context then? Well, it's a set of ideal measurements of compatible ideal observables. That is what I meant by a context afterwards. And what is a contextuality scenario? Well, it's defined through a number of ideal measurements of ideal observables, specifying their possible outcomes and their relations of joint measurability. And these relations of joint measurability or compatibility can be captured into a graph in which the vertices are the observables and the edges identify those that are jointly measurable. Good. So this is an example that will represent a scenario with two observables that are compatible, or this one, which is more famous, which is four observables such that they have this particular relations of compatibility. Good. What is a behavior, or sometimes called a matrix of correlations for a given contextuality scenario? Well, it's nothing but a set of probability distributions produced by ideal measurements that satisfy the relations of compatibility dictated by the scenario. Okay, there's one probability distribution for each of the contexts. And I mean, we assume that the probability for every outcome of every measurement does not depend on the context. So we assume that we are guaranteeing the non-disturbance condition. Okay, for instance, this is an example of a behavior. Imagine the scenario that we put before, the square. We have four observables with these particular relations of compatibility. And then you have this, in each line, you have a probability distribution, right? together, all this object is a matrix of correlations or simply a behavior. Okay, and now we are in condition of properly define what is contextuality. We said that a behavior for a contextuality scenario is contextual if the probability distributions of each context cannot be produced as a marginal of a global probability distribution on all measurements. Otherwise, the behavior is non-contextual. The general picture of the geometry of the sets of behavior in the most general case is something like this. On the one hand, you have the set of non-contextual behaviors, which is a polytope for any scenario. Then for some scenarios, you have the quantum set that goes beyond the non-contextual polytope and is a convex set, and that is contained in another polytope, which is the non-disturbing polytope. Within this picture, the notion of a non-contextuality inequality is something that separates, identifies contextual behaviors. It can be a tight non-contextuality inequality if it's really a facet of the polytope, or it could be a non-tight inequality. Good. This with respect to the, let's say, technical definition of contextuality, but typically people ask, why should I care? Why is contextuality important? And I would like to make emphasis on this. There are basically two reasons. On the one hand is the observation that contextuality is necessary in applications with quantum advantage. Key examples are device-independent quantum key distribution, which is arguably the way of secure communication, which highest degree of security offered by the laws of physics. Well, it's easy to see that device-independent quantum key distribution requires quantum contextuality. The other example is quantum speed up in submodels for universal fault-tolerant quantum computation, for instance, in quantum computation by a magic state distillation, or in measurement-based quantum computation. Both cases, one can prove that quantum contextuality is a necessary condition for quantum speed up. So this is, let's say, the kind of the standard answer, but I would say more important answer, the main reason why I think most people should care about quantum contextuality is the following. Quantum contextuality provides a unique clue to understand quantum mechanics. There are lots of quantum phenomena, I mean, entanglement, incompatibility, Bell non-locality, steering, wave particle duality, tons of them, okay? But as far as I know, unlike any other quantum phenomenon, contextuality, the notion of contextuality as presented before, leads to a series of questions whose answers are really illuminating about the question, where does quantum mechanics come from? Okay, so I don't have much time, but I would like to just try to explain in what sense this is true. For instance, we already asked, when is contextuality surprising? And we said, okay, for ideal measurements of ideal observables, yeah, contextuality is kind of interesting, right? Because in classical physics, we don't observe it. Okay, then is, well, in which scenarios does quantum contextuality happen? And that's the first interesting answer. In all the scenarios in which contextuality can happen. Okay, and by this, I mean the following. There's a maybe not so well-known result, but super important result, which is Vorobyov theorem, that basically says that the only scenarios that admit contextual behaviors are those in which the graph of compatibility is non-chordal, that is, contains, as inducer graphs, at least one cycle of 4 or more vertices. I mean, a square, a pentagon, an hexagon as an inducer graph, okay? Which, for instance, implies that the simplest scenario in which contextuality with ideal measurements is possible can happen from the logical point of view. It is the square, okay, which is, if you are coming from Bell non-locality, the familiar Clauser-Simony-Hold Bell scenario. But the interesting point is the second theorem. We can prove that quantum theory produces contextual behaviors with ideal measurements in absolutely every scenario allowed by Borovjev's theorem. Okay, this is a clue from my point of view that is important. And then notice also that thanks to Borovjev's theorem, incompatibility does not imply contextuality. You have this kind of trivial example. The right-hand side has two observables, the red and the yellow, that are incompatible. However, you cannot have contextuality there because of Borovjev's theorem. Okay. So yes, incompatibility is a necessary condition for contextuality, but it's not sufficient for contextuality. Good. We are coming to the, I would say, key question. Is there any theory that is more contextual than quantum mechanics for ideal measurements of ideal observables? Okay. In principle, the answer is yeah, well, probably, right? But the surprise is that the answer is no. Under the assumption that the statistical independence exists, quantum probability theory is the most general probability theory for the outcomes of ideal measurements of ideal observables. Okay. And this is kind of key. Okay. What does it mean? Well, depends on your perspective, but in terms of ontology, it means that there are systems and interactions for which nature has no laws. There's no restrictions, in the sense that every form of contextuality for ideal measurements of ideal observables that is not forbidden happens. Okay. And this is, to me, very, very significant. Okay. People also ask, why not focusing on Bell non-locality? I do agree, Bell non-locality is a spectacular example of contextuality, but the problem is it does not provide a complete enough picture to understand even Bell non-locality itself. For most of the cases in which contextuality can happen, cannot be transformed one-to-one into examples of non-locality. And the examples of quantum contextuality that have guided us to the result I put in the previous slide cannot be transformed one-to-one into examples of non-locality. So we need a kind of stepping back from Bell non-locality into this wider picture under the label of contextuality to really get insight on why contextuality, on why Bell non-locality, and eventually on why quantum mechanics. Okay, another point I would like to mention before entering into the new results is the difference between Cauchy-Specker and Peirce-Mermin proofs and non-contextuality inequalities. In the Cauchy-Specker and Peirce-Mermin proofs, you use two things. On the one hand, the assumption of outcome non-contextuality, fine. But the problem is that you also use properties that do not hold for general models, but only for specific quantum systems. So by themselves, you cannot use any of these proofs to go to the lab and test whether or not nature is contextual, because this is not as in Bell inequalities. In Bell inequalities are inequalities that are completely independent of quantum mechanics. They hold for a class of theories, and you go to the lab, and whenever they are violated, you can conclude that these theories cannot explain what you're observing. On contrast to these proofs by Cauchy-Specker and Peirce and Mermin, the non-contextuality inequalities hold under the only assumption of outcome non-contextuality without any reference to quantum mechanics. And therefore, you can use them to test contextuality in nature. From this perspective, Bell inequalities are a particular case of non-contextuality inequalities. And from a historical perspective, non-contextuality inequalities were actually discovered by George Boole, the father of logic, under the name of conditions of possible experience in 1862, right? Good. Now I'm in position to introduce these new results. The first one is a recent experiment performed in Tsinghua in China, together with a group on Q1 Kim, which is, to our knowledge, the first loophole-free test of contextuality. Has been published last week in Science Advances, and let me introduce this idea. It is true that contextual correlations have been observed in experiments for a long time. I mean, experiment with photons, not to mention Bell inequalities, but there are also specific experiments with photons and contextuality, neutrons, ions, molecular nuclear spins, superconducting systems, and nuclear spins. Okay, there are lots of reference. However, all these experiments have loopholes as non-contextual models assisted by mechanisms that exploit the experimental imperfections can simulate the observed correlations, right? So in that sense, the idea of performing a loophole-free experiment of contextuality was an open problem. What are the loopholes in contextuality experiments? The first loophole, and it's quite a specific of contextuality experiment, is the so-called sharpness loophole, which follows from the observation that the assumption of outcome non-contextuality on which the bound of non-contextuality inequalities is derived is not justified for general interactions or even general measurements. Actually, it's justified, for instance, for the case of ideal measurements. Okay. And most of the experiments, of the quantum experiments, of the measurements in quantum experiments are not ideal. The second loophole is more familiar to the community, is the detection loophole, which exploits the lack of perfect detection efficiency, typically occurring in experiments with photons, and it's common to Bell inequality experiments. And the third main loophole is also specific of contextuality experiment, is the so-called compatibility loophole. The definition of context in contextuality experiment is a set of ideal observables that can be measured ideally, but that are also compatible. So they have a common refinement. Okay. And the problem is that even the best experiments we have, the experiments with ions and sequential measurements, the measurements are performed always on the same system. So we measure two things sequentially, and we think that they are compatible. Basically, they are compatible, but actually the assumption that the observables, I was saying the assumption that the observables targeted in the experiment are really compatible cannot really verify it in the experiment. So on the one hand, we have loophole-free Bell experiments that can be seen as contextuality tests that close simultaneously the detection and compatibility loophole. However, they leave open the sharpness loophole. And on the other hand, we have previous trap ion contextuality tests in which basically they suffer from the compatibility loophole as they require sequential measurements on the same system. So the assumption that the actually measured observables are compatible cannot be verified. So what we did, okay, we consider a system of two different ions, one of ytterbium and the other of barium, both trapped in a 4-rod pole trap. Okay, they are separated, but they are in the same trap. And the good thing about this, this setup is that we can perform sequential, repeatable fluorescence measurements on each of the ions individually. Another good thing is that the detection efficiency here is 100%. To close the compatibility loophole, we target Bell-like non-contextuality inequalities, in particular, one which is exactly equal to the Closure-Hall-Simony hold, in which only 2 observables are measured per context, and each of the observables is defined on a different ion. Okay, and this is the key point. Therefore, these 2 observables that we measure in each context are, following the words of the definition of Chris Eisen, trivially compatible. Okay, they are simultaneously measurable in an uncontentious sense. Okay. Finally, and in addition to this, let's say, physically enforced compatibility, we also work on the fact that technically we enforce the compatibility by choosing ions of different species. And the reason for choosing different species is precisely that this way, each ion requires a different operation laser, a different fluorescence wavelength, and a different kind of detector. So we minimize the possible disturbance between measurements performed in the one ion and measurements performed in the second ion. The actual trap in which experiment has been performed is in the left hand side of the slide, and you'll see in the right hand side the scheme with the ytterbium, the barium, the relevant Raman transitions used in the experiment. The observables measured are pretty much the same observables in standard Bell experiments, but here with ions, there you have the compatibility structures. The non-contextuality inequality looks like identical to the Closure-Hall-Simony hold Bell inequality. There you got the Bell experiments, I mean the results, sorry, and you get the value of the Bell, or in this case, contextuality witness, which is 2.5 with a clear violation. But importantly, before running this test, before checking the value of the witness, we first have to check that the measurements are actually sharp. So this means basically 2 things. First, that whenever we repeat the measurements, we get the same outcome. Okay, and measurement repeatability in our experiment is higher, and is 98.4%. Okay, could be made even higher, but we make the calculations. We basically check that for the 3 families of non-contextual models that can be used mechanism exploiting this little lack of perfect repeatability. This is not important. I mean, the difference between 98.4 and 99.9. Okay. And the other thing you have to check is that the measurements on the ytterbium are not disturbing the measurements on the barium, and vice versa, right? Not because they are different, but you have to really check. And once you have checked everything, and now you have a reason to start believing that the assumption of outcome non-contextuality makes sense here, then you check the witness, and then you notice that something is wrong because you are violating the corresponding non-contextuality inequality. Okay, as I said, this is, to my knowledge, the first experiment in which the 3 main loopholes of contextuality experiments has been closed simultaneously. The second new result I would like to present is a joint work with Stefan Trandafir and Peter Licc that will be in the archive next week. And it's about fundamental magic sets. This requires a small introduction. In the previous slides, I mentioned about Peirce and Mermin's proof of contextuality. I hope some of you are familiar with the magic square and the magic pentagram. The magic square is this construction in the left-hand side of the slide as a set of Pauli observables for a system of 2 qubits with certain properties, while the magic pentagram is a set of 3 qubit Pauli observables with a certain properties. Okay. These properties and the definition, what is a magic set, are important, and is the following. A magic set is a set of Pauli observables, that is, observables represented by n-fold tensor products of single qubit Pauli operators, the identity and the Pauli matrices X, Y, and Z. A set that has all the following properties. 1, its observable is in an even number of contexts, and here by context I mean a subset of compatible observables represented in quantum mechanics by commuting operators and such that their product is the identity, in which case we call this context positive, or minus the identity, in which case we call the context negative. Second property is that the number of negative contexts is odd. Third property is that the set is minimal. So the previous 2 properties do not hold if any observable is removed. And a fourth property that is sometimes demanded, that is a nice property and is also fulfilled by the 2 examples I presented, is a property of symmetry, which is that the hypergraph of compatibility, which is the one in which each vertex represents an observable and each hyperedge represents a context, is vertex transitive, meaning that its automorphism groups acts transitively on its vertices. In simple words, all observables play exactly the same role in the proof. Okay. So yeah, everybody I've heard one way or another about these 2 magic sets, and you can check that actually these 2 magic sets satisfy exactly these 4 properties. But the general question is, okay, good, besides being really beautiful mathematical and physical objects, why are magic sets important in a wider perspective in physics, applications, so on? Well, that's a really long list of reasons. I just collected here some of them. They were introduced because they were simple proof of the Cauchy-Specker theorem, but immediately DiVincenzo and Perez connected them to quantum error correction codes. And then we start using them to, for instance, generating 2 observer Greenberger-Holmes-Seilinger proofs. Immediately they were essential part to define non-local games, were at the core of the definition of state-independent non-contextuality inequality, were used and key in measurement-based quantum computation, stimulate the discovery of Bell non-locality based on local contextuality. Many applications, including surprisingly even quantum gravity. Okay. So in a nutshell, magic sets are simple tools that allow us to capture quantum advantage for n-qubit systems and investigate with them the interface between classical and quantum physics. That is the reason why magic sets are useful in so many contexts, in so many branches of science. So if this is the case, an interesting question is how magic sets are related to each other, especially because there's a very important but probably not well-known theorem by Icqif, which sort of suggests that among all possible magic sets, the magic square and the magic pentagram are special. In particular, the Icqif theorem says that the intersection graph of the context of any magic set, but in which each observable is in exactly 2 contexts, must contain either the intersection graph of the context of the magic square or the intersection graph of the context of the magic pentagram. So in this sense, all magic sets of this kind are derived from the square and the pentagram. Okay. But the question is then, okay, this is a very fine result, but is it true that all sets, all magic sets, or at least all sets with properties 1 to 3 mentioned before, can be reduced either to the square or the pentagram? And then come one observation. In the case of 2 qubits, each Pauli observable can be only in at most 3 contexts. Therefore, the only even number that can be used to define magic sets for the case of 2 qubits is 2. Okay. However, this is not true for 3 or more qubits. So if you go to the definition of magic set, I mean, there's a difference. There's a difference between the definition of magic set and the case covered by Icqif. Icqif focus on the case of 2. So natural question then is, does the conclusion of Icqif's theorem hold if the requirement of each observable being in exactly 2 contexts is replaced by the requirement of each observable being in an even number of contexts? In other words, are there magic sets which cannot be reduced to the square and the pentagram? This sounds, in principle, like mathematically interesting theory, but why should we care about it? Because if the answer to this question would be affirmative, then there's another question, which is of physical relevance. Okay, are the magic sets which cannot be reduced to any magic set with 2 or 3 qubits? And therefore, are there magic sets which are specific, genuine, for systems of a specific number of qubits? Because if this is true, if this is the case, this is important, as we would identify fundamental and simple structures that capture quantum advantage and which are specific for different systems of a specific number of qubits. So this is the motivation of our work. And I will give you the conclusions of our research. And the conclusions are really interesting because the answer to the first question is yes. There are magic sets which cannot be reduced to the square or the pentagram. And yes, there are magic sets which cannot be reduced to any magic set with 2 or 3 qubits. And thus, they are genuine for systems of more than 3 qubits. I won't give here the details on how we reach these conclusions. First of all, because it's not needed, because to really convince you that this is the case, it's enough to present examples. Basically, we've been developing an algorithm for looking this magic sets. The message is that finding magic sets is really a super hard problem. Okay, so the value of the work is the algorithm itself. And after running this algorithm for a lot of time, we have found 4 magic sets exactly with the same definition used before, satisfying exactly the same 4 properties that we put, that the magic square and magic pentagram share. This is the first one. It's a magic set for 4 qubits that has 21 observables and 21 contexts. Okay. And cannot be reduced to the square or the pentagram. Therefore, can be used to certify that quantum advantage in a system of 4 qubits. Okay. This is the second example we found. It's also for 4 qubits, but now has 27 observables and 27 contexts. Remember that all the examples I'm putting also are vertex transitive. Okay. The third example has 5 qubits, 27 observables, and 27 contexts, right? And in addition to these 3, we found another one with 3 qubits, 27 observables, 27 contexts, that has no planar representation with the straight lines as the previous one. You need 3 dimensions to really represent. In the paper, you will see it. And in addition, we have found magic sets requiring 6 qubits, but so far we have found not anyone that is vertex transitive. And actually, we have found many other examples of sets satisfying conditions 1, 2, and 3, but not condition 4, for 3 to 5 qubits. Okay. Okay, what does it mean? Well, it means that the landscape of basic magic set is quite different than the landscape suggested by Icqif's theorem, which was basically, okay, there are 2 magic sets from which the rest of the magic sets derive. Actually, our results suggest that each number of qubits has its own set of irreducible vertex transitive magic sets, okay, which can be used, the elements of each of these sets can be used to capture quantum advantage that is specific for this system with this specific number of qubits. So with this, I would like to finish the talk by just remembering the references on which most of what I said is based. On the one hand, the review paper on quantum contextuality, together with Constantino Budroni, Otto Gune, Matthias Kleiman, and Jan-Åke Larsen. On the second place, the Science Advances paper this week with a group of Ki-Wan Kim. And on the third place, the paper, hopefully next week in the archive, together with Stefan Trandafir and Peter Elisonic. Thank you for inviting me to this nice conference, and I'm open to questions.
Thank Professor Cavallo for your beautiful talk, and now it is open for questions or comment.
Yeah, can I ask a question?
Yes.
Yeah, thanks, Professor Cavallo, for your nice talk. So in the second part, when you generalize these different magic set, they are all the all of them have even number of context or odd number of context also you allow?
In total, they have an even number of contexts, and the difference, if you notice, is that the difference between any of these results and, let's say, the magic square is that here each observable belongs to exactly 4 contexts rather than 2 contexts, as is the case.
Yeah.
Yeah.
So all other results also you all are even number.
Yes. So yeah, exactly.
Any special reason to look into even number case, or means odd is more harder? Yeah.
Oh, the reason is the very definition of magic set. Okay, it's a good question. The reason is because the historical origin of magic set is because they provide a proof of a Kochen-Specker thing, and for that you need, on the one hand, a total of an even number of contexts, and you need some of them to be negative, and in particular, you need an odd number of them to be negative, because in this case, you cannot assign predefined outcomes. Okay, that is the reason of this game.
So another question. Yeah. As you have mentioned, this magic square are important. One important things you have mentioned, then they are useful to construct two-party GHJ kind of proofs. So that, like, if magic square I take, then we require 4-dimensional entanglement for perfect winning strategy. Means two EBIT is required. For pentagon, 3 EBIT is required.
Yes.
So now, is there any result that by C3 system we cannot have a GHJ kind of argument?
No, you can always, I mean, it's gonna be more convoluted, but given any magic set, you can prove that you can produce a bipartite or 2-observer GH set-like thing by giving all the context to Alice and all the context to Bob in the worst case scenario. The beautiful thing about the magic square is that it also works if you just give half of the context to Alice and the other half to Bob, and then you have it. But as I said, it's easy to prove, and probably there are some papers containing the proof already, that for any given magic set, you can produce a bipartite non-local game, a bipartite Greenberger-Horn-Seilinger proof, a bipartite Bell inequality.
Okay. Thank you for this answer.
Thank you for the question.
In the chat box, you can see there is one more question. Do you see it?
Sorry. Okay. Wait. Okay, that's a very good question. I say it loud just in case. Icqif, I get this one, right? Icqif's results uses this Pontryagin-Kuratowski theorem from graph theory. Have you also identified such generic structures in your results? Yeah, it's an amazing question. Actually, I just mentioned half of the results we have in this paper, because Icqif's result basically is an algorithm to identify magic sets given a hypergraph. So a natural question is, okay, you prove that there are magic sets that escape from Icqif's theorem, but then the question remains how you identify them. Is there any algorithm more general than Icqif's algorithm that allows you to identify? And yeah, there is such a thing, and is presented in the paper.
Any more question?
You're welcome.
If there is no further question or comment, then let us thank the speaker once again. Okay.
Thank you.
Okay, thank you, Professor Cavallo.
Okay, now I try to stop sharing the screen.
Yeah.
Which is non-trivial. Sorry. Is it okay now?
Yes, it is okay.
Okay. Thank you very much.
Our next speaker in this session is Professor Lucien Hardy. Yes, he has been very well known, as I know, since 1992, when most of the physicists were thinking there will be no direct proof of Bell's theorem for 2-qubit case. He surprised the community by giving an example where he could show the non-locality in 2-qubit case, like in the spirit of GHZ paradox. He had been Royal Society University Research Fellow at Oxford, and presently he is a faculty at Perimeter Institute, and as all we know, he has taken the challenge of unifying gravity and quantum mechanics in the context of quantum information theory, and today he is going to speak on what is time symmetry in operational quantum theory. Okay, over to Professor Hardy.
Thank you very much. I'll share my screen. Okay. Okay, and you can see that?
Yes.
Okay, fantastic. And I'll just put a
Yes,
timer on. Good. Okay, thank you very much for the introduction, and thanks for the kind invitation to this conference. It's great to visit India, virtually at least. So this talk is about time symmetry in operational theories in general and in quantum theory in particular. And also, if I get a chance, I'll talk a bit about conditional frames of reference, which have a bearing on this same subject. The talk is based on a paper which is on the archive, which it's a very long paper. It's 150 pages almost. So hopefully this talk will provide an introduction to that in case you're interested. Okay, and the picture there is one of the proofs in the paper. Okay, so first of all, introduction. Well, the subject of time symmetry has a long history in quantum theory. Back in 1926, Schrödinger wrote down his equation, and that equation was time symmetric, and that accorded with the sort of mindset of the day. Physics previous to quantum theory was also time symmetric, and so everything was as it should be. But then a few years later, von Neumann introduced his collapse postulate, projection postulate, and this looked like it introduced a time asymmetry into quantum theory. After the state would evolve, and then you perform a measurement, and then the state would collapse, and then you could carry on evolving it, which looks like a time asymmetric situation. But then in 1964, Aharonov, Bergman, and Leibovitz showed how you could actually still construe quantum theory as being time symmetric, and they did that in this pre and post selected formalism. So if you think of pre and post selection systems, so you have some pre-selection in the past and some post selection in the future, and you're interested in measurement results at an intermediate time, then everything goes back to being time symmetric. And so for a long time, that was thought to be the way it was. But then in 2010, Chiribella, Perinotti, and Dariano wrote down what I call the Pavia causality condition. And that showed that quantum theory was actually, the operational quantum theory, I should say, was actually time asymmetric. There's a difference. So the work that Aharonov, Bergman, and Leibovitz did was in the context of pure states, whereas the Pavia causality condition applies to the general case of mixed states. And so this causality condition seemed to show that quantum theory in this general case was time asymmetric. Actually, really what they did is write down an alternative version of the rule that the operator should be trace non-increasing. And trace non-increasing is really a different way of saying, is a way of introducing a time asymmetry. And then there's been recent work by myself and others, which seems to restore time symmetry to quantum theory. So you can see that what's happened is we keep going backwards and forwards. The pendulum keeps swinging between time symmetry and time asymmetry. And it's not quite clear where it will end. There are certainly time asymmetric clouds on the horizon. I mean, of course, it's clear that in fact the universe is time asymmetric in some sense, and so ultimately we have to account for that. In any case, I'll tell you the story of this recent work of mine and has a bearing on other people's work as well. Yeah, the recent work. So in the operational context, a few years back, Onion Oreshkov and Nicholas Cerf wrote this paper, number 1 on that list. And then, and what they did is really a very different formulation from the formulation I'm going to give you, but they gave a kind of time reversal, a time symmetric version of quantum theory. A paper more recently by Andrea Di Biagio and co-authors is much more similar to the kind of work I'm doing, and in some sense the work I'm going to present builds on that work. So I recommend that paper. It's a nice short paper. I recommend that paper to you. And then there's been other work also recently. There's some references there on this slide. Okay, let's look at standard operational quantum theory. Operational quantum theory is the theory of density operators, completely positive maps, trace, POVMs, and so on. It's a framework which has its roots back in the 1960s, or actually even much earlier, 1960s and 70s especially. And it's something that's very well known to people who work in quantum information theory and quantum foundations. It's not so well known outside of those communities. A lot of people think that fundamentally we should talk about pure states, and that mixed states are a sort of a necessity to deal with real experiments, but fundamentally pure states are what's important. Whereas some people, myself included, take the point of view that mixed states are what is fundamental. In any case, standard operational quantum theory applies to the sort of latter point of view. And in standard operational quantum theory, you have operators which have to satisfy what I call physicality conditions. And there's 2 physicality conditions. The first one is that these operators are completely positive. And I've given you a diagram which expresses that condition in my own notation. And this condition is a time symmetric condition. What this condition says in quantum theory is that if you take the adjoint over the, if you take the transpose over the input space or over the output space, then you should get an operator which is positive. Okay, it's equivalent to the condition that the map should be completely positive in the usual sense. So this is a time symmetric condition. And then there's a second condition, which is that the operator should be trace non-increasing. And here's a diagrammatic way of representing that condition, which has to do with the Pavia causality axiom. And this says that if you have some operator associated with a box in your laboratory, there's a system A coming in, a system B coming out, and then you trace over the output, well, that should be box should be less than or equal to the effect of tracing over the input. This is a time asymmetric condition. And so this is where the time asymmetry comes into standard operational quantum theory. There's another place you can see it, which is that operators in standard operational quantum theory can be written in the Stein-Spring dilated form. So you have some operator here, and you can write it by introducing an ancilla. This is W in my notation, prepared in some initial state here, and then you act on that joint system with a unitary process here, and then afterwards you trace over some subsystem, the Z subsystem here, and the V subsystem goes forward. And you can write down any operator in this form. But you can see this is time asymmetric because the preparation of your ancilla is a pure preparation, and the Whereas on the other side, this trace is not a pure operation. So these are different kinds of thing. Okay, so it's odd that operational quantum theory is time asymmetric for various reasons. Well, first of all, abstract probability theory concerns calculations of objects like the probability of A given B, and so on, and it doesn't know anything about time. You know, a conditional probability A, so a probability of here I have X given Y, a conditional probability like X given Y, you don't really care whether X is in the future of Y or to the past of the Y or whatever. Probability theory doesn't really care about causal relations. So it's odd that nevertheless that operational quantum theory, which is all about probabilities, becomes time asymmetric. Secondly, quantum theory at the level of the Schrödinger equation is time symmetric, as I discussed earlier. Third, the quantum theory of measurement can be treated very simply without reference to the second law. So the von Neumann model of measurement, for example, it doesn't use entropy or entropic considerations. It is a very simple model. Of course, real measurements in a laboratory will involve entropic considerations, but the essential features of those measurements can be captured in these very simple von Neumann models. Okay, so we'll see how you can formulate operational quantum theory in a time symmetric way. And the physicality conditions, what I had earlier, now get replaced by time symmetric physicality conditions in this new formulation. And these are the following. We have a positivity condition. This is very similar to the positivity condition you get in standard operational quantum theory, and I won't dwell on that too much. It ensures that that circuits, when you calculate probabilities, have positive probabilities associated with them. And then the interesting condition is what I call double causality. And this condition looks like this. I'll explain in detail later what this means. There are many of these double conditions in this work. And double condition is where you have one condition which, where you have two conditions which are kind of the time reverse of each other. So you can see this condition and this condition are the time reverse of each other. So we'll have lots of double conditions. So these physicality conditions are time symmetric. We also get a time symmetric dilation theorem. So a general operator like this can be expanded in a way which is time symmetric, and I'll talk about that a little bit as well. Okay. Well, first of all, let's talk about operations and circuits. The standard notion of an operation looks like this. You have some inputs, what could be quantum systems coming in, and some outputs, quantum systems going out. Then you also have a choice of settings, so you adjust some knobs on your device, and then you have some outcomes. So you have a light that flashes or detector clicks, something like that. Okay, so these settings and these outcomes are classical. And we can just look at that a bit more. We can see that there's a difference between settings and outcomes. Settings are actually available before and afterwards. You can look at the knob on the box and see where it is both before the experiment, before the operator is used, or the operation is used, and after the operation is used. So so here we've represented it now more accurately. Whereas the outcome is only available afterwards. It's not available before. So this diagram here is a better representation of what's going on. And now you can see that it's time asymmetric. So this basic notion of an operation in operational theories that's used is a time asymmetric notion. And so it's not surprising that operational quantum theory is time asymmetric. But fortunately, you can make it time symmetric. All you have to do is introduce an extra arrow here and give it a name. So if this is called an outcome, I'm going to call this an income, because this is something that comes in. So outcomes are only available afterwards. Incomes are available before, but not afterwards, within the context of this operation, So an example of an income in quantum theory would be if you send if you have something that prepares a quantum system in one of a basis set, okay, of states. So you send a system in one of the basis set of states, then this operation will eat up that quantum system, so you won't have it available afterwards. So that's an example of an income. But the income is it's the classical label of the basis element. So incomes are classical, just like outcomes. Okay, now mostly in this work, I'm going to take the settings to be implicit. So I won't have an arrow. So I'll just get rid of the arrow for the settings and take those to be implicit, and I'll focus on the incomes and outcomes. So we have incomes and outcomes, which are classical, inputs and outputs, which in the quantum case are quantum, and the settings are taken to be implicit. Okay, and a bit more notation. I'll use this kind of font to indicate, so bold font down the bottom here to indicate incomes and outcomes for the quantum systems or whatever systems you have. And I'll use typeface font here and here to indicate the income and the outcome. So these are the classical. One other point is I could have made these wires come in from the bottom and go out from the top. So the X and Y the X could come in from the bottom and the Y could come out from the top. And that's just a sort of notational choice. It seemed to me useful to discriminate between income outcomes, which have a particular role in the theory, and inputs and outputs, which have a different role. Okay. So the incomes will take values. So here we're representing by typeface font the types, and then the particular values they take will be given by X in this notation, and take values 1 through n sub X, and Y will take values 1 through n sub Y. Okay, so those are the actual values of those classical incomes and outcomes. When you form a circuit, you wire together a bunch of these operations, and here's an example of a circuit. And you can see what we've done is we have an income, and then we have a particular value on that income, X, and then we also have some initial operation here, which is preparing a distribution of values. And then we have another case here. Here's an outcome, Y, and we have a operation at the end of that, and so on. Okay, so here's a circuit. A circuit is a case where you have no open wires left over. And what we're interested in is the joint probability for the incomes and outcomes. So here's the joint probability of getting X, Y, and Z. So this joint probability is probability incomes, comma, outcomes. But you could consider different points of view. So the point of view I just expressed was what I call the time symmetric point of view, and it's where you consider the joint probability of incomes and outcomes. You could also consider the time forward point of view, where you have the probability for some outcomes given some incomes, and that's the standard thing. Generally, you set your incomes to be certain values, and then you look at the probability of outcomes. A time backwards point of view would be where you look at the probability of some of the incomes given post-selecting on some outcomes. And okay, so the standard operational framework is in the time forward point of view, this one here, and I want to work in the time symmetric point of view. The paper by Andrea Di Baggio, Donna, and Ravelli took a sort of different point of view, and it showed that there was a symmetry between the time forward and the time backwards point of view. Okay, so in the time symmetric point of view, we demand that we get the same answer whether we calculate this probability for incomes, this joint probability for incomes and outcomes. We demand we get the same answer whether we do that in the forward direction or the backwards direction. So let me, I'll discuss what that means in detail in a bit. Okay, let me give you the definition of what I mean by a time-symmetric theory. We'll say that an operational theory is time-symmetric if every allowed operation can be mapped to an allowed time-reversed operation. So here's an allowed operation A, and here's the time reverse, and you can see that X and Y have changed places, and also the inputs and outputs have changed places. And the second condition is that any given circuit E that we obtain, we can obtain the time reverse circuit by inversing the graph and replacing operations. Then we require that the probability of E is the same as the probability of E tilde. Let me show you an example of that. So here's a circuit. It's the same one I showed you earlier. And here's the time reverse of that same circuit. So A has been replaced by A tilde, B by B tilde, C by C tilde. And we demand that you get the same probability. This is the joint probability over incomes and outcomes in both cases. If this is true, it means that for every process described in the forward direction, there's a corresponding process described in the backwards direction with the same probability. Okay, so in this talk, I'm going to talk about physicality conditions in the sort of general operational context. And then I'll talk about about quantum theory, and then if I get time, which I probably won't, I'll talk about conditional frames of reference. But first of all, I'm going to talk about some double properties for a simple classical situation. Okay, so here's a very simple circuit where I've got some operations here. And I have incomes coming in from the left and outcomes going out from the right. And then what I can do is I can represent that thing here by this box here, where I simply collapse out the physical systems A, B, A, C, C, B. I collapse them out and I get this. And so an M now is a classical box, but it has some physics, which may be quantum physics, hidden inside it. Then I can simplify this a bit further. If I take M like this, I can represent by U and V the composite systems. So I can represent this whole thing by this very simple classical box. And this very simple classical box, in some sense, holds the key to understanding time symmetry in operational theories. So let's look at this box a bit more. So we'll take that box M and we'll send in a distribution over its incomes. We'll pass through here, and then we have some outcome, and then we finally have an F box at the end. So you can do a calculation for the joint probability over U and V. U is the income, V is the outcome. We can do a calculation for the joint probability in the forward time direction. So to do that, we first of all take the distribution over U, and then multiply it by, we take the probability for a given U, and then we multiply it by the conditional probability for a given V, given that U. Okay, so this is a standard calculation in probability theory. We can do the same calculation, but backwards in time, so calculate the joint probability backwards in time. So now we have a distribution over V coming from F, that's this, and then we have the joint probability of U given V. So this is standard probability theory again, same kind of calculation, but backwards in time. And we demand that these probabilities are equal. Because remember earlier I said that we demand the joint probabilities are equal whether you do the calculation forwards in time or backwards in time. So we have this property. So I'm going to take that equation on the bottom of the page. And that you can do exactly the same thing. Instead of having E and F, you can have E prime and F prime. Okay, we do the same calculation. So I'll take those two equations that I just derived, this one, and divide them, and you get this equation. And you can show, if you using the fact that probabilities have to add to 1, you can show that this equation implies that the distribution over U according to E is equal to the distribution over U according to E prime, and the same for F. This is true as long as you have non-zero probabilities for the conditionals in the right places. So what this is saying is that actually you have to have a unique distribution. If you want to get these time symmetric probabilities, you want to get the same answer whether you do the calculation forwards in time or backwards in time, then actually you have to only consider unique distributions coming in and distributions coming in also from the future. Okay. Okay, so yeah, I'll call that double distribution uniqueness. One way to achieve this double distribution uniqueness is to only consider flat distributions. So we only consider distributions where you have a flat distribution over the incomes coming in and also over the outcomes coming in from the future. And then secondly, we impose double flatness. I'll explain what double flatness is in a few slides. So if we impose these two conditions, then we can achieve double distribution uniqueness, this property. Double flatness is a property that holds in quantum theory, and it's deeply related to the thing I'm going to call double causality. So it relates to causality properties in this time symmetric setting. Okay. So the first point means that in the time symmetric point of view, we're only considering circuits that have a flat distribution, okay, where this R indicates a flat distribution. We only have flat distributions on the incomes and outcomes. And this is necessary, so we get the same probability whether we do the calculation forwards in time or backwards in time. And then also we impose a condition called double flatness. And double flatness is the property, if you just look at the diagram at the top, so there's forward flatness, and that means that if you send a flat distribution in, then you get a flat distribution out. And there's backwards flatness, which is the same thing in the reverse time direction. If you send a flat distribution in from the future, you get a flat distribution out to the past. Okay, so these properties are true in quantum theory, as you'll see, and it is essential to have this to make this whole thing work, to get this time symmetry. Okay, so we want to impose physicality conditions that guarantee two things. We want to guarantee complete positivity. This just means that probabilities for any circuit you build are non-negative. And we also want double flatness, the property I just talked about. And we'll see that we can get these conditions if we impose two conditions. We impose what I call T positivity, that guarantees complete positivity, so circuits are positive. And we impose double causality, and this guarantees double flatness. And I'll skip over the bit about T positivity because this is reasonably standard. Okay. And I'll go on to the second bit, which is about double causality. So first of all, I need to introduce this idea of an ignore preparation and an ignore result. So here's an ignore preparation. So this is a preparation where we essentially ignore what comes in. We have a flat distribution over the quantum system coming in. This is like a completely noisy system. So in quantum theory, this will be represented by preparing the completely mixed state coming in. And we also ignore what goes out. So this is this is represented by taking the trace over the outcome. Oh, sorry, over the outputs. Okay. So I'm using, my notation is with the box with the I in it, and the standard notation that you'll find in the literature quite a lot is this Earth symbol. So we can prove using some very basic linearity properties that these ignore preparations and results are unique, meaning that there's only one way of ignoring the future and ignoring the past. Okay, so here's the double causality condition. So if we if the operation here satisfies these two conditions, then we say it's doubly causal. Okay, and this is the case in these theories. So the forward causality condition is where you take the operation, you have the ignore preparation and a flat distribution coming in over the incomes, and that should be equivalent to the ignore preparation here on the output and the flat distribution here over the outcome. And then you have the same thing in the backwards direction. Okay. So that's the double causality condition. And this is, in some sense, the substantially new result in this paper. This replaces, in the time symmetric setting, the physicality condition we had for standard operational quantum theory, the second of those physicality conditions. Okay, and if you take that condition, what you can do, well, here it is again at the top of the page, and you can regard various of the systems here as being the trivial system, so that then you just ignore it, you get rid of it. So the trivial system in quantum theory would be a system that had Hilbert space dimension 1. So, for example, if I take this input here to be a trivial system, then I can get rid of this box. So I just have this, and this condition simplifies to this condition. So here are various conditions. I've written them here in this table. This is not exhaustive, but here's the various conditions that you get by simplifying, by treating some of the systems as trivial systems. And interestingly, one of the conditions you get is double flatness. So you get double flatness back from double causality. Here it is. Another condition you get is the Pavia causality condition. Here it is. You also get the time reverse of the Pavia causality condition over here, and many other things. Okay. Let me show you double causality in action. So here are some boxes wired together, and they have open incomes. And now I know from backwards flatness that this whole thing here should be equivalent to just for having the flat distribution of this Z, S, Y, and X, Ys. Okay, that's an application of double flatness, but it's interesting to see how it actually works out. So let's take this circuit again, and I'm going to start by replacing the box up here with the box I get from the double causality condition. Okay, so I've done that, and then I can go a step further. I can replace this here with the box I get from double causality. So now I get this circuit, and then let's carry on. Now I perform another replacement and another replacement, and then you derive this backwards flatness. So I'll just go through those steps again. You perform these replacements, and at the end of that, you derive the results you wanted. And it's interesting, if you take these kinds of circuits, lots of circuits will simplify if you replace the double causality conditions in them. Okay. What about quantum theory? So in quantum theory, you have operators, and the framework I'm using is this sort of operator tensor formulation, which you may or may not be familiar with. If you're not familiar with it, don't worry, just look at the pictures. So you have an operator here. This operator belongs to a Hilbert space, which is indicated by the wires coming in and going out. It also has classical. It also has a classical wires coming in and going out. So it belongs to a space that's defined by a Hilbert space and also some classical spaces. And you can set up a correspondence from operations. These are the things that happen in the laboratory to operator tensors. So we get the correct probabilities for circuits. That's how the operator tensor framework works. And then in this context of operator tensors, you can impose a T positivity condition, which I won't talk about, but it's sort of the same as in standard operational quantum theory. And you can impose the double causality condition, which looks the same as a double causality condition before, but now it's for operators. Okay, and these conditions are time symmetric. So these are these conditions. There's a curious issue that crops up in this way of representing quantum theory, which is that you get a gauge parameter appearing in how you represent your ignore operators. So here's the ignore operator associated with a preparation. And remember, I told you that that's the same as the totally mixed state. If it was the totally mixed state, then this alpha here would be equal to 1. So it actually would be equal to 1 over root n, because the totally mixed state in standard quantum theory is given by the identity over n. But actually, you have a freedom to put alpha equal to anything else. And likewise with the ignore result, well, this is usually thought of as the trace, but actually this alpha means that you can write it down in different ways. It doesn't really matter what value you choose for alpha, you'll get the same answers. In standard quantum theory, we write alpha equal to 1 over root n, but another choice would be alpha equals 1. You could choose any real value for alpha. Okay. In this way of formulating quantum theory, it's possible to give a dilation theorem, and you can show that any physical operator like this can be represented in this dilated form, where you introduce ancillas, sort of pre-ancillas and post-ancillas, and you have a big unitary operation in the middle. Now, if you look at this, you can see it's time symmetric. So the what happens is the wire corresponding to the income gets converted into a box which prepares one of a basis set of for this quantum system. Then also you have a ignore preparation, it's like the totally mixed state coming in. Then you have ignore result, which is a totally mixed state going out. And then here you have you post-select on a basis set of quantum states. This whole thing is time symmetric. And it's interesting to prove this theorem. It's not simple to prove, but the proof is like the standard Steinspring proof, although I think it turns out to be more elegant in some ways, but I don't have time to talk about that. If you have an operator like this, you can write it down in its Steinspring dilated form, and then you can use that to find the time reverse of that operator. So you take the adjoint of this unitary, and you change the boxes from the bottom to the top. Interestingly, these gauge parameters make an appearance as a prefactor. So this box here is a prefactor. If you can set these gauge parameters to be equal to 1, in which case the box disappears. So you can use this dilation to calculate the time reverse of any operator. Okay, I have a bit of time left, so I'll talk a bit about conditional frames of reference. So if you have this circuit here, what you're calculating is the conditional probability over incomes and outcomes. But you might instead be interested in calculating the probability over outcomes given certain incomes. That's what you do in standard quantum theory. And this box here with the arrow on it, with the angle on here indicates pre-selecting on X. Well, you can use the framework I've set up to calculate that just using the standard rules of conditional probability. So this probability here is just equal to, well, the joint probability on the top, and then the same thing on the bottom, but where I've got rid of these boxes where I select on a certain outcome. Okay. And now we know that this denominator is equal to 1 over nx, ny, nz. We know that from backwards flatness. So this is a constant, this denominator, and it just gives us a prefactor of nx, ny, nz. So that means that we can write this probability here, where we're pre-selecting, as being equal to this probability, where I've now got these angle things, where I just define that this box here, this x box, is equal to nx times the r followed by x thing we had before. Okay, and this nx here is the appropriate prefactor that we got from this, sorry, this denominator. And the boxes on the outcomes just remain the same. We can say that the forward conditional frame of reference is given by choosing, if I look at this diagram again here, we can make different choices for these income boxes and these outcome boxes. The forward conditional frame of reference can be given by this replacement, where you've got the prefactor here over the incomes, the outcomes to stay the same. You can have the backwards conditional frame of reference, where you put the prefactor over the outcomes, and that gives you, use that to calculate the probabilities of incomes given outcomes. And then the time symmetric conditional frame of reference is where you have just the original thing with no prefactors, and use this to calculate time symmetric probabilities. So what's interesting here is that there are sort of different ways of thinking, different sort of almost, they're really like transformations you can perform, where you're calculating either probabilities of outcomes given incomes, probabilities of incomes given outcomes, or joint probabilities of outcomes and incomes. And these are sort of like conditional, these are like choices of frames of reference. And a question is, can you have a continuous set of conditional frames of reference? Well, you can set that up, and a way to do that, I've just indicated it on this slide. I think I won't go into great detail, but basically you can introduce a box S and T. This is a bit more general, and you can show you can show that you can recover the 3 special cases I discussed earlier just by making particular choices in these boxes. Okay. Okay. So this time symmetric formulation, you can show it's equivalent to time forward quantum theory, because you can always transform into the forward conditional frame of reference, and you get the same answers as you would expect to get in forward operational quantum theory. You can also transform into the backwards conditional frame of reference and get backwards quantum theory. So the formulas, the framework I've shown you is equivalent to standard quantum theory. It's really just a different way of formulating it. In fact, I would argue that the time symmetric setting, where you calculate joint probabilities of incomes and outcomes, is a more natural way of looking at the theory. The time forward setting that we normally employ, although it sort of relates to our experience more naturally, it's a less natural way of looking at the theory. look, you can play various interesting games. So you can take an experiment. So here's teleportation. You have you prepare some Bell state. So if x takes a certain value, then you prepare if x takes the value 1, then you prepared a certain one of the Bell states, and then you have a system coming in a certain state, and then you send the outcome there into the income, and this will be the classical information that's shared in teleportation protocol, and that sets a unitary, and then you recover the state that you sent in originally. You can, if you do that, you can then find a time reverse setting, time reverse experiment. This is just the time reverse of the teleportation, and it's interesting to look at this and see how it's different from the standard teleportation protocol. So this is a fun thing you can play, a fun game you can play once you've got this time symmetric framework. Okay, so let me conclude. So one question is how should we interpret these results? And we know that the world itself is time. Well, maybe I'll discuss that point later. So what is the interpretation of these results? So the double causality condition, in some sense, the causality condition tells you that you can't signal from the future to the past. So it would seem that the double causality condition is telling you that you can't signal from the past to the future, or from the future to the past. And there's some sense in which that's true, but it's a bit more subtle than that. There's questions about porting classical information around, which become very interesting in this framework, but I won't discuss that. The time symmetric frame is the most natural frame. I mentioned that already. It's in some sense an analog of an inertial frame of reference, which is the most natural frame of reference in general relativity. If we work in this time symmetric setting, can we find better axioms for quantum theory? My hope is yes. If this time symmetric frame is more natural, then perhaps that's the best place to derive quantum theory. Will this help with quantum gravity? My reason for studying this in the first place was because of quantum gravity. Well, there's more questions here. I put this point in just in case Chris Fuchs was in the audience. And then there's time symmetric clouds on the horizon. We know that ultimately the universe is time asymmetric, and we have to account for that. And this is problematic in the framework I've shown you. So that's definitely something that we need to work on. And yeah, I'll stop there. Thank you very much.
Thanks, Professor Hardy, for your beautiful talk. Now it's open for question or comment. Yeah, Professor Warner.
Yeah, I have a couple of short questions. One is, you're always saying that you were saying that quantum theory satisfies this, but what about infinite dimensional Hilbert spaces, continuous variables, and all that, where you really don't have a flat distribution?
Yeah, I mean this is definitely I formulate this within the finite dimensional setting.
Yeah, sure. Yeah.
And I think that's a challenge, that a technical challenge I have to work on. Yeah, I don't have a very good answer to that question at this stage. I mean, there's sort of trace operations play a role in all sorts of places in finite dimensional quantum theory, throughout quantum information and so on, and so that's a challenge, generally speaking, not just here.
You can sort of make adjoints like this, like always something going the other way. If with every system you assign some faithful state, so like Burckhardt-Kümmerer's quantum probability theory does that, and they have an adjoint, so which would play the role of your time reverse thing. So there you don't need a trace, actually. Maybe you want to have a look at that.
Yeah.
But
okay,
but also I would be curious to hear what you think about the causal nets, or I mean, there's a difference between the inputs and the outputs, in the sense that you can choose the one, but the other one is spontaneously generated. So we had a talk by Tony Yassine on causal nets, which and that's certainly popular stuff these days. So how would you relate to that?
Yeah, I'd have to look at the detail. Are they working? Are they still making time asymmetric?
That's totally asymmetric because you have arrows all over the place, right?
Yeah. Well, arrows don't have to be time asymmetric as such. It's just
sure. But the understanding is definitely that that certain variables can be causes of others and not the other way around.
Yeah. Okay. So I'd have to look at it in detail. I mean, my hope is that this sort of time symmetric setting, this time symmetric way of thinking about things, is in some ways more natural. Maybe it's less intuitive because it's not.
Maybe it's just not right.
But mathematically, maybe. I mean, one place where it becomes more natural mathematically is when you're proving this dilation theorem. The standard proof of Stein-Spring dilation theorem, it really doesn't get. You prove that the unitary operator exists, but you don't use both parts of the property of unitarity. So you only really prove that an isomorphism exists. But isometry exists. Sorry. Whereas here you end up using both conditions for unitarity, and so it seems more natural in a mathematical sense than the standard one. So as you work with this, there's a sense in which it's more natural. My worry is there's what I call these time symmetric clouds on the horizon that you have to account for the fact that the universe really does appear to be time asymmetric, and I'm thinking about that.
So thanks for now.
Thank you.
Is there any more question? Orchon.
Yeah, hi Lucian, great talk.
Thank you.
Maybe doesn't relate to the technical analysis of your talk, but somehow maybe presumably the spirit of your conclusion. So if we come to the recent developments in superposition of causal orders, so do you think that in a certain sense that it indeed vouches for time symmetry, because without time symmetry it will be hard to superpose causal orders, and as a corollary the performance of a quantum switch experiment maybe somehow gives a quote-unquote proof of time symmetry in operational quantum mechanics.
So I missed what kind of experiment you mentioned there.
Quantum switch.
Switch. Okay. Yeah. So definitely this was my motivation for working on this time symmetry. That when you have indefinite causal order. So actually, I would actually refer to what I think I'd call indefinite causal structure, which is a slightly more general concept. So in general relativity, you have this time symmetry because the light cones can point in either direction, and so it's weird that in quantum theory you seem to have this time asymmetry. And so if you start to have superpositions of different causal structures in the context of quantum theory, but you still have this time asymmetry, it looks like it's going to be difficult to make that fit with general relativity. So for me there was a kind of tension there. That's maybe not. That's more of an intuition. I don't have a very formal way of stating that. So I was motivated to consider that exactly because of indefinite causal structure. But I haven't done anything with that yet. I mean, I feel like time symmetry is part of the problem of taking an operational approach to quantum gravity. The experiments. I don't know. I don't have any particular comments on the connection between this work and those experiments, I'm afraid. Thank you for the question.
Yeah, Manik.
Yeah, thanks, Professor Hardy, for this nice talk. So my question is what Professor Warner asked, continuing that. So in time asymmetric formulation, this income is chosen by agent, where outcome is continuously generated. But in time symmetric formulation, now incomes and outcomes are nearly same footing. So the role of agent is less here in this time symmetric formulation. Is my understanding correct?
The role of what is less?
Agent.
Right. Yeah. Okay. Yeah. Okay. This is a good question. So I distinguished what I called incomes and settings. So settings, you typically think of, on a stone gullet, for example, you have a knob setting that you can vary continuously as you change the angle. Whereas incomes, I typically think of those as being as discrete, associated with, for example, you send in a quantum system in one of a basis set. But you might ask the question, well, can I choose my income? I mean, okay. So in some sense, you can certainly consider that possibility, and that just corresponds to conditioning on that income. And if you condition on that income, then you're typically going to calculate the probability where you pre-select on incomes and you look at the probability of outcomes. So you'd be in the time forward point of view. But you might also condition on outcomes. So there is a question how you sort of fit this idea of incomes with our usual notion of agents, and this is something I'm still struggling with. One idea I have is to treat agents, so to have an actual model for how agents work. So to treat them somehow within this model, maybe still classically, but nevertheless treat them within the model, and then see how they fit into the model. So how they fit into the model as boxes and so on. I'm thinking that may be a way to remove some of these time asymmetric clouds on the horizon. So yeah, so that'd be a way of dealing with the question of agency, and then perhaps also understanding where time asymmetry comes in.
Thank you.
Any more questions? So if there is no further questions, let us thank the speaker once again, and thanks to all the participants also. So today, we conclude this session, and tomorrow we will start at 11. Okay, thank you all.
Thank you.